Good morning, everyone. As the unbridled intoxication of day one of a conference gives way to the soberness of day two, I'd like to, welcome you again to another fun day of activities. So what we like to do at RSS for the keynote sessions is to have one of the keynotes be from a person who's from our community and another from a person who's from a bit outside of our community. And so I'm really excited to announce our program. Our second keynote is from a distinguished biomedical researcher who's been working on body sensors. Very exciting stuff, very distinguished career, John Rogers from Northwestern University. Later in the afternoon, we're going to have an early career spotlight talk from Jens Kober of TU Delft. And we also have one of the highlights of RSS, the banquet. This is a very exciting banquet going to be on a cruise throughout New York Harbor. We have a lot of detailed information about how to get there. It's going to be a little bit of an adventure for some of you, so we'll stay tuned in the afternoon for some of those instructions. But without any further ado, let's get started with the program. So we do have some hybrid sessions during RSS. We're going to be switching off between virtual and in-person presenters. Fingers crossed that all of this works. We have not tried this yet, and so we're hoping that it does work properly, but please bear with us if we have any technical difficulties. Also, I will just say again that we do take COVID seriously. Please do wear your masks. We have had actually 3 presenters who will be presenting tomorrow come down with COVID yesterday. So, and they haven't, well, this is maybe a bad argument for wearing masks, but one of them was saying he's wearing masks the whole time, but he still got COVID. It is a very transmissible disease, so please be careful out there. Okay, without further ado, let me get started with Kostas Spekris, the chair of the first session.
Great. Good morning, everyone. This is paper session 5. So it is indeed a hybrid, short and long talks. We're going to have 3 virtual talks first, but the presenters will be available online for questions. So please prepare your questions for them. We're going to have 5 talks, then a Q&A session. So the first talk is going to be Embodied Multi-Agent Task Planning from Ambiguous Instruction.
Multi-agent task planning from ambiguous instruction. In human-robot collaboration scenarios, instructions given to robots are likely ambiguous, as humans always omit some information in instructions. Meanwhile, the visual perceptions of robots are updated continuously. In the task planning process, multiple robots need to retain the missing information, dynamically decompose and allocate subtasks based on their visual observations to complete the task collaboratively. So we want to tackle these challenges in this paper. We propose a multi-agent embodied task planning framework, develop a learning method which is effective for both simulation and real-world scenarios, and we perform evaluation experiments with newly built benchmark datasets in both simulation and real world. We propose a new framework. Given a high-level ambiguous instruction, missing information and subtasks are generated based on knowledge reasoning, and then subtasks are allocated to a group of agents. With the change of visual observations, agents need to dynamically adjust the task decomposition and allocation results to complete the whole instruction as soon as possible. We construct a new benchmark dataset based on off-rate. We propose 3 types of tasks, and in each type, there exists the implicit receptacle that needs to be retained in the ambiguous instructions. We also generate the expert demonstrations for model learning. There are 4 modules in our proposed model. The scene encoder extracts the semantic scene features based on the pre-training method. The task planning consists of decomposition and allocation parts. the task decomposition part dynamically enforces the implicit receptacle and generates the subtask sequence. The task allocation part dynamically allocates subtasks to each agent based on their predicted distance to target objects. The communication module exchanges the information among multiple agents based on the multi-head attention structure. And the action module predicts the next subgoal for each agent and generates low-level actions. We use imitation learning to train the whole module. The semantic perception and subgoal prediction bridge the gap between the simulation and the real-world scenarios. In our experiments, we have easy and hard settings in both simulation and real world. In easy setting, targets and agents are in a single room, and in hard settings, targets and agents are distributed in different rooms. We compare different task planning methods, and our model with dynamic task decomposition and allocation methods achieves the best, except for Oracle methods. And we compare multiple agents with single agent methods. Our model with multi-agent methods achieves better results. We will show qualitative results in both simulation and real-world environments, in both easy and hard settings. In this easy task, the instruction is put the cup away. The carbonate is reasoned to be the receptacle. Based on visual observations, subtasks are reallocated. In this hard task, the instruction is clean the plate and put it on the desk. The sink is inferred to be the receptacle. Based on the visual observations, the agent 2 finds that the desk is in another room, then it enters another room and completes the task. In the real-world scenario, the instruction is freeze a bottle of water. The fridge is inferred to be the receptacle. They find the bottle and the fridge, and finally the bottle can be put into the fridge. In the hard setting, the instruction is bake the apple and put it on the dining table. The microwave is inferred to be the receptacle. After they find the apple and can put it in the microwave, the agent 1 needs to put the apple on the dining table, and it notes from the agent 3 that the table is in another room. Then it goes to another room to find the dining table. That's all. Thanks for listening.
Great, and the next virtual talk is going to be Data Augmentation for Manipulation from the University of Michigan. Peter Mitrano.
And I'll be discussing our paper titled Data Augmentation for Manipulation. In this work, we propose a data augmentation algorithm to increase data efficiency for learning robotic manipulation. Data augmentation has been used to great effect in computer vision. For instance, in an image classification task, we can sometimes apply random rotations or crops to the input without changing the class label. Prior work has shown that models trained on these augmented examples generalize better than those trained without augmentation. However, these methods are specific to both data type and task. Although there are well-established augmentations for image and text, the same cannot be said for robotics. We aim to augment trajectories of geometric state and action data. This includes data like object poses, joint configurations, voxel grids, and point clouds. Furthermore, we focus on short trajectories where some objects in the scene and/or the robot are moving. Additionally, we demonstrate the proposed method on both classification and regression problems. I will now describe our proposed augmentation method, then present our experimental results. The correctness and efficacy of our method is subject to the following assumptions, which are discussed further in the paper. At a high level, our method produces augmentations by applying a rigid body transformation to objects in the scene. Specifically, we divide objects in the scene into 3 categories: the robot, the moved objects, and the environment. We frame augmentation as the following optimization problem, where we consider 3 terms: validity, relevance, and diversity. We define an augmented example as valid if it obeys the laws of physics. Augmentations are relevant if they are similar to data that would be seen when performing the target task. Diversity is maximized when the transformations applied to a given example are uniformly distributed. Given this abstract problem, we then define a tractable approximation specifically for robotic manipulation. This approximation contains 6 objective terms, weighted by parameters beta 1 through 4. The first term expresses diversity as the distance to a uniformly randomly sampled target transformation. The next 4 terms define validity and relevance for the moved object state. These terms encourage the object to remain within the workspace bounding box, penalize invalid transformation parameters, and preserve contacts and near contacts with the environment. The final term defines validity for the robot state, which preserves contacts the robot makes with the scene. We solve the optimization problem by splitting it into 2 parts. In part 1, we optimize the validity, relevance, and diversity for the moved object state. In part 2, we optimize the validity of the robot state. We evaluate this approach with 2 simulated experiments and 1 real-world experiment. First, we evaluated augmentation on a simulated bimanual rope manipulation task, shown here. The robot is holding the ends of the rope and is tasked with placing the middle of the rope within the goal regions under the hooks shown in purple. The planner uses an imperfect model of the rope dynamics, and in order to find accurate plans, it uses a learned classifier which predicts when the dynamics model is accurate. We apply data augmentation to the training data for learning this classifier. We compare against a baseline without any augmentation. Initially, both methods fail to reach the goal, but the method using our augmentation succeeds earlier and more often. If we analyze the success rates averaged over the final 10 iterations, we find that without augmentation, the success rate is 48%, but with augmentation, the success rate is 70%. Next, we evaluated augmentation on a simulated cluttered planar pushing task. The robot's end effector is shown as a pink cylinder, and the red cylinders are the objects being pushed. We apply augmentation to the training data for the dynamics model. The predictions of the trained model are shown in blue. Note how the predictions with augmentations have less drift, less penetration, and are closer to the true positions. Finally, we also evaluated our method on bimanual rope manipulation in the real world. The scene here is a mock-up of a car engine bay. The robot must move the rope and place it under the engine without snagging it to set up for lifting the engine. To track the rope, we use CDCPD2. We ran 30 iterations of learning, then froze the models for evaluation. Without augmentation, it succeeded in 7 out of 26 trials, and with augmentation, the robot successfully placed the rope under the engine in 13 out of 26 trials. In summary, we propose a novel method for data augmentation for robotic manipulation. We frame augmentation as an optimization problem and show in 3 experiments that training on augmentations improves performance on downstream tasks in the low data regime. Thank you.
Great, and our third virtual talk is bridging model-based safety and model-free reinforcement learning through system identification of low-dimensional linear models from UC Berkeley.
Hi everyone, I'm Zhongyu. I'm going to present our work on bridging model-based safety critical control and model-free reinforcement learning through system identification of low-dimensional linear models. So a year ago, we leveraged reinforcement learning to develop a working controller for a biped robot Cassie. It enables the robot to reliably track different walking velocity and walking height in experiments. And it also shows notable robustness when the robot is applied random perturbations. So such robustness actually creates interesting questions. That is, where does this robustness come from? And whether we can formally assess the stability of such an IO-based controller. So if we take this closed-loop system as a new open-loop system with commands as an input, now the input has 4 parts: the desired statutory walking velocity Vx, lateral walking velocity Vy, walking height Z, and turning rate theta. The output is the robot's actual walking velocity and walking height. So can we find an explicit model to describe such closed-loop dynamics? Although it sounds challenging, we can use traditional system identification to tackle this problem. So let's take statutory walking velocity as an example. The input contains the step input, the ramp input, and the chop signal, which is a swipe frequency sine wave. We can measure the robot's actual Vx using the MLP policy we just developed, and we can also test on different policies with different neural net structures. So by looking at the input-output pairs, we can obtain the system step response the ramp response and the frequency response. So let's take a look at how does this identification look like. The red line is the system input, the black one is the robot output, and the blue line is the predicted result using these identified models. This actually shows quite good prediction accuracy. Sensing happens in other dimensions, such as the lateral walking velocity, walking height, and turning yaw rate. We find that a linear model is good enough to describe the closed-loop dynamics in each dimension. So since we obtained the explicit model, we can apply some stability analysis on it. We find that all the zero pools are on the left-hand plane, which means that each dimension is asymptotically stable and the minimum phase. This can actually give us some insights about the reason of the robustness using this RA controller. This is only a single controller. We will validate this on different RA policies. The linearity exists among all of these policies except this one. Just using the eyeball test, you can tell the nonlinearity still exists, even when forced to fit a linear model. This is because this policy is not well trained. So the linearity can be a potential metric for the convergence of RA. Moreover, we find this cutoff frequency. If the input frequency exceeds this value, the linearity is not well preserved. So this can actually be a good guidance for the control design if we want to use this closed-loop system. This system has 4 inputs and 4 outputs. So we further show that this is decoupled under a low-frequency input. So this finding is actually a big surprise, because when we explicitly write down Cassie's 4-order dynamics, we obtain a huge file. Now, when we use an RA controller, it gives us a simple linear system. It is stable, decoupled, and the minimum phase. So this idea resembles a feedback linearization controller. So is it possible that the model-free RA learns IO linearization unconsciously? So this is a very preliminary work in these directions, and there are lots of questions we cannot answer. But this is a very interesting and open questions we want to bring up to the community. Before solving this theory question, we can actually apply what we found in the safety critical task. Now we use this IO policy, and this closed loop system becomes a new open loop system, but a linear system. And we use this linear model in a higher level safety critical controller, namely the MPC with control barrier functions, to provide safety guarantee in the task where Cassie navigates in high constraint environments. This is a joint simulation. Cassie is using the proposed method to track the global path while avoiding obstacles nearby. When the robot sees a high constraint environment, the robot will crouch down and travel underneath this space. And after the robot travels through this, it will quickly recover to a normal height and accelerates to the goal while stopping in front of the obstacles. So in conclusion, we propose a new direction to bridge the model-based optimal control and the model-free reinforcement learning by looking at the closed-loop dynamics controlled by RL policy. This can combine the advantages of both sides. We let RL to wrap up the high-order nonlinear dynamics, and it can give us a linear model. And we can use model-based method to provide safety guarantee on top of it. And it can be more practical to use because we have a linear model. Okay, thanks. I'm happy to take questions.
Yeah, now we're going to switch to a live presentation for a short talk. So Richard Wren from Carnegie Mellon University will discuss a local optimization framework for multi-objective ergodic search.
Hello, everyone. I'm Richard Wren, a PhD student at Carnegie Mellon, and very happy to share our work, a local optimization framework for multi-objective ergodic search. So we are motivated by search and rescue. Let's consider a hazardous material warehouse with leakage. We want to deploy a mobile robot to cover the red area to find the leakage sources, to cover the blue area to find survivors, and stay within the green zone to stay with communication to a base station. So with this motivation, we formulate the following multi-objective ergodic search problem. So the goal is to compute a control for a dynamic robot with some dynamics so that the resulting trajectory can simultaneously cover multiple information maps. Here, each information map is basically a probability distribution that encodes one type of information. To measure the quality of a trajectory, we use an ergodic metric. A trajectory is ergodic if the amount of time spent along this trajectory in a region is proportional to the amount of information in that region. So now, given M information map, we can compute M ergodic values, and put them together, we get an ergodic vector, where each component in this vector corresponds to an objective to be minimized. And since we're optimizing multiple objectives, in general, there does not exist a single solution that can optimize all the objectives at the same time. Therefore, we seek to find a set of Pareto optimal solutions. A solution is Pareto optimal if we cannot improve over one objective without deteriorating at least another objective. Okay, now to compute a set of Pareto optimal solution, in this work, we're going to take a weighted sum-based approach, which will appear in the next slide. Okay, to begin with, we will sample a weight vector from the weight space. Here, the weight space is the first quadrant of a sphere subject to the L1 norm, or more intuitively, it's a m-1 dimensional simplex. With the sampled weight vector, we can now take the weighted sum of the information map to get a scalarized information map. And now, with the scalarized information map, we can run existing single objective ergodic coverage algorithm to compute an ergodic trajectory. And the ergodic vector of this trajectory is basically a point in the objective space that approximates the Pareto optimal front. And we will run this iteratively. And actually, with some derivation, we realize that the ergodicity with respect to the scalarized information map is actually a convex function in the Fourier coefficient space. So this motivates us to run local optimization to expedite the computation. So first, we're going to run breadth-first sampling for the weight vectors in the weight space. And second, we're going to cache the pre-computed trajectory, the previously computed trajectories to warm start the subsequent ergodic optimization process. Okay, and then to further expedite the computation, we're going to take a deeper look into the weight sampling procedure. So the basic approach is to directly sample from the weight space. But this approach cannot take the similarity between information maps into consideration. For example, if two information maps, 1 and 3, are similar to each other, then we can simultaneously cover them well at the same time. And we don't need to sample a lot of weight vectors to capture the trade-offs. And like if two information maps are different, then probably we need a lot of weight vectors. So with this idea, we propose the following approach. We're going to first compute the pairwise ergodicity value between each pair of information map, and then use them as the edge length to construct a transformed weight space. And now we're going to sample from this transformed weight space, which can be affinely mapped to the original weight space, which can then be used to scalarize the information map. Okay, next I'm going to show a video that visualizes the entire computational process. Okay, to begin with, we sample from the transformed weight space, get a scalarized information map, run ergodic coverage that is warm-started, and eventually, we will end up with an approximated Pareto optimal front. Okay, due to time limit, I have to skip the numerical results, but the short message is that our approach can run up to 3 times faster than the baseline approaches. And our code is also available online. I'm happy to take questions in either the QA or the poster session. Thank you.
And our fifth short talk is by Christian Lanneker from ETH Zurich, Area Layouting, Design and Control of a Compliant and Actuated End-effector for Precise In-Flight Marking on Ceilings.
So, hi everybody, my name is Christian. I'm from the Autonomous Systems Lab from ETH Zurich. And in this short talk, I would like to show you some of our more recent work where we designed an end effector for aerial vehicles that can precisely mark points and lines on ceilings so that we can use it for layouting on construction sites. Layouting is basically a step before any fabrication is done. It mainly involves just marking points and lines on ceilings to indicate where to place drywalls or drill holes, for instance. So nowadays, this is still done manually, and takes up quite a bit of time, and it's repetitive, especially on big construction sites. Additionally, if you want to do this on ceilings, you have to put up scaffolding, requiring more time. So he thought this could be a nice application for drones to automate the whole process. There is a key challenge to this, though, and that is that for layouting, you have to be very precise, and this is still something that drones are not very good at nowadays. So we asked ourselves if we can actually design an end-effector for aerial vehicles that can achieve such a high precision so that we can use it for layouting, and if we can do this in a way such that the end-effector is forgiving enough so that the precision of the aerial vehicle itself doesn't have to be that high. So we then started developing the end-effector and tried to inspire ourselves how people usually write. We ended up with the design you can see here in the image. It incorporates 4 key features. The first one is compliancy, which we basically added by building the platform as a passive Gauss-Stewart platform. That's a 6 degree of freedom end effector that consists of 2 bodies, a static lower one and then a freely moving upper body. Both of them are connected by 6 spring dampers. For such a passive Stewart platform, the motion and the compliancy of this upper part actually highly depends on the geometry of the end effector itself, and we therefore try to optimize this such that the end effector counteracts disturbances by always trying to move the upper part back to its center position. If you look at the plots which show the energy required to displace this upper part, you can actually see that this is not always given. For our optimized geometry at the top, we have a nice basin of attraction at 0, 0, shown in green, surrounded by higher energy levels in blue, whereas for a Stewart platform with equally sized upper and lower body, you can see that less energy is required the further the upper part moves outwards, which would make it always fall to the side. So we then also added 3 Swedish wheels to the top so that we have multiple contact points. Each of those wheels is actually actuated by a servo motor, making this whole upper part basically an omnidirectional ground robot that you can compress against the ceiling. And then we also added an upward-facing camera looking at a checkerboard pattern so that we know where this upper part is relatively to the lower part. Here you can see the full system in action. So we have the drone basically compressing the end effector against the ceiling, and then both of them are tracking the same trajectory, which is a circular one in this case here. So as part of this work, we also then did an ablation study to evaluate the impact on precision of every design choice we made. For that, we manufactured a set of dummy components as drop-in replacements for the actual parts. And then we did different experiments with different combination of the end effector. So to actually remove the multiple contact points, we built a single point of contact rigid end effector. We also had rigid rods as a replacement for our spring dampers. And then we also used dummy servos with bearings so that we have freely turning wheels. Additionally, we then also ran our end effector in an open loop fashion. So here's a table with the results from the experiments. Let me just highlight a few of them. So in free flight, our aerial vehicle had a mean absolute error of roughly 2 centimeters, and only by adding multiple contact points and pushing against the ceiling, we actually were able to almost halve that. By then additionally controlling the motion of the end effector along the ceiling, we actually found out that the rigid end effector is almost as precise as our full compliance system, and this showed us that actually compliance is not necessarily the key factor for precise aerial manipulation, but rather the right contact with the environment. This is somewhat counterintuitive, especially when you do research with drones, because we tend to see objects as something we should normally avoid. But the study actually showed us that in order to do aerial manipulation very precisely, we should not shy away from contact, but rather try to exploit it. So to conclude, in this work, we tried to develop an end effector for aerial layouting, and we managed to achieve state-of-the-art precision. We did this by carefully choosing, evaluating, and optimizing the individual end effector components. And during the development, we actually found out that that if you exploit or exploiting the contact with the environment is actually one of the key factors to improve precision during aerial manipulation. Yeah, so with that, I would like to thank you all for listening, and I hope to see you at the poster session later so that we can go a little bit more into detail of this work.
So now is the time and our opportunity to ask questions to the speakers. And we are going to set it up also so that we have the online presenters joining us. So time for questions.
Hi, I have a question about the reduced order linear models paper. So my question is, How did you decide the dimension of your lower dimensional linear model? Because I would imagine that, in theory, as you increase that dimension, you would get a better and better linear fit. Oh, sorry, I think you're muted.
Yeah, just one moment. You're muted and we cannot hear you. Let's try again. Can we hear you?
Can you hear me now?
Yes.
Oh, nice. Okay, let me go with the question. Thanks for the question, very good questions. So we actually have details in the paper, but to be short, is that we first go with a very, assuming it's a high dimensional, systems, like 10 order stuff. And then we do linear fitting, and we find the systems, and then we do model reductions by looking at Hancock singular values. Because we want to balance the models, don't want to, if we higher order, because if we increase orders, the fit will be good, but it won't be that linear increase will convert to some values. So we want to cut off the orders. So basically we pick up the most, we just look at Hancock singular values to pick up the optimal dimensions of the systems.
Okay, thank you.
Okay, we have another question.
Yeah, I have a question for the end-effector paper. Are you localizing the area vehicle with a Vicon system, or are you using other methods?
Yeah, so yeah, actually, all of the experiments we did, so we had ground truth for the aerial vehicle, which we used to move it, and then the end effector actually, it was very hard to get the position because it was occluded by from the top, from the bottom from the aerial vehicle, and from the top from the ceiling. So we actually then used the ground truth from the aerial vehicle, and then the upward-facing camera, which were tracking this upper part. And then we did also experiments to see how actually accurate the camera tracking by itself is, which was below a millimeter actually.
All right, thank you. Do you think the maybe you can use the odometry of the wheels to better localize?
Of the what? Sorry?
Of the wheels to better localize the vehicle?
Yeah, so yeah, you maybe could. I don't know if that works since they're omni. Yeah, maybe you could actually. Yeah. So I don't know if the servos which we use, they're quite lightweight, and I don't know if they're accurate enough. Usually, you don't get such a good feedback from them. But yeah, so I mean, in general, it's something we want to look at now, how to actually get rid of the Vicon system or the motion capture system.
Thank you.
One more question from the audience?
Yeah, I have a question about the multi-objective ergodic search. So first we formalize the problem into a multi-objective problem, and then we scalarize it using adaptive weighting mechanism. And it seems like the weights are important. So how do we set these weights?
Okay, so the question is how we set the weight. So normally we will begin with a user-defined initial guess or just some random initial guess. And then we will run breadth first sampling in the transformed weight space. So basically we will cover the entire weight space so that we can get different options, different trade-offs in the entire Pareto optimal front.
So it's application dependent, the weight.
Okay, that's an excellent question. So in real-world application, so twofold. First, we believe with the Pareto optimal front, then the decision maker can actually have a better understanding of the task and pick the one that match his preference. And secondly, far away in the future, we think it's a very promising direction to leverage machine learning to learn, to mimic those decision makers' preference, so that those highly nonlinear preference can be captured and automatically select the best solution from the Pareto optimal set.
Thank you.
Well, perhaps I'll ask one last question to one of our online presenters on data augmentation for manipulation. So Peter, you had multiple things that you augmented over. Do you have an ablation of which aspect matters the most in order to improve performance?
So by that, do you mean the different terms in the objective, or?
Yeah, and yeah, like you had the robot and you know, the environment.
I see. So we don't have ablations in the paper over whether to augment the environment or not, whether to augment the robot or not. We only test augmenting both the robot state and the moved object state. The intuition there being that for manipulation, typically you care about what's moving. So if it's stationary, augmenting over the stationary thing may not improve either predictions or recognition or whatever the actual downstream task is. But if that was true for your task, then I suspect that you could keep a lot of the objective terms and just apply them to the stationary objects, or if for some reason you really didn't want to augment the robot state, you could basically just not do that. But it would probably be task dependent.
Great, thank you. Let's thank all of the speakers. Now we're going to have a long talk by Matthew Cavorsi from Harvard University on multi-robot adversarial resilience using control barrier functions.
Is there a reason nothing's coming up? Nope. Okay, hello everybody. My name is Matthew Cavorsi and I'll be presenting our paper for RSS. In this paper, we use control barrier functions to satisfy multiple different objectives simultaneously. One of those objectives is resilience, which models a physical constraint on the team formation. And we notice that when the team formation is restricted in this way, it becomes more difficult to navigate through cluttered environments, and so we analyze some of the different scenarios where this may occur. Robot teams satisfying multiple objectives is a common but important problem. Control barrier functions are formulated as an optimization problem that takes these different objectives as constraints and looks to find a control vector that satisfies all of them. As an example, I will put our methods into the context of a flocking problem, where different objectives are to navigate across an environment, agree on a heading direction to move, while also avoiding collisions and maintaining a resilient formation. Now, as I mentioned, the addition of a resilience constraint, which attempts to fortify the team's communication network to protect it from vulnerabilities, will be the main focus of this work, as its inclusion adds new interesting challenges for control barrier functions. We assume that robots can communicate with each other if they're within a certain distance r from each other, allowing them to form a network such as the one shown here. However, malicious robots within the network may be able to compromise the performance of the team by tampering with the information they relay to others. We'll assume that malicious robots can only perform attacks on information, but still follow the other objectives of the team, so as to not be easily detected. As a motivating example, we show what a successful attack can look like. The arrows below the robots here correspond to the heading direction that they share with the rest of the team. As the robots start to move, they begin a linear consensus protocol, as shown by the plot on the left, and eventually converge on a heading value. As the network becomes sparser, the adversary can perform an attack by broadcasting different heading directions to different robots. This causes the team to physically split apart and the flocking to visibly fail. As I mentioned, this is due to the fact that the network becomes too sparse such that all the information has to flow through the adversary. This motivates us to build networks that are resilient, meaning that there are multiple paths of communication between any two robots. Previous works have shown that there are certain topologies that guarantee this resilience to adversaries, and a common theme among all of them is that resilience is related to a network that's well connected. Since we model the connectivity between robots as a function of distance, we can actually impose resilience as a physical constraint by enforcing that robots stay close enough together to form a well-connected network. Control barrier functions have been widely used to take multiple different constraints and satisfy all of them simultaneously. By formulating resilience as a physical constraint, we can now actually include it under the same framework with the other physical constraints such as collision avoidance. However, this introduces new challenges, as the resilience constraint can sometimes be at odds with the other constraints. To explain more about this, I will start by giving more detail about the control barrier function framework. The basic idea behind control barrier functions are that the robots look to minimize the difference between their input and desired input UDES, which usually encodes the main navigational objective of the robot team. While minimizing the difference between their input and the desired input, they also look to satisfy several constraints. In our paper, we consider resilience constraint as well as safety constraints. For the resilience constraint, we look at the algebraic connectivity of the network, which quantifies how well connected the network is. Previous works have shown that if the algebraic connectivity is at least 4f, where f is the number of adversaries in the network, then resilient consensus can be guaranteed. And so we set this as our resilience constraint. To deal with collision and obstacle avoidance, we set safe distances d-min-c and d-min-o and require that the robots respect these distances. Now, ideally, a CBF can handle all of these constraints simultaneously, but sometimes it can be difficult for the robots to maintain a close-knit, well-connected formation while navigating through certain environments. In these cases, the environment forces a trade-off between resilience and navigation. In this paper, we look to characterize when this happens and determine how to handle it. How we deal with the trade-off between resilience and navigation is often problem-dependent. Ideally, we want to treat resilience as a hard constraint, where it could be guaranteed to be satisfied. A key challenge here is to characterize some of the different scenarios where resilience may be compromised. For example, we look at a scenario where robots must navigate around a large obstacle, and we looked. Sorry. For example, we look at a scenario where robots must navigate around a large obstacle, and we look to find the largest such obstacle that robots can split around it without losing resilience. However, there may be times where the environment makes it impossible to navigate in a resilient formation. For example, if the robots were to encounter a narrow corridor, they would be unlikely to fit through it without the formation breaking down. In these scenarios, we derive an alternative control barrier function, along with some critical control parameters to allow the robots to break down resilience and treat resilience as a soft constraint, which means that resilience will be compromised if necessary to allow for navigation to continue. Finally, I will conclude my talk by showing some example experiments where the robots encounter some of these different scenarios to show how well the theory that we developed aligns with actual real implementation. But first, I will talk in more detail about resilience as a hard constraint. As the robots navigate around a large obstacle, they may split around the obstacle to opposite sides. Since we model resilience as a function of distance, when the robots split around an obstacle, the resilience may be compromised. As shown by the plot of algebraic connectivity on the right here, approaching the resilience threshold of 4f plus epsilon. In this case, the resilience will try to pull the robots back together, while the obstacle tries to push them apart, and the desired input tries to push them forward, causing the team to get stuck. This motivates us to characterize a critical size such that the robots can navigate around the obstacle without losing resilience. To do this, we look at the distance that the robots must separate from each other if they were to navigate around the obstacle to opposite sides. Then we consider all possible formations where some number of robots I and n minus I make up the two groups, and we find the lowest algebraic connectivity of all these different formations. Then we look at the distance that's sufficient for this worst case formation to still maintain resilience, and we set this as our critical obstacle size, DO max. The DO max that we derive is shown here, and we show it to be a function of the resilience threshold, the number of robots, and the communication radius of the robots. This slide uses simulations to verify the theory from the previous slide. In the top plots, what we do is we set the obstacle size to DO max, and we show that the robots, which are shown by the little blue circles, are able to split around the obstacle while maintaining resilience. However, if we increase the obstacle size just a little bit, like in the bottom plot, the robots no longer can maintain resilience while splitting around the obstacle, and so they get stuck behind it, as the theory predicts. Next, I will talk about resilience as a soft constraint. Take, for example, the narrow corridor scenario. In this scenario, as the robots try to navigate through a narrow corridor, the formation starts to break down, and resilience may be compromised, as again shown by the algebraic connectivity plot on the right, approaching the resilience threshold of 4f plus epsilon. In this case, the resilience input will try to drive the robots back out of the corridor, while the desired input tries to push them further through it. Because of this, it may be impossible for the robot team to make it through the corridor while maintaining a resilient formation. This motivates us to redesign our CBF to take resilience as a soft constraint. We call this the nested CBF approach. The intuition here is there's an inner CBF that minimizes the difference between the robot's input and a desired input while satisfying the resilience constraint. Then the solution to this inner CBF is fed to an outer CBF, which minimizes the difference between this new input and a final input while satisfying the safety constraints. In this way, the safety constraints are guaranteed to be satisfied, and the resilience constraint will be satisfied as much as possible. Now, we notice that the robots don't always compromise enough resilience to navigate through any corridor, and so we also include a gain term denoted by gamma in the inner CBF. This motivates us to determine a maximum gain such that robots will always compromise resilience in favor of navigation. To do this, we again look at the worst case formation that can arise, which in this case is when robots form a path graph. We find the algebraic connectivity of this path graph formation and the resultant control vector that will look to try to improve the resilience. We compare this to the desired input pushing the robots the other way and choose a gain such that the desired input is greater than the resilience input. The maximum gain value that we derive is shown here, and we show it to be directly proportional to the resilience threshold and inversely proportional to the desired input. Shown here is a simulation that shows the existence of a gamma critical. Now, gamma critical is an empirical value for a particular narrow corridor that shows essentially if gamma is greater than gamma critical, the robots will be able to compromise resilience and move through the corridor. Whereas if gamma is less than gamma critical, then the robots get stuck in the corridor. We show that our gamma max that we derived is greater than the gamma critical, and so the robots are able to navigate through the corridor. Finally, I would like to show some experiments where the robots encounter some of these different scenarios. This first experiment shows an obstacle size that's small enough such that the robots can split around it without losing resilience. In this experiment, as shown by the plot on the right of algebraic connectivity, the algebraic connectivity always remains above the 4f plus epsilon resilience threshold, and so the robots are able to navigate around it safely. In this scenario, the robots use the nested CBF approach to navigate through the narrow corridor. As shown again by the plot on the right, the algebraic connectivity now actually drops below the threshold as the robots compromise resilience to make it through the corridor, and then it moves back above it as they reconvene on the other side and regain resilience. Finally, I'd like to circle back to the resilient flocking example from the beginning. In this example, the arrows below the robots correspond to the heading directions again, and they all choose a heading direction and must share and agree on that value. The heading consensus will be plotted on the left-hand side, and the algebraic connectivity will be plotted on the right. The adversary, highlighted in red here, will try to choose a heading direction to try to drive the robots towards the right side wall. Now you'll see that since the algebraic connectivity is greater than the threshold, as the robots move across the test bed, they are able to maintain a resilient consensus despite the attack and travel across the test bed as a unit. Thank you so much for listening, and I'll be happy to take any questions now.
So we have a few minutes for questions. Well, let me start. So I think you mentioned in the hard constraints that you are modeling resilience as a function of distance, right? But communication is also dependent from many other factors. You know, there could be multipath effects, it could be a body of water that affects that. Have you thought of alternative ways that you can have, more, taking these factors into account, or perhaps monitoring the quality of communication that's affected by them?
Yeah, so that's a good question. So in this paper, we model resilience, we model connectivity as a function of distance because with the distance, we can quickly optimize the communication by telling robots to move closer to each other. If we were to consider other things such as maybe obstacles that occlude the communication from happening, then we would have to kind of formulate the connectivity as a connected graph, or a directed graph, which makes it a little more difficult, but could be an area for future work, as well as like packet drops, something like that. We can model the communication as something that's a probability, but then the whole notion of resilience is a little bit more difficult because we have to basically say, like, in expectation, the network is well connected or something along those lines.
Hi, great talk. I just have a quick question regarding the number of adversarials in the network. Have you guys studied sort of like a ratio of like the maximum ratio of the number of adversarials possible in the network to keep resilience? Thank you.
Yeah, good question. So the algebraic connectivity is limited to n, which is the number of robots. And so since we require the algebraic connectivity remains at least 4f plus epsilon, then naturally we can only have up to a fourth of the network be adversaries. Most of the examples we showed here only include one adversary, but that was only a limit of hardware because you need more robots to have a greater resilience to more adversaries. So generally the only restriction is that only a fourth of the network can be adversaries, and beyond that, f can be whatever we choose it to be.
Thank you.
Other questions?
Hi, great talk. So I have maybe a little bit of a forward-looking question of what would change if the adversary was allowed to take arbitrary actions in addition to passing arbitrary information? And could the CBF be used to detect which robots are acting adversarially?
Yeah, so actually it becomes a lot easier to detect when adversaries are performing actions in this way by using the CBF because the CBF computes the control input for all of the robots. So each robot has an expectation of what the other robots around them are going to do and can quickly observe that one of the robots isn't following what it should be doing. So in that way, that's why I said it would be easy to detect an adversary if it were to behave differently. In the sense of if it were trying to behave differently to try to affect the team's performance, there have been papers that have looked at some of these kind of problems. And the idea here is to kind of just assume that the robots are going to do the worst possible thing they can do and choose your strategy around maintaining resilience while that's occurring.
All right, thank you.
Great. Let's thank Matthew.
Thank you.
And the last talk for this session is titled Autonomously Untangling Long Cables from UC Berkeley.
Good morning, everyone. I'm Justin, and I'm here with Vainavi and Kaushik from the Autolab at UC Berkeley, and we're going to present our work on autonomously untangling long cables. So if you're like me and you pack your luggage like this, maybe when you arrived at RSS, you're greeted with a view of a tangled cable, and you had to fumble with it to unpack the clothes beneath it. And although humans do this almost automatically, this is actually a really interesting problem for roboticists to study. Because it's a very challenging state estimation problem, there are very complex dynamics which make it difficult to simulate, and the cable often extends far outside the reach of the workspace of the robot. In addition, there are many practical benefits of household manipulation. There's lots of great related work on 1D deformable object manipulation, including exploring dynamic actions for efficient manipulation, or leveraging approximate models during planning, or learning visual dynamics models from experience. In addition, there's lots of work on untangling, for example, using key points to predict grasp points, or using analytical state estimation to produce viable actions. The focus of this work is really pushing the limits of how long the cables we can handle are. Asking the question of, like, can we use cables that are realistic in household settings up to 3 meters in length? Using these types of cables have a lot of unique perception challenges, where these two cables are the exact same topological configuration, but visually, the right side is almost imperceptible and the left is trivial to see. In addition, even minor changes in the cable state can drastically change the visibility. For example, this knot on the left is completely obscured by the pile of slack on the right if it's moved by a small amount. There's also a host of challenging manipulation problems. There's a high degree of precision required for this task, where the difference between a successful grasp and a failed grasp can be on the order of millimeters. In addition, the workspace of the robot is extremely limited compared to the size of the object, and because of the stiffness of the cable, it tends to form these tricky loops which are difficult to remove and can snare the grasp. So the goal of our system is to produce a system which can go from a cable state on the left, which is tangled with knots, and unknot it into a nice state on the right. So for some intuition on what some initial configurations looks like, here are some visualizations. To make this a little bit more formal, our goal here is cables with at most 2 figure-8 or overhand knots, and our goal is to remove all knots and then verify that all the knots have been removed. If you want some more formalism, you can think of this as defining an indicator function over the length of the cable, and our goal is to make this indicator 0 everywhere. So now I'm going to briefly discuss the system design of this physical system design. We use a Yumi robot, which is a bimanual collaborative robot with 7 DOF arms and parallel jaw grippers. To each of these grippers, we attach custom gripper designs with little teeth at the bottom, which we call cage pinch jaws. And the cool thing about these cage pinch jaws is that they allow dual grasp modes. On the left, we have caging, which constrains the cable within the jaws while allowing it to slide laterally along the cable. While on the right, if we just pinch harder, we can constrain the cable completely within the fingers. We use an overhead depth camera, which has grayscale and very accurate depth at a low frame rate, an example point cloud of which is on the right. And here's a visualization of our foam padded surface for safety of the robot, and as well as the observable region marked. And here we visualize the reachability of the left and the right arms respectively. Notably, you can see that the size of the cable is large enough that even in compact configurations, it can reach outside the workspace. And now we're going to present the software system to handle this task, which we call sliding and grasping for tangle manipulation, or more affectionately, SGTM.
Okay, so I'll begin by introducing the manipulation primitives used by SGTM. First, we have dynamic shaking. This is a primitive used to disambiguate the cable state or reconfigure it into another configuration in the event that it's in a difficult position to perform other motion primitives. Next, we have tracing, which we use as a verification primitive. Once our perception system determines that there are no knots remaining, we want to physically verify this by tracing through the cable using alternating pinch and cage grasps. In the event a knot is encountered, we perform a knot isolation move that's shown in this video, which places the cable down such that the knot is unoccluded and ready to be untangled. Dual cage separation is used for loosening or untangling knots, and in this case, both the jaws are caging the cable. A Reidemeister move, the name coined by the knot theorist Kurt Reidemeister, grasps the endpoints and pulls them to opposite ends of the workspace. This preserves the topology, but makes knot visibility easier. Now introduce the perception system, which enables the manipulation primitives I just discussed. So we train a fully convolutional neural network in a supervised manner to output a heat map over the location of the endpoints of the cable. This is used in Reidemeister moves as well as for dynamic shaking. We use the faster RCNN architecture to learn bounding boxes for knots. This is used as the first step in identifying grasp points for dual cage separation and for also verifying that no knots remain before we perform tracing. We use two fully connected networks with a ResNet34 backbone for grasp point selection for the dual cage separation primitive. The first network takes in the image of the knot crop produced by the previous network that I just discussed and predicts the first grasp point. The second network takes that image along with that first grasp point to predict the second grasp point for the dual cage separation action. And the grasp points predicted by this previous network are passed into our planner, which does a joint search over grasp poses to find a pair that is collision-free and reachable. When tracing, we use an analytic method that observes the 3D point cloud near the grippers and analyze whether we've reached a knot. So if the crop of the point cloud directly in front of the grippers has greater than n points, or we see more than one connected component, that means that we've encountered a knot and we terminate tracing and move on to knot isolation. We use the same FCN for endpoint detection used on the full cable image to also determine if we've encountered an endpoint during tracing, which is our indicator that we've fully untangled the cable. So putting together now all the manipulation primitives and the perception system, we present our SGTM algorithm. So first, we check the number of endpoints, and based on that, we either determine to shake, perform a Reidemeister move, or do nothing at all. And next, we perform knot detection to disambiguate the state. And if our perception system doesn't see any knots, we physically confirm this to make sure that we can terminate. And if we are to encounter a knot while tracing, we return to the knot detection step. If a knot is detected, we determine the grasp points and perform dual cage separation to loosen the knot, and then we loop back to our first step.
We now present the experiments that we use to validate the performance of the manipulation primitives, our perception pipeline, and the SGTM algorithm. So we use two primary tiers of cable configurations to validate the algorithm. So the first tier consists of single overhand or figure-8 knots, tier 1, and tier 2 consists of 2 overhand knots, 2 figure-8 knots, or a combination of the two. And we run 12 rollouts to validate our algorithm. Now moving on to some example results. In the first video, the robot detects an overhand knot, and it uses the grasp point networks to predict points for the dual cage separation action. It then runs a shaking action, and then it moves on to tracing to verify that the cable is fully untangled. And once it reaches the endpoint of the cable, it terminates successfully. In the second video, the robot loses its grip on the figure-8 knot as it pulls it apart. But then it shakes, performs a Reidemeister move, and then does one more shaking action. And the figure-8 knot has been sufficiently loosened such that these dynamic motions fully untangle the cable. And then once again, it traces to verify that the cable is fully untangled. The table here shows our results. For tier 1, we have 8 out of 12 rollouts ending in untangling successes, excluding the verification step. And for tier 2, we have 6 out of 12 rollouts ending in untangling successes. As you can see, tier 2 is significantly more difficult, especially because of the longer time it takes to untangle both of the knots in the cable. Now we present some of our dirty laundry, or failure cases that SGTM encounters.
In the top left video, the cable leaves the workspace entirely due to failed slack management when we're performing a shaking action. On the top right, SGTM misses a grasp while trying to untangle the cable. But while this is not fatal, it often creates complications due to the cable moving off to one side of the workspace. On the bottom left, the cable actually becomes jammed due to the adapters at the endpoints when SGTM attempts to perform a cage separation action to untangle a knot. And finally, on the bottom right, we can see that the robot actually takes a long time. This is a sped up video, and it often takes a long time to slide along the cable. And we observe that in experiments, there are often false positive knot detections that cause the algorithm to have a low verification success rate. We've also been working on a second version of the SGTM algorithm to address the failure modes and improve upon the current iteration of the algorithm. Currently, we focus on one type of USB cable, but we wish to generalize to more types of cables in the next iteration of our work. And we also plan to use SIM and larger quantities of data to improve the generalization to new types of knot. And finally, our contributions include a problem formulation for the untangling long cables problem, a dual mode gripper design that critically allows for sliding and pinching actions. And we also leverage the unique capabilities of these grippers and combine them with a perception pipeline into the SGTM algorithm and present a unified system, an integrated system that is modular and capable of untangling long cables up to 3 meters in length. Thank you.
And we have again time for questions.
Hi, really excellent talk. I have 2 questions. My first is, if I recall, you said at the beginning something about that you assume at most 2 overhead knots. Is that, what's the reason for that? And my second question is, I missed, how do you decide which of the primitives to execute?
Yeah, thanks for the question. So the first assumption is mostly just for defining our experiment tiers. And so there's a little bit of practicality involved there in choosing what to experiment with. In terms of the second question, I think Vainavi could.
Yeah, so for determining which primitive to use, we use our perception system. So for example, we check the number of endpoints to see if like a Reitermeister move is necessary versus if a shaking action is necessary. And similarly, we also check like, do we see any knots in the scene with the perception system? And if we do, we'll use the dual cage separation action to undo that knot, or else we'll trace. So essentially, our perception system determines, or helps us determine, what's the optimal action.
Great, thanks.
Can you talk a little bit more about your inspiration for these manipulation primitives? You referenced, I think, topological work. It comes mostly from this literature to putting together this system, or perhaps how you've observed people solving these problems?
Thanks. So I think the inspiration for some of the primitives themselves are based on ourselves just playing with cables and noticing that when humans handle long objects, a lot of times we're not statically grasping a cable, but instead we have to slide along the cable. And so we wanted to have some simple mechanical design that allows this without any sensing or closed-loop control. And so we settled on a design like the grippers that we have, which allow us to do these primitives similar in spirit to what humans do.
Yeah, there we go. Yeah, very interesting talk, thank you. I was wondering if you noticed any difference in the success rates depending on where the knot was on the string. Like, was it better at untying knots in the middle compared to the end? Because it looked like it would be harder to grasp if it was right at the end.
Yeah, so we actually, when we ran the experiments, we systematically tried different knot configurations, as in where the knots were located. We didn't notice any significant differences in success rates, but it is significant that a knot is near an endpoint, for example, because you won't have to slide as far along the cable to fully undo the knot. So, for example, in the video where you saw the cable actually coming out of one of the grippers as it tried to untangle, in that case, if that cable were actually closer to the endpoint, it might have already untangled that knot by the time it fell out. So in general, you might expect that knots closer to endpoints would have a slightly higher success rate, but we didn't observe significant statistically, or very statistically significant difference. So.
Okay, cool, thank you.
I appreciated your failure cases. Did you ever generate a knot during the process of trying to a knot?
Yeah, so actually that was one of our failure modes, because if you even just with primitives that place the cable in certain places and then pick it up at other locations, you can actually tie knots. And we did experience that. And there's obviously a lot of work to be done to mitigate this failure case with improved slack management, because if you manage slack very carefully, then this wouldn't happen. But because of the difficulty and complexity of the problem, it does end up happening. So there's definitely a lot of further work to be done there. Yeah.
Great. Let's thank the speakers.
All right, next up is a coffee break. So please join us back here for more short talks and the keynote at 10:30. From the coffee break, we'll need to flag some people down. I know you all love your coffee. We've got great talks coming. Okay. Started, and then people will hopefully start trickling back in. So the chair of the next session is Russ Tedrake.
Okay, hi everybody. Very excited for the next set of talks. We got a lot of, maybe if there's a theme to the session, it's a bit on tools, and I'm very much a fan of tools myself. We're going to get started right away here. We'll start with the first talk about Proxima from Daniel Rakita.
Great, thank you. So a collision proximity query in robotics is a scalar function denoted as C here that characterizes how close a robot is to either a self-collision or collision with obstacles in its environment. A common way to frame this function is to take the sign distance between all pairs of rigid shapes, map these distances through some loss function, then sum up all these values to get a single collision proximity output value. Many areas of robotics, like those listed here, rely on this kind of function, as well as its gradient, to generate motions that avoid or adapt to potential collisions. So a big question at this point is, how should this collision proximity function be computed? So culling approaches, such as bounding volume hierarchies, try to eliminate many unnecessary distance checks at runtime. These approaches still provide an exact result, but they have no efficiency guarantees, and in the worst case, may still need to perform distance checks between all pairs of shapes. Conversely, recent approaches have used supervised learning in order to train models that approximate proximity functions. These approaches have guaranteed efficiency as they just involve a single feed-forward pass through the model. However, the output value has no accuracy guarantees, and errors may be difficult to characterize or bound. In our work, we present a new approach for computing a collision proximity function for robot manipulators that formalizes a trade-off between efficiency and accuracy and provides an algorithm that gives control over it. Our algorithm, called Proxima, works in one of two ways. First, given a time budget as input, the algorithm returns an as accurate as possible proximity approximation value in this time. Or second, given an accuracy budget, the algorithm returns an as fast as possible proximity approximation value that is within the given accuracy bound. Further, both the time-budgeted and accuracy-budgeted versions of our algorithm are able to guarantee that the output value is a cautious approximation that is bounded from below by the ground truth value, meaning the safety of the robot or surrounding obstacles can be ensured in downstream applications. So how do we achieve all this? At a high level, our algorithm involves the following steps. First, the algorithm computes lower bounds on signed distance for all pairs of shapes. Our work proposes a novel way for computing these bounds in just a few nanoseconds each, making this step efficient even for scenes with hundreds of shapes. Next, the algorithm prunes any pairs of shapes with lower distance bounds that are too large to be included in the final output. The algorithm then computes guaranteed upper bounds on signed distance for the remaining pairs of shapes. Again, our work proposes a novel way for computing these upper bounds in just tens of nanoseconds each. These upper and lower bounds are interpolated to form an approximate distance for each remaining shape pair, and if the loss function used is monotonically non-increasing, we can also bound the maximum possible error that could come from each pair in the output sum. The algorithm sorts the pairs of shapes based on their maximum possible error from greatest to least, sums up an initial approximation value in maximum total error, then processes ground truth signed distance checks between pairs of shapes in sorted order until either time is up in the case of a time budget, or until the total possible error is below some given epsilon in the case of an accuracy budget. Because ground truth distance checks are processed in order of maximum possible loss function error, we argue that our algorithm makes great use of its computational resources within its allotted budget. So briefly looking at some results, we see that Proxima here with an accuracy budget of 0.5 is much more efficient as it requires many fewer expensive signed distance checks, all while having a cautious, comprehensible bounded error. Our paper shows that Proxima and its gradient can be incorporated into robot motion generation tools, such as this optimization-based inverse kinematic solver seen here. We show that Proxima affords highly interactive, collision-free motions even on this 66-dimensional humanoid robot. And here is another example where the humanoid is avoiding collisions with a dynamic environment obstacle, again using Proxima to afford a tight, interactive computation loop. So we provide open source code that implements Proxima, so feel free to check that out. Thanks so much, and I'll take any questions after this session. Thanks.
Beautifully presented. Thank you very much. Our next speaker is Antoine Bambade from INRIA.
Hi, my name is Antoine Bambade. I'm a PhD student at INRIA and working at the interface between robotics and optimization. And I will present you, I'll present you ProxQP, which is a convex quadratic programming solver, which consists in minimizing convex quadratic costs under linear constraints. And ConvexQP is a core modeling tool of robotics because it is involved in contact modeling for dynamics, inverse kinematics, and dynamics. And the problem is that today, QP solvers have trouble to be at the same time accurate, fast, and numerically robust. For example, IDMM algorithm has trouble to reach in a reasonable time solutions at a low accuracy. Interrupt methods cannot be easily warm started, which restrict them from control applications, and active set methods can be fast, but also they depend, they need strong assumptions to work well. Hopefully, another family of methods based on the augmented Lagrangian can match a priori all these specifications, and that's what has motivated our choice for designing a solver based on this approach. So the augmented Lagrangian is defined as the sum of the cost function and this difference of two squared norm term in blue. This merit function introduced by Esnes and Powell is the basis of the method of multiplier below, which we'll see below, and which can be used for solving the original QP problem. And the first term in blue constitutes a smooth penalization of the constraint with respect to a shift defined by the multiplier z. And the problem of this method is that xk is not guaranteed converging, which can be troublesome for some robotic application like in motion planning. Hopefully, Tyrrell Rockefeller has shown that by adding this proximal term in blue to the augmented Lagrangian, if one iterates the proximal method of multiplier below, then both xk and zk will converge as soon as there is a solution, which is really appealing, and the function phi is what he has called the proximal augmented Lagrangian. We have introduced one supplementary term to phi, so the blue one, which makes the function m depending both of x and z. And we have introduced this merit function because the linear systems involved for minimizing it are better conditioned than the one involved with the phi function. So our scheme is more robust and accurate. And minimizing this merit function enables solving also the original QP problem with the scheme below. But we are not limited to this algorithm because we have another contribution for accelerating it. So this minimization step is only the first step of ProxQP. So here you can see ProxQP algorithm. So once we have found candidates for minimizing the m function, then the if-else condition in red is here for accelerating the scheme. It constitutes what is called the bound-constrained Lagrangian algorithm introduced by Twin and al. For calibrating the mu parameter, which is the one calibrating the speed of the algorithm. So mixing the new merit function plus BCL is the second contribution of the algorithm. So the third contribution is that we have implemented ProxQP in C++ using Eigen library, and we have also re-implemented 3 specialized backends for dense, sparse, and very sparse and large matrices, which is, to the best of my knowledge, unique for a QP solver. And the solver will be open source with a BSD license, and the API will be close to the one of OSQP. So now we'll present you some benchmarks. So I've benchmarked ProxQP against OSQP on inverse kinematics and dynamic tasks. And we have seen that ProxQP is about 6 to 9 times quicker than OSQP. We have also made benchmark on standard QP from the optimization community, and I've seen that ProxQP is also always the quickest. For example, for a QP with 1,000 variable, ProxQP is about 10 times quicker than OSQP. Yeah. And so on this slide, you can see performance profiles on a subset of very hard QP from the optimization community, so Mars Medzaro's repository. And so on the ordinate, you can see a performance ratio, a ratio of problem solver with respect to a performance ratio, measuring how slow a solver is with respect to the best solver solving all these percentage of problems. So the higher, the better. And you can see that ProxQP is always above all other solvers. So I've introduced you ProxQP, which is a fast, robust, accurate open source solver based on a new augmented Lagrangian algorithm, combining a new merit function and a globalization strategy for speeding it up. And I'll be happy to discuss with you more on it on the poster session, the sixth poster, and thank you very much for your attention.
Okay, excellent. Our next talk is from Skydio. Heike from Skydio is going to present SimForce.
Yeah, hello. So we present SimForce, an open source library for fast symbolic computation, code generation, and nonlinear optimization for robotics. This is work from the Skydio autonomy team. So SimForce is made for writing algorithmic code for tasks like SLAM, MPC, calibration, bundle adjustment, and controls. Compared to alternatives, it results in faster runtime performance, faster development cycles, and fewer lines of code to maintain. SimForce powers tens of thousands of autonomous robots at Skydio. So the primary workflow consists of 3 stages: symbolic math, code generation, and optimization. First, the problem is modeled in Python with the SymPy API extended to include geometry types, camera models, and Lie group calculus. Second, symbolic functions are introspected to auto-generate highly performant runtime functions. And third, generated functions are used in our tangent space optimizer. So let's walk through this simple example where a robot moving through a 2D plane has noisy measurements for a distance sensor and bearing to known landmarks in the scene. To begin, we model with a residual function for each of the sensor measurements. These functions output symbolic expressions which can be explored, analyzed, and manipulated for rapid development. The top function computes the residual for distance traveled, and the bottom for bearing angle to the landmark. So we pass each function to the code generation class and tell it what language to generate, in this case C++. We get a generated C++ function with an equivalent API to the symbolic function. It has no branches, memory allocation, and its only dependency is the eigenmatrix library. By changing one argument, we can generate an equivalent Python runtime function that depends only on NumPy. SimForce aims to support many target languages. With one more function call, we can automatically generate tangent space Jacobians, or Gauss-Newton linearization with respect to any of the function arguments. And finally, we can construct a factor graph from the generated residual functions and derivatives at each time step, create initial values, and invoke the optimizer from Python. And the same optimizer API is supported in C++ once the user is ready for production use. So here we see the problem being optimized. This overall workflow scales well to a wide range of complex problems up to hundreds of thousands of operations. And SimForce's code generator is broadly useful even without the optimizer. So as we saw, SimForce does not require any handwritten derivatives, which tend to be among the most error-prone tasks in robotics. SimForce introduces a novel method to automatically compute tangent space Jacobians of functions that operate on Lie groups, like rotations and poses. All a user needs to do is create a symbolic expression and call the Jacobian function as shown here. SimForce introduces a technique to avoid singularity points without introducing branching using an infinitesimal variable epsilon. For example, this strategy can create a branchless expression for sine of x over x without a singularity at the origin. Handling this correctly is key for robust behavior. And the largest advantage of SimForce is speed. SimForce generates highly performant code by operating on the fine-grained structure of a computational task to avoid unnecessary work. SimForce functions are flattened into a chain of instructions that share all common subexpressions, leverage sparsity, and avoid branching. So let's take as an example computing the product of x and y, the matrices shown here. Similar tasks are common when dealing with 3D transformations or applying the chain rule during automatic differentiation. So naively computing x, y, and their dense product requires 417 operations. SimForce's generated expression, as shown here, requires only 34 operations. SimForce generates output entries directly with no overhead because it knows the exact sparsity patterns from the symbolic code. In contrast, using sparse matrix multiplication at runtime is slow because it requires dynamic memory allocation. In addition, SimForce is much more powerful at common subexpression elimination than a compiler because it can flatten and share terms across arbitrary symbolic function boundaries. So we profile this task for a wide range of matrix sizes and sparsity patterns from the sweet sparse collection. SimForce outperforms the best of eigen in C++ sparse or dense by 4.8x on an Intel CPU and 7.1x on an NVIDIA Tegra CPU. Next, we measure the linearization time of a robot localization problem with 5 poses and 20 landmarks, implemented idiomatically in SimForce, GTSAM series, and JAX. We generate 2 SimForce formulations, a fixed size problem that is faster and a dynamic size problem that is more flexible. SimForce fixed outperforms the best non-SimForce result GTSAM by about 5x on both Intel and Tegra platforms. SimForce dynamic outperforms by about 2x. So please visit our repository or pip install to get started with SimForce. Thank you, and we hope our contribution can benefit many of you.
Okay, very nice. Our next speaker is Yash from NVIDIA, who's going to tell us about Factory. No? Oh, sorry, David Snyder. My bad. My bad. David Snyder from Princeton is going to talk to us.
Hello, everyone. My name is, I guess I'll jump right in. So our motivation for our work on failure detection is that many systems, including simple ones, can have unexpected failure modes. Some of these may be innocuous, but on the other hand, we see that on the right, an autonomous vehicle may mistake something like the moon for a yellow light. And more generally, we know that learned systems that use black box policies, including possibly humans, can fail catastrophically in novel environments. And so our goal is to provably predict failures in these environments. So we use for our problem formulation the motivating example of drone navigation. We assume we have access to an environment E. We do not know parameterization of E, of the distribution that E is drawn from. Instead, we access it through a sample S of n IID environments from DE. We don't make assumptions about the underlying dynamics. They could be nonlinear or hybrid. We allow for rich sensing, e.g. camera images, and we assume an arbitrary black box task policy mapping the observations to actions. And so for this framework then, the intuition for how we will then perform failure prediction is as follows. We will assume that we can run the policy pi in any of the environments, and then from this we will get an observation history and a true label determining whether or not the controller truly succeeds or fails in the environment. From this, we can run the failure predictor online to generate predictions of failure. And then the cost for this then is structured as follows to act over the course of the entire trajectory. We have that if the trajectory is truly a failure, it must predict failure before the failure occurs. And if it's a success, it must never predict failure. In each case, there's a cost of 1 otherwise. So this is a setup to allow us to run online while having a cost over the whole trajectory. So in order to then generate bounds or safety guarantees, we need to train on the environments drawn just from S, but we need to generalize to the unseen environments in the distribution DE. So we'll use Pack-Bayes bounds that say essentially that with high probability, the true cost of a failure predictor generalizing to DE is bounded by the training cost plus a regularizer term. So then the intuition is that in order to get a good failure predictor that generalizes, we need to optimize the right-hand side of the above equation. However, this runs into a slight hitch, which is that if we assume that we have a good policy with a low failure rate, most of the training example will be successes, and the error won't depend on the actual failures that we want to classify. So in order to get around this, we motivate a class conditional Pack-Bayes bound in which we minimize the conditional error rates, and then this helps us control for the bias towards the more common class. So we show here an example for drone navigation, which we'll discuss in the experiments, where we see the true performance in blue and then the bound in red for minimizing varying weights of the conditional errors. For the first experiment, we used drone navigation. We have correct predictions in the top right and bottom left. And then we have an overly conservative error in the top left, where we stop a case where it doesn't actually fail. There were, importantly, no false negatives during test time, so we have a relatively conservative behavior. So for this experiment, the controller succeeded about 75% of the environments, as shown in the top row. Our misclassification bound for trajectories was on the order of about 12%, so we have reduced the number of costly failures by at least a factor of 2. This bound is validated both in simulation and on real environments drawn again from this distribution, as you can see in the last 2 rows here. The second example we use is vision-based grasping amidst clutter. So here, the robot is tasked with grasping a mug. Similar to before, we have the correct classifications in the top right and bottom left with an overly conservative misclassification in the top left. And again, no failures were observed at test time for this setup. So the results are similar, presented similarly to before, except we have 2 different controllers with varying degrees of performance, as shown in the top row. Again, the misclassification bound is able to meaningfully reduce the number of failures observed in testing. And then we're able to we validate these bounds again in simulation and on real experiments in the future. So in summary, we present Pack-Bayes failure prediction to provably improve safety online. The bounds are computable, interpretable, and they're policy agnostic, task relevant, and they apply to systems with arbitrary dynamics, high dimensional sensing, unknown measurement of the environment. So for more details, please see our poster and see our paper, which is linked. Thank you so much.
Okay, now for Yash from NVIDIA, the final talk before our Q&A. So get your questions ready.
I'll present Factory, a collaboration between NVIDIA, robotics, and simulation. We have 3 primary contributions. The first is methods for fast, accurate, robust simulation of contact-rich interactions developed in PhysX. The second is robot learning tools for robotic assembly, provided in Isaac Gym. And the third is proof-of-concept RL policies for assembly developed in Isaac Gym. I'll now discuss our methods for simulating contact-rich interactions. We synthesized sign distance field collisions, a contact reduction scheme, and a Gauss-Seidel solver to achieve our results. Rather than representing objects as convexes or meshes exclusively, we also represent them as sign distance fields. We compute the SDF for an object on a dense voxel grid and collide the mesh of an opposing object against this SDF. A canonical problem in contact simulation is simulating a nut and bolt assembly. And using SDF collisions, we were finally able to do this in real time. But SDFs are not all that you need. In robotics and RL, you may want to simulate hundreds of thousands of environments at the same time. But for a single M4 nut and bolt, you may generate 16,000 contacts. With a Jacobi solver, due to memory bandwidth limitations, you may only be able to simulate 20 nuts and bolts at the same time. and an inherently serial Gauss-Seidel solver would be unfeasibly slow. Thus, we implemented a contact reduction scheme. First, we generate candidate contacts using SDF collisions. Then we assign these contacts to existing contact patches based on the similarity of their normals. And for any unassigned contacts, we select the deepest ones and generate new contact patches. And we reduce contacts within patches using similar methods. Using this scheme, we can reduce 16K contacts to just 300. A Gauss-Seidel solver is now feasible, and we can simulate a theoretical maximum of 35,000 nuts and bolts. Here's a simulation of 1,000 nuts and bolts in real time. This is effectively a 20,000 times speedup over the state of the art. We also tested the simulator on 7 other challenging test scenes. Here are 512 bowls falling in the same environment. And for some reason, this video went viral. And here is a vibratory feeder mechanism actually vibrating at 60 hertz. And the Franca picks up a nut and tightens it onto a bolt, and we're able to simulate 128 of these in real time. I'll now discuss our robot learning tools, which consist of part models, robotic manipulation environments, and controllers in Isaac Gym. We provide 60 high-quality part models that were designed based on international standards or designed sourced directly from manufacturers. This includes all rigid parts on the NIST task board, as well as dimensional variations. We also provide 3 robotic manipulation environments for planing, control, and RL. This includes the nut-bolt environment, which includes a Franca robot and a nut-bolt subassembly, an insertion environment, which includes insertion assets such as electrical connectors and pegs and holes from the NIST board, and a gears environment, which includes the gears subassembly from the NIST board. We also implement 7 tensorized controllers, and the RL agents in our framework can be formulated to use their action spaces as targets to any of these controllers. Finally, I'll talk about our proof of concept RL policies. We use our simulator, assets, environments, and controllers to demonstrate that we can perform multi-step assembly procedures using data-hungry on-policy algorithms, but very efficiently. So we focus on the case study of nut and bolt assembly, and we decompose the problem into 3 phases: pick, place, and screw. We train a sub-policy for each, and then address policy chaining. So out of the 3 sub-policies, the screw sub-policy was by far the most difficult to train. It was replete with numerous pathologies that one might also expect to see in the real world. As a result, we did a systematic exploration of observation spaces, action spaces, controllers and gains, and reward formulations, and ultimately we were able to achieve an 85.6% success rate. We then focused on sequential execution of these sub-policies. We used a very simple policy chaining scheme whereby the output states of policy N were used to define the randomization bounds of the input states of policy N+1 during training. And we achieved successful execution of pick, place, and screw in sequence. Finally, we compared contact forces generated during simulation execution of the screw sub-policy against a real-world human data set for the same task. We found that the histograms were essentially very well aligned. Thank you very much. The factory code is being officially released today, and we're really excited to see what you do with it. Thank you.
Okay, thank you very much. So I have all the speakers come back up. I'll take the right to ask the first question, I guess, here. So for the factory talk, since we just heard it, so I guess the contact reduction was a big part of your performance improvement. And I know PGS is standard concern. The standard concern with the projected Gauss-Seidel is accuracy. So I wondered, did you ever do any metrics, for instance, on when you went from 16K down to 300 contacts, what's your maximum penetration on the 16K contacts? What were your kind of, did you have an energy dissipation budget? Did you check the accuracy of your reduction?
No, this is a great question. We didn't actually explicitly evaluate maximum penetration depth. I think it's an important thing that we should do. We should provide these maybe tables that can actually evaluate that. We also use TGS rather than PGS, okay. So temporal Gauss-Seidel, which has sort of accuracy improvements relative to PGS. Maybe some of those concerns will be alleviated.
Excellent. Okay, I see a question over here.
Yes, I have a question regarding to the failure prediction with statistical analysis. Yes, just wondering, what's the time, how much earlier can you predict the failure, or can you tune about it?
I'm sorry, could you repeat the last part of that really quickly?
So how much earlier can you predict for the possible failure, and can you somehow tune this horizon? Like basically, we can predict this failure earlier or sooner, or something like this.
Oh, that's a really good question. For the setup that we used, we only penalized as long as it was predicted beforehand. You could see in one of the experiments, like the drone, for example, had time to react in order to not hit the obstacles. I think there are ways you can modify the cost function, for example, so you could make it sort of scale with the amount of time in advance that you predict. I think the trade-offs are that the earlier you do it, perhaps, the less information you allow yourself to gather. It's maybe you look ahead and you see a lot of obstacles, then you see later there's a gap that you actually can go through. But it is tunable, yes.
I see. And another question is, like, in control theory, there's a lot of work done in reachability analysis. Like, have you considered that?
Yes. I think we were thinking of this as being, in some ways, complementary in that we rely on fundamentally different assumptions. And so we, for example, don't need as much, perhaps, if you will, sort of knowledge about the fundamental system dynamics, the noise, what have you. We allow the system to sort of behave so as it is. So we do have to assume stronger things about the environments not being, say, adversarial in order to do this. So I think they're kind of complementary type guarantees. Yeah.
I see. Thank you. Great topic, by the way.
Thank you.
Okay, it looks like we've got another one at the same microphone.
Yeah. Hello. My question is for SimForce. How do you guys handle constraints in optimization problems?
Yeah, so the question is about constraints.
Yeah.
So right now, the SimForce optimizer itself doesn't do hard constraints, although that's something that we plan to add. But we use soft constraints and barrier functions. And I'll also just note that, you can use the SimForce symbolic math and code generation and easily integrate that with any other solver, for example, ProxQP or any other optimization library you're already using by generating runtime functions and plugging them in.
Okay, thank you.
We have somebody up on the balcony that's going to ask a question. Get the microphone.
Hi, I have a question for the SimForce team. When you generate the C++ code from the Python code, how interpretable is it by a person? Like, could I read through the C++ code and understand it, or is it effectively treated almost like a black box in Sky?
Yeah, great question. So if you generate a function, the thing that's very interpretable is the interface. So that'll match argument for argument with your Python function, including kind of runtime versions of the geometry types and an eigen, dense, or sparse matrix, and so on. And the outputs. The inside of the function will have a series of kind of intermediate terms and then output results. And those, they won't be very interpretable at all, although you can look at the code. If it's a short function, you can, trace it out, but it's not, it's really a flattened version of what could have been many symbolic functions from different modules, and so it's not readily interpretable as a human.
Thank you.
Told one more question. Sorry, Eric. But last question.
Yeah, I have a question for David, the one on vision-based control. So now it looks like the obstacles were more or less at the same distance in all these scenarios. What happens if you have more variability in terms of the distance to the drone?
Sorry, just to repeat the question, it's about the distribution over the obstacles for the drone navigation example?
Yeah, so now it looks that they are always at the same distance, and you vary a little bit the position. What happens if you have more variability in the distance to the drone?
Right. So I guess there are maybe two sort of answers to that. One is it would mean in some sense you're in a different distribution, so you might have to deal with bounds for distributional shift. In terms of our particular choice, we were trying to generate examples where, we were trying to create a distribution where we, I think, believed that there would be some feasible options, in part because we just didn't want to drive the drone into too many obstacles too many times. So in that sense, I think we tried to make sure that there was many of the things would be feasible, but varying degrees of gaps or what have you. So you may have seen like the false negative rate. There was a very tight gap that it was trying to go through, and the gaps were a bit tighter there. In general, I think the main thing is whether or not there's a distribution versus an adversarial type setting is better for the problem at hand. Yeah.
Okay, let's thank these speakers again. Okay. We'll move on to the next 4 talks before for our keynote here. The first one is from Louis, who's going to tell us about contact detection from a convex optimization perspective.
Hello everyone, my name is Louis, and I will be talking about collision detection accelerated and optimization perspective. So collision detection is a fundamental problem in many robotics applications, such as optimal control, reinforcement learning, motion planning, but also in fields such as computer graphics. And basically, given the 2 convex shapes, we want to compute the distance that separates them. Since we spend more time than ever inside the simulation, we need every fundamental algorithm to be as fast as possible, and that includes collision detection, for which we can encounter millions to billions of collision detection problems. And so for the specific problem of collision detection or distance computation, the JGK algorithm was designed back in 1988 and is still state-of-the-art today. It's named after its authors, Gilbert, Johnson, and Kearthy. And the beautiful idea of JGK is that computing the distance between the 2 shapes is equivalent to computing the point of minimum norm inside their Minkowski difference, which is the set in gray. And although the sub-operations of JGK have been improved over the years, the algorithm itself has remained unchanged and is often presented as a computational geometry algorithm. And we argue that in order to better understand it and to accelerate it, we must view the problem through the lens of mathematical optimization. And at its core, as explained by the authors of JGK, the JGK algorithm is an instance of the Frank-Wolf algorithm, which was designed in 1956 and is one of the oldest and most studied method for convex constraint optimization. It can be understood intuitively as gradient descent modified to stay inside the convex set D. Basically, at each iteration of Frank-Wolf, we compute a support point by solving a simple linear subproblem. And after computing this support point, we move toward it, and by repeating this scheme over and over, we get closer and closer to the optimal solution we're looking for. And the computation of the support point on the Minkowski difference is very easy to do, as it can be decomposed back onto the original shapes. The problem with Frank-Wolf is that it zigzags. And to deal with that zigzagging, many solutions have been proposed over the years. And in this work, we focus on 2 of these accelerations for maximal computational efficiency. The first one is the so-called Nesterov-accelerated Frank-Wolf algorithm, which is a recent work by Lee et al., in which the authors modify the Nesterov acceleration of gradient descent to suit it to the Frank-Wolf setup. And intuitively, the authors add inertia to the gradient, which generates a different sequence of support points, which hopefully reaches the optimal solution faster. Now, the second acceleration of Frank-Wolf is in this talk is the so-called fully corrective Frank-Wolf algorithm, in which we try to identify the optimal active set, so the optimal set of support points, which describe the convex combination as fast, the optimal solution as fast as possible, as a convex combination of them. And it turns out that you only need simplexes to describe the optimal solution. So, and simplexes are very computationally efficient to work with because there are a minimal set of points. So if you take the fully corrective algorithm and you restrict yourself to simplexes, as we show, you get the JGK algorithm. So to accelerate collision detection, we designed the Nesterov-accelerated JGK algorithm, which uses the 2 previously accelerations I just mentioned. So we use JGK as a base, and we add the Nesterov acceleration, which only really adds 2 lines of code. So it's a very simple addition. And we also design a simple heuristic for meshes, which are especially important in robotics, which gives us better performances in practice. But the Nesterov acceleration is the star of the show, and it's, even though the heuristic is here for meshes, it's basically the same thing. So we evaluate our method, Nesterov accelerated JGK, against JGK on two very large benchmarks. One is made of ellipsoid, the other one is made of meshes, as you can see here. So for this mesh benchmark, we took thousands of shapes of shape nets, and we generated millions of collision problems. And our results show that both in terms of number of iterations and in terms of timings, Nesterov accelerated JGK is up to 2 times faster than JGK, and that's especially true for when the shapes are in proximity or shallowly overlapping, which are two very important cases in physics simulation, especially when you're doing contact simulation, for example. So finally, Nesterov accelerated JGK is already implemented inside HPP-FCL, which is a fork of the FCL library. And HPP-FCL is used inside the Pinocchio robotics framework. But you can also implement this Nesterov acceleration inside of your own JGK implementations, as again, it takes only a few lines to do so. Finally, I'm poster 10, so I will happily see you at the poster session. Thank you very much.
Excellent talk. Thank you very much. So we'll have Vincent from Princeton come and tell us about failure, fundamental performance limits this time. Yes.
Thank you. I'll be presenting our paper on fundamental performance limits for sensor-based control and policy learning. So problems in robotics often reduce to finding the right mapping between pixels or sensor observations to motor torques. However, it's not always clear what sensor observations we need to find the right motor torques for our task. A recent example of this is the ongoing debate between Waymo and Tesla, where Tesla insists that they only need cameras to get safe and performant self-driving cars, whereas Waymo uses a multimodal sensor suite to achieve this task. And so this raises the question of whether both of these methodologies are equivalent, or stated otherwise, whether or not there's a fundamental limit on the safety and performance that can be achieved with cameras only. So we attempt to address this in our paper by proposing a fundamental limit for robotic control, where we consider a partially observable Markov decision process, and our goal is to find an upper bound that is independent of how the policy is implemented on the closed loop reward achievable by your controller, regardless of how your controller is implemented. It could be via MPC or reinforcement learning or some other method. And to do this, we introduce a new quantity that we refer to as the task relevant information potential, or TRIP. And the definition of this quantity is a little bit too complicated to fit into a 5-minute talk, but it is a function of mutual information between the robot state and observation, and also the optimal closed loop, or the optimal open loop reward achievable on a given task. And importantly, the trip is monotonic in both of these quantities, which captures the intuition that if the task is either easy to perform in the open loop setting, then you can achieve better performance, or in the case where moving forward. So the trip provides an upper bound for single step problems, and we can leverage this bound recursively to derive to get a bound on multi-step problems using dynamic programming. In our examples that are coming up, it's important to note that we are restricted to a finite action space for numerical reasons only. Our bound is independent of that, but however, the theory is independent of that. So for our first example, we consider a POM-DP problem that's a common benchmark that admits a good open loop solution. So the robot needs to move to the goal state without falling into the lava, and there is a safe open loop policy that it can take where it simply moves left, either directly reaching the goal, or it will bump into the wall and then it can move right to the goal. However, the robot is equipped with a noisy sensor that gives a correct state reading with probability p correct, and it can use that information to achieve a better performance. And so we plot our bound versus the optimal POM-DP solution and see that we get a fairly close correspondence between the two. In our next example, we consider a ball catching problem where we implement a MPC policy that selects between various trajectories for the robot. And in this case, the robot receives a noisy estimate of the ball's location with different noise scales. And here the state and observation space are both continuous. Again, we see a close match between the two. In our final example, we consider a motion planning problem where the robot is equipped with a LiDAR, and it needs to identify a path that it can that will navigate it safely around the obstacles. And the LiDAR has multiple failure modes and different noise scales. And again, we evaluate our trip bound as we vary the noise scale and see that our bound it matches the performance well. And in the last case, the policy that we were comparing against was a learned neural network policy. And to conclude, I want to mention some future directions that we're looking at. The most direct is to use our bound to compare different classes of sensors for robot tasks. We would also like to modify our algorithm to be amenable to continuous action spaces as well. A much more interesting extension is to apply this bound to robust control by considering fundamental limits on the performance of an adversary and then trying to minimize the performance of the adversary so that we can generate a large reward with a guarantee. And finally, we'd like to try and derive similar fundamental limits for other important quantities in robotics like memory or computation.
Okay, next we have Charles Dawson from MIT. He's going to talk about robot design optimization.
All right, thank you. As Russ said, my name is Charles Dawson, and it's my honor to be here as part of this fantastic program. Today I'd like to talk about how advances in programming languages, particularly automatic differentiation, can be used to improve the experience of designing and verifying robotic systems. To motivate this talk, I'd like to start by thinking about how engineering design happens in other disciplines. For example, both mechanical engineers and electrical engineers can make use of automated or semi-automated computational design aids to be more productive during the design process. This begs the question of what tools are available to us as roboticists to accelerate our design process. Clearly, robots are more than the sum of their hardware, mechanical, and electrical parts, so we need to think about what new computational design aids are appropriate for the robotics task. Our key insight in this paper is that if we can model a robotic system, both its software and its hardware, through a simulator, which is itself a computer program, we can use program analysis techniques like automatic differentiation to improve the process of designing and verifying that system. This idea of using automatic differentiation in the design process is not itself new, but our new take on it in this paper is that we can look at the full stack autonomous system from planning all the way down to control, and we look at the entire robot design process to come up with a framework that uses automatic differentiation in the process of design. At a high level, we like to think about this sketch of the robot design process. This starts with high-level design in problem definition and architecture selection, where the designer needs to think about what task they want to solve and what robotic system they're going to use to solve that task. And then it proceeds to a lower level where the designer needs to optimize their given architecture and then verify that their design will achieve the desired amount of performance. The important distinction between these two levels is that a lot of the creativity in the design process happens at the higher level in problem definition and architecture selection, where the designer needs to specify things like the objective and what parts of the robotic system are subject to optimization. To go through a concrete example, we can consider this case where the designer wishes to use two robots to collaboratively manipulate a large box. Here in the problem definition phase, the designer needs to specify an objective, say get the box as close as possible to its target, and they need to specify some assumptions about the environment, such as making assumptions about the distribution of parameters like coefficients of friction. Then we need to move into the architecture selection phase, where we need to think about what sort of robotic system is appropriate to solve this design problem. And this involves specifying which parameters are open to optimization. In this case, we already said we're going to use 2 autonomous ground robots, but we might say that we want to use a neural network path planner to choose what paths those robots are going to follow, and then a feedback controller for tracking that trajectory. We don't need to know at this point what the exact parameters of that system, of those subsystems is going to be. We just need to sketch out the design in enough detail that we can implement a simulator to model its behavior. Once we have that simulator, we can use program analysis techniques like automatic differentiation to invert that simulator. You can use your favorite gradient-based optimization method to modify the design parameters to achieve the best performance. We also include a couple of different domain randomization and variance reduction techniques at this step to achieve better performance. And here we can see that the initial design with random parameters on the left does not get the box, which is the open outline close to its target position, whereas in the optimized design, it can get pretty close. Once you have an optimized design in hand, the next question becomes, how do you verify that design? How can you be sure that your design will achieve the desired level of performance? There are 2 sub-questions that we can consider within this topic of verification, and specifically in the context of our statistical method for verification. The first is, what is our expected worst-case performance of a design? And the second is, what is the sensitivity of that design to changes in the environmental parameters? For instance, our coefficients of friction in the simulation can't be perfect, so how much would we expect the performance to degrade if those parameters were to change? We answer both of these questions through the lens of extreme value theory and statistics. And there's a lot of nuance that I'd love to get into, but don't have time for this talk, so please ask a question in the Q&A or come up to the poster session. I think we're poster number 12. A natural question here is that if we're relying so heavily on simulation for designing and verifying a robotic system, what about the sim-to-real gap? Well, the anecdotal and empirical answer to that is that in our case, due to our domain randomization and variance reduction techniques, we find that the gap is not very large at all. Even with the rich contact dynamics in this pushing case, we are able to transfer without any further tuning or any system identification at all. I'd like to close both with these contributions and with a request, which is that if any of you are working on a challenging design optimization problem in robotics, and I'm sure many of you in this audience are, I'd love to hear about it. Please come up to me at the poster session, and I'd love to have a conversation about how we can use our framework to accelerate your design and verification process.
Okay, our last talk for the session is Ciro Moreno, who's going to talk about collocation methods for second-order systems.
So, our purpose with this talk is to show that the usual collocation methods for trajectory optimization are fundamentally flawed when applied to second-order dynamical systems like those in robotics. I will try to show you why and present our solution to this problem. To start with, let us recall the trajectory optimization problem. Suppose we have a robot for which we want to find an optimal trajectory Q of t minimizing a given cost function. This trajectory must fulfill some path and boundary constraints and satisfy the dynamics equation of the robot. To solve this problem numerically, a usual choice is to apply a collocation scheme. This consists in dividing the time domain into intervals and applying a quadrature rule to each interval to transcribe the continuous problem into a nonlinear programming one. This is done by imposing the constraints at a set of collocation points. The crucial part of this process is how to transcribe the continuous dynamics equation into its discrete counterpart, and this is the focus of our work. Usually, dynamics are described by a second-order differential equation, but usual collocation methods are designed for first-order systems with this form. So, to use these methods, in robotics, we typically reduce our problem to this form by defining the state vector x as qv and adding the constraint q equal to v. This results in this first-order system, which already has the form stated below. This reduction, which in the continuous domain is perfectly valid, leads to inconsistencies when the problem is discretized. In usual collocation, configuration and velocity trajectories are approximated using polynomials of the same degree, collocation equations for the slope q dot k to match the vk value at the collocation points. However, q dot of t will be a polynomial of a lower degree than v of t, so the two polynomials will not coincide. This yields an inconsistency between the q and v trajectories. Moreover, since the two curves do not coincide, the derivatives will be different too. In this case, their values will be different even at the collocation points because no constraint is imposing their coincidence. So we have that the collocation constraint imposes this condition, but we have that these two values are different. So the second order dynamics equation is not satisfied at the collocation points. To solve these inconsistencies, in our approach, we directly impose the second order dynamic constraint at the collocation points, and we impose q dot equal to v on the approximation polynomials. As a result, we obtain new versions of the trapezoidal and Hermite-Simpson collocation schemes that remove the inconsistencies and also present continuous accelerations. Here we see the collocation equations for the usual and new versions for such schemes. We can observe that the new equations are similar in complexity. The main difference is that usual scheme use the state variables in the same way, but in the new schemes, we have different collocation formulas for the Q and V variables. To see how the new schemes compare to the usual ones in practice, we apply them to two benchmark problems from the literature, the carpal swing up and the 5-link bipedal walking problem. To measure the quality of the obtained solutions, we compute the second order dynamic error, which is the integral of the residual of the dynamics equation. Here, we can see how this error decreases with the number of time intervals for the usual schemes. This is for the bipedal problem, but for the carpool, the plot is similar. Clearly, the Hermite-Simpson schemes shows a much lower error compared to the trapezoidal schemes. But when we switch to the new schemes, the error for each method is reduced in more than 1 or even 2 orders of magnitude, depending on the case. We can observe that this increase in accuracy doesn't come at the cost of additional running time, as new algorithms take about the same time as the usual counterparts to find a solution. So to wrap up, we can conclude that usual collocation methods yield inconsistent configuration and velocity trajectories, whereas the new methods we propose achieve trajectories with a much smaller dynamic error, satisfaction of the dynamic equation of the collocation points, consistency of the configuration and velocity trajectories, so less control effort will be required to track them, and continuous accelerations, which result in smoother trajectories, and all that without increasing the computational cost significantly. Thank you, and I hope to see you at poster number 13.
Okay, we'll ask everybody back up here again and have a few minutes for questions. Maybe I'll start, even though there's someone at the microphone, but this is my chance. Okay, so Vincent, so yes. I haven't thought enough about TRIP yet, but it sounds too good to be true. So I find myself trying to defeat it, right? Like, so the way you write, so the way I would think you would defeat it is if there's problems that are susceptible to memorization, for instance. Like if there's something that maybe, I think you guard against this with your open loop R in the mutual information, but what if there's something where if I get one bit of information that has a low mutual information with my state, but it's enough for me to flip in a memorized something? It seems like, it just seems fundamentally very hard to bound the performance in that kind of a setting.
Yeah, so I would be curious to see how it performs in that case, but I think that that would be compensated, like as you said, that would be compensated for by the relationship between the mutual information and the kind of like open loop case. I mean that is somewhat. I guess that would be one step past the lava problem, because the lava problem you can solve without with zero information. But but you're right. I would be curious to see how it performs there, but yeah, the boundary accomplishment. I would say that the main way that, I didn't have time to include this in the 5 minutes, but the other big assumption that we have is that the rewards are bounded. So if you have unbounded rewards, then the generalized Fano inequality, which is how we derive the trip bound, that doesn't really hold. So
that seems okay.
Yeah.
Good. Awesome. Thank you. There's a whole line of questions here.
Yeah, I have a question for Charles. So for the example you showed, it seems like the parameter search space is rather small. Have you looked into ways to use your framework for, like, for example, larger scale robotic system where you have more parameters to search, and then have you looked into ways to sort of like figure out the correct parameters to optimize?
Yeah, that's a great question. So in our paper, we use two main examples to demonstrate the capabilities of our system. The example that I showed on the slides here actually has several hundred parameters. It's a several layer fully connected network in planning, and then a number of trajectory feedback control gains. So I think several hundred is the upper limit that we've tested so far. The other example that we showed had far fewer parameters, but many more subsystems. So the other example in our paper is an autonomous navigation problem where you're optimizing the location of landmarks for sensor-based navigation. In that problem, we had more on the order of 10 parameters to optimize, but we had interactions between 5 or 6 independent subsystems that we wanted to optimize through. So I would say that the short answer is we've tried up to several hundred parameters. It performs well, and there are tweaks that you can do for automatic differentiation, forward or backward mode, depending on the relative number of parameters that you have.
Thank you.
Hey, I also have a question for Vincent on the fundamental limits paper. So I wonder if you could comment on how tight the upper bound is. I think in your talk we saw as the noise level increases, the bound and the actual performance gap also widens.
So we don't have a theoretical quantification of how tight or loose the gap is at different noise levels, but it does it does seem that way in some examples, but not in others that we tried on. Yeah, so that would definitely be something to look at in an extension. But in general, we have found that the bound is, I guess, what I would call practically tight, and that it's not like totally vacuous in a lot of cases. So, yeah, so that's definitely something that I'd be interested in looking at for the next paper.
Cool, thank you.
I'm afraid we're only allowed one more question because we have to move on to the keynote. Sorry. Here we go.
I really like the idea of design and algorithm co-optimization. I'm wondering, how do we satisfy the physics constraint of designing the robot? Some parameters need to be physically plausible, right?
Yeah, that's a great question. So I think that at a high level, you can compare our optimization most directly to a single shooting optimization where the physics are baked into the simulation. So if you have hard constraints on the physics, we're not trying to satisfy those through collocation, for example, where we have those as hard constraints in the nature of the simulation. For parameters that you don't have full control over, our framework includes a distinction between design parameters, which might be like the weights of a neural network that you can freely change, or the mass of a link in your robot, and exogenous parameters or environmental parameters. So we include a method for handling these uncontrolled parameters in the environment. So in the example that I showed, the parameters that were uncontrolled included the mass of the box, the initial position of the box and the robots, and the coefficients of friction of all contact pairs. And those were assumed to vary according to various different distributions, either uniform or Gaussian. So we include the opportunity to bake in those uncontrolled parameters to our framework, because I think it's definitely important to account for what you can't control in the design process.
Thank you.
Okay, I hope you'll ask the rest of your questions at the poster session. Let's thank our speakers again.
All right, it is my distinct pleasure to welcome one of the world's most foremost researchers in bioelectronics, John Rogers. He is the Lewis Simpson and Kimberly Query Professor of Material Science and Engineering, Biomedical Engineering and Medicine at Northwestern University, and he also serves as director of the Query Simpson Institute for Bioelectronics. Before joining Northwestern, he was faculty at my current institution, University of Illinois, but I promise it wasn't my fault he left. We did not overlap. He's a member of the National Academy of Engineering, the National Academy of Sciences, the National Academy of Medicine, the National Academy of Inventors, and the American Academy of Arts and Sciences. He has been recognized by numerous awards, including a MacArthur Fellowship, the Lemelson MIT Prize, the Smithsonian Award, the Benjamin Franklin Medal, and a Guggenheim Fellowship. He will be giving his talk entitled Wireless Skin Conformal Devices for Health Monitoring and Haptic Interactions, and let's give him a warm welcome.
All right, thank you, Chris, for that kind introduction. It's a real pleasure to be here. I have to admit, I don't have enough opportunities to interact with this particular community. It's a little bit outside of my core areas of expertise, but I'm excited because I think a lot of the things that we work on have very powerful potential synergies with the field of robotics. And so I'll share some of our work with you, but keep in mind those potential areas for collaboration, and I'd be happy to have follow-up discussions with anybody who identifies areas of overlap that might be interesting to explore. So as Chris mentioned, I'm at Northwestern. My core expertise is in material science and engineering, but we do a lot in the space of bioelectronics and biomedical engineering. And in this talk, I'll sort of summarize what we've been doing in those fields and try, as I move through the talk, to highlight opportunities where these platforms might be useful to consider as input-output interfaces to robotic systems. So devices that either mount on the human body who's controlling a robot, or robotic skins that may provide an enhanced sense of a range of capabilities for the robot to perceive its physical surroundings. And so the title of the talk, as was mentioned, is sort of wireless skin conformal devices. So these advanced classes of microsystems technologies, electronic, optoelectronic, photonic, and even vibrohaptic microelectromechanical systems that are designed to be compatible with the human body. And in general, with moving curved surfaces that one might encounter in the field of robotics, mainly for healthcare monitoring, monitoring physiological health, mental health, that sort of thing. But also more recently as a capability for generating haptic interactions that could be useful for virtual environments that go beyond just visual and audio cues. And I think it's really that area that may have the strongest potential for intersection with this particular community of robotics. So I'll start a little bit with a background and give you a sense of the technology foundations, but I'm going to go pretty quickly and not sort of dwell on the underlying ideas or the material science, but try to give you a sense of the technical maturity, the kinds of platforms that are possible currently, and the range of capabilities, both in sort of medicine, but as well in this area of virtual and augmented reality, sort of skin interface devices that provide haptic cues and a sensation of touch to complement video and audio inputs. We do have actually a small effort in robotics as conventionally conceived, and as bonus content, if I have time at the end of the presentation, I'll give you a sense of what we're doing in that space. I think we built the world's smallest terrestrial micro robots to give you a sense of what that's all about as well, again, if I have time. So, as Chris mentioned, I'm at Northwestern. We have a unique institute, at Northwestern. I'm fortunate enough to serve as the director of that institute that really facilitates research at the boundaries between engineering science and medical science. So trying to develop new technologies that can have a positive impact on human health, improve patient outcomes, reduce costs, and change the way that we think about delivering healthcare into the future. And so what that involves is, at least in part, an attempt to kind of reformulate the classes of electronics that currently serve as the foundations for consumer electronics gadgetry into platforms that are compatible with soft tissue systems that you encounter in the biological world, the human body specifically. And so this is probably one of the world's most successful forms of technology, the CMOS integrated circuit. It's very powerful. But if you think about the physical properties, you think about the kinds of constituent materials that are used to form these integrated circuits, they're highly mismatched from the sort of textured, soft, time dynamic surfaces of the body. I mean, this platform is completely planar, to align with the kinds of optical and photolithographic procedures that are used to fabricate these devices. They're built on rigid platforms of high modulus materials like silicon wafers, silicon carbide, for example, that don't bend and they fracture easily. And so what we've strived to do as material scientists is overcome those physical constraints in integrating this class of technology with the human body by developing new materials, new manufacturing strategies, new design strategies to enable soft forms of electronics. And you might ask, well, what's that going to be good for? Well, I think one of the most obvious examples would be to take this kind of technology and interface it with the human brain. So bring man's most sophisticated form of electronics into intimate interfaces with biology's most sophisticated form of electronics, to maybe as research tool to understand the basic operating principles of the brain, or to deliver engineering forms of medicine to treat various sorts of brain disorders, or maybe into the future as the basis for a brain-machine interface. Again, as a control system, perhaps for interfacing with an external robotic system. And so, like I said, I'm not going to dwell on the underlying foundations of what we've been able to do, but just sort of cut to the chase and make the statement that at this point we can create skin-like forms of electronics that have all the sophistication that you would see in a microprocessor that's in your smartphone. And the way that we do that is we start with the wafer. We create a very thinned version of those integrated circuits, reduce the thickness of the overall system by a factor of 1,000 or so. That renders mechanical bendability just due to the fact that the flexural rigidity scales with the cube of the thickness of the material. We split it into very tiny parts, and then we interconnect those parts with serpentine interconnects that provide an out-of-plane buckling mechanics that, when embedded in a soft elastomer, give you a soft, stretchable set of physical characteristics that can be tailored to really match an interface point of interest across the body: skin, brain, heart, bladder, kidney, and other places where we deployed this kind of technology. So you think about it from a design standpoint, now you're considering circuit design as a primary driver in how you do the layouts, but now you're also coupling circuit design with mechanics design. And we do that through full 3D finite element modeling of the mechanics of these hard, soft, hybrid material systems. So you can do all of that, and it turns out that that works very well, and you can create devices now that can be interfaced with any location across the human body persistently to sort of blur the distinction between the artificial system and the living system for purposes in health monitoring. So this was an early device of that type that we published in 2011, just illustrating that we felt like we had a handle on basically how to do this form of soft electronics, where we developed systems that have all of the physical attributes of the epidermis itself. So not just the modulus and the range of stretchability, the bendability, for example, the flexural rigidity, bending stiffness, but also the aerial mass density, the thermal mass, the water vapor permeability, and so on. So you can almost think of this as a second skin that goes on your natural skin to establish a physical interface that allows you to reproduce a lot of the clinical grade measurements that are currently confined to hospital settings, now deployable into the home, operating in a wireless fashion for continuous monitoring of health, not episodic evaluations that currently serve as the basis for how we do healthcare. So that was 2011. We got a little bit better in 2014. And from that point on, we really focused on adapting and engineering these kinds of systems to address specific unmet clinical needs. And I'll give you some examples in the next few slides. But there's a whole sort of zoology of these kinds of devices. The idea being that you can create platforms that can mount at any location of the anatomy. You can think about these as wearable devices, but not constrained to the wrist or the finger. You can place them on any relevant part of the anatomy to address a particular measurement requirement. Each device can include multiple classes of sensors, and you can mount multiple devices at different locations across the body and do readout in a highly time-synchronized manner to get kind of full body assessments of health processes, all without the wires and without the need for hospital apparatus. So there are a number of different kinds of sensors that have been developed over the years, not only by my group as a sort of a global community now working in this space, precise thermal characterization, not only spatial and temporal mapping of millikelvin variations in the temperature of the surface of the skin, but also quantitative measurements of thermal transport characteristics, heat capacity, thermal diffusivity, thermal conductivity, and so on. All sorts of electrical sensors as well, so you can pick up biopotential, you can pick up brain waves, electrocardiograms, electrical activity associated with cardiac cycles, muscle activity, motion of the eyes, for example. You can embed in these same platforms microfluidic channels, and so you can capture micro and nanoliter volumes of sweat, eccrine sweat, as it emerges from the surface of the skin, and you can do biomarker analysis of sweat as a non-invasive analog and correlate to blood chemistry. All kinds of mechanical sensors as well, strain, motion, modulus, pressure, and get kinematics. You can measure volume changes. Optical sensors, optoelectronic devices drop very naturally into these types of frameworks. So you can do blood oxygenation, for example, other kinds of optical measurements of tissue properties. You can also measure body sounds. So you can reproduce the kinds of function that you would associate with a stethoscope, but now in these wireless patches that could be mounted at various locations across the body. So you can do cardiac auscultation, for example. So each device is multimodal. You can stack up multiple sensors in any individual platform. As I mentioned, you can operate them as a multinodal body area network as well, all time synchronized to microsecond levels of precision with clinical grade quality. So that's an aspiration and a goal that we've been able to meet, so you can reproduce ICU grade measurements, but again, continuously in a home setting. At cost points that would allow this type of technology to be deployed around the globe, not just in expensive healthcare facilities like we have here in the United States. I'll give examples of that in the next few minutes. So the class of patient that we focused on initially was one that we thought could benefit most strongly from this kind of wireless skin-like technology, and that class of patient happens to be premature babies. And so if you've ever experienced what happens in a neonatal intensive care unit, you'll realize that it's a highly primitive, highly non-ideal engineering solution to the problem of continuous monitoring of all vital signs, because these patients are in a very fragile health status. Their vital signs need to be monitored 24/7 so that healthcare professionals can engage as necessary. And that's currently done by hardwired interfaces that join skin-mounted biosensors affixed to the surface of the skin with adhesive tapes to external boxes of data acquisition electronics. This is the way that it's done, even in the most sophisticated level 4 NICUs that we have in Chicago, for example. But the problem is that the tapes can induce damage to the skin upon removal, and they have to be removed on a 12, 24-hour cycle as part of the standard of clinical care, because the skin in these babies is highly underdeveloped. It's very fragile. It's almost like an open wound, and so that represents a risk factor. The presence of the wires actually is a natural constraint to movements of the baby, and so that's not non-ideal, and it also frustrates the kind of parent-child interactions that are known to be so important for therapeutic development of the baby at this stage of their lives. And so this was a power of Photoshop illustration of what we were hoping to do. This is back in 2016 or so, is like get rid of this rat's nest of wires and the invasive tapes and replace that with one or two of the, or three of these skin-like wireless devices to improve the care of these patients. And it turns out you can do all of that. And I won't go into the details. We published this in spring of 2019. So with a pair of devices, skin-like in their physical properties, wireless and battery-free in their operation, you can reproduce all of the vital signs that are currently measured with those wired-based setups. One of them goes on the chest, the other one goes on the limb. The one on the chest is capturing electrocardiograms from which you can determine heart rate variability, respiration rate. There's also a clinical grade digital temperature sensor in this chest unit, which is a pretty good approximation of core body temperature. And then the other device is going on the limb to determine blood oxygenation. They're time synchronized, so we're also getting hemodynamic information as well, actually going beyond what's done in a NICU facility today. So this is a 26-week gestational age baby, one of about 200 premature babies that we've tested the technology on through our collaborations with folks at Lurie Children's Hospital. This hand here is the hand of Aaron Homvis, who's head of neonatology at Lurie's. You can see our device here, and we do all of our measurements in parallel with conventional assessments using these wire-based devices to establish quantitative equivalency between skin-like wireless and the traditional wired-based systems. So that's turned out to work very well for monitoring in the NICU. It's actually propagated beyond the NICU into the PICU, so this is the pediatric intensive care unit, slightly larger babies, but in most cases in challenging health situations that require 24/7 vital signs monitoring, and the wireless skin-like platforms that I just described to you are very beneficial for those classes of patients as well. And so you can see a baby here in the PICU at Prentice Women's Hospital, also downtown Chicago. You can see the device on the chest there, measuring the parameters I mentioned before, device on the foot, that's getting blood oxygenation. And we can determine the time delay between when a pulse of blood is initiated from a cardiac cycle as measured with this device and the time arrival of that pulse of blood at the foot. And it turns out that that pulse arrival time and the equivalent pulse wave velocity is a pretty good surrogate for blood pressure. So you get a beat-to-beat non-invasive measurement of blood pressure as well. So these are wireless and battery-free in their operation. We use a magnetic inductive wireless link for power delivery and also data communication. It's happening through an antenna, in this case, that's mounted on the base of the chair. So that's what it looks like. Here's the raw data. I won't get into the details, but the data is illustrated up here. This is ECG. This is photoplasmography. These are the optical measurements that you need to assess blood oxygenation. And those are three raw data streams, very important. We actually, in this instance, are also going beyond what's the standard of care because we have a high bandwidth accelerometer in the chest unit. And so we actually get cardiac sounds. This is seismocardiography, and so you can measure the sounds of the opening and closings of the valves in the heart. And that provides information that's complementary to the electrical characteristics associated with a beat cycle as embodied by the electrocardiograms. You also get chest wall movements, so you can capture respiration rate using multiple data streams for redundancy. So this is all the raw data, tremendous amount of information there, and we're working on advanced machine learning algorithms to try to tease out subtleties associated with the shapes of these waveforms. But what's done currently in hospitals, you just take that data and you distill it down into very primitive parameters, just heart rate. You can see the heart rate variability there as well. SpO2, that's blood oxygenation. You're getting this parameter from those two curves. This curve is giving you the heart rate. You get respiration rate either from chest wall movements or for variations in the peak of that R feature in the QRS complex. You get temperature, and with a pair of devices, you also get variations in temperature between the core and peripheral locations, such as the foot and the hand, and that provides additional insights into cardiovascular health. So we published those results in spring of 2019, very shortly after we were approached by program managers at the Bill and Melinda Gates Foundation and folks at the Save the Children organization asking whether we could take those kinds of technologies and deploy them into lower and middle income countries where there's no monitoring hardware at all, wired or otherwise. And that occurred to us as a great challenge, so we were able to take the devices that I just described to you, engineer them to allow for deployment in these very resource-constrained areas of the globe at manufacturing cost points that would allow for economic viability in the range of a few cents in terms of patient monitoring days. And so we were able to do that. I won't get into the details. We published the results about a year later. And now we're deep into a scaled deployment of these devices, about 10,000 of them so far into India, Pakistan, Zambia, Kenya, and Ghana. And that started in 2020. This is an example of my students training healthcare professionals in Zambia on the use of these technologies. I think I was taking the picture here, spent a couple of weeks in Zambia to see how these technologies can impact not only how we treat infants and newborns in the developed world, but also in these resource-constrained areas of the globe. So to just give you a sense of kind of what's possible, we have a number of different these soft electronic technologies that I would say are entering this similar kind of translational pipeline, sort of moving them out of an academic laboratory context and into scaled production and deployment. We have startup companies that are configured to do that. I won't go through the details. They're doing a lot in maternal fetal health as well as a natural extension of what we've done in the past in neonatal and pediatric health. But let me focus on some challenges at the end of life. So we're very interested in beginning of life challenges, again, maternal, fetal, neonatal, pediatric, but also end of life health challenges that might represent areas of opportunity for these kinds of technologies. And there we work with Parkinson's patients, Alzheimer's patients, and stroke survivors. So this is an example of a device that we developed in response to a request from rehabilitation physicians at our Shirley Ryan Ability Lab. It's one of the largest rehabilitation hospitals in the world in downtown Chicago. And one of the challenges they have is with stroke survivors, they have to relearn basic things that we sort of take for granted. So they have to relearn how and when to swallow, for example. They have to relearn how to speak. And so they come into the rehabilitation clinic, they go through various training protocols. In many cases, their condition improves while they're in the clinic, but a lot of those gains dissipate when they return to the home. So the request was for a device that would allow a physician to remotely monitor patterns of speaking and swallow dynamics remotely and continuously in a home setting. And so we're able to do that. We developed a soft sort of Band-Aid-like device that mounts on a unique part of the anatomy. It's a soft tissue location at the base of the neck known as the suprasternal notch. And it includes a high bandwidth tri-axis accelerometer sitting right at that location, wireless Bluetooth connectivity to a phone or an iPad with embedded memory that allows for on-sensor data storage. And from that position, we're close enough to the throat, we can measure swallow events. We're coupled to the chest wall cavity, so we can measure when those swallows happen relative to the respiratory cycle. And we have enough bandwidth here, we can actually measure vibratory motions of the surface of the skin as an indication of speech without needing a microphone. And that turned out to be very important for a couple of reasons. One is the microphone represents an invasion of privacy. There are very few people who want everything that they say to be recorded with a microphone. You can't get anybody to sign up for that. The other thing is with a microphone, you can easily be confounded by ambient noises. And so this is a study group where we have devices monitored on this individual and this individual. They're having conversation with one another, but this device is only responding to speech patterns of the person who's wearing the device, and likewise for this person as well. And it doesn't produce an audible signature of voice. It just captures a pattern of vocalization, tonality, and cadence, which is what the rehabilitation specialists actually need and want. So this device was designed initially to measure swallow and speech in the context of aphasia and dysphagia associated with stroke survivors. But it turns out that this is a very information-rich location of the body for measuring physiological parameters relevant to health. I mean, you might ask yourself the question, if you have one wearable device, where would you put it on the body to capture the most rich, broadest, and deepest set of data associated with health? And we think the suprasternal notch may be the answer to that question, because you get speech and swallowing, which is what the device was originally designed for, but you're actually close enough to the carotid arteries so you can actually measure motion signatures associated with pulsatile flow of blood up through the carotid. So you actually, from that data, you can get heart rate and heart rate variability. As I mentioned before, you're also coupled to the chest wall cavity, so you get motions associated with respiration, so you get respiration rate. You also get respiration sounds, so you can capture sounds of wheezing. You can count coughs, for example. You can determine if it's a wet cough or a dry cough. You're coupled to the core body, so you get core body orientation. And of course, you can just capture activity levels as well, because you can monitor steps and motion in that way. So it's one device, a very simple device, only requiring a mechanical coupling to the skin, but tremendous amount of data associated with the recordings. And so what does that look like? This is raw data collected from that device, so it's a tri-axis accelerometer. Again, Z is the out-of-plane direction, normal to the surface of the skin, and you can kind of see the different features here. So it's mounted on an individual sitting still initially. You can see the cycles associated with respiration, but you also see this fuzzy stuff here. If you zoom in, those are the cardiac sounds. Those are pulsatile signatures of blood flow coming through the carotid. You continue here, and the individual starts to talk. You can see very well-defined oscillatory signatures of speech with associated harmonics. And so even though these features could be overlapping in time, they have unique spectral characteristics. So you can develop simple bandpass filtering approaches to separate out all these activities and quantify them, even though they appear in just a single time series of data. Here's a swallow. This is a very characteristic feature. You can't confuse that with talking or cardiac activity, so you can count swallows very easy. And then walking and running correspond to very high amplitude motions that you can likewise separate from these other features. So with a set of digital filters, you can take the raw data and you can distill it down into energy expenditure, for example, heart rate variability, respiration rate, swallow count, and talk time, just as very simple metrics that people are interested in measuring. So this is what some raw data looks like from a Parkinson's patient who's undergoing therapy around swallowing. And the raw data is shown in the upper graph here, and so it kind of looks like a noisy set of data with a little bit of oscillation superimposed. It's actually not noise, so if you apply a bandpass filter that allows signals associated with frequencies between 20 and 50 hertz to pass, you capture all the cardiac signature. And you pull that out, you do peak finding, you determine heart rate variability, Then you can take this data, you subtract it away, and then what you're left with is very high signal and noise measurements of oscillatory behaviors associated with inspiration and expiration. So you're getting depth of respiration and also respiration rate. But what's interesting here is you're also capturing swallow events. Difficult to see in the raw data, but they show up very nicely here after you do this bandpass filtering and subtraction. There's a swallow, there's another one, there's another one. So you can count how often swallows are happening. It's very important because Parkinson's patients, stroke survivors, for example, many times don't swallow frequently enough, which is why you see some of these individuals drooling, for example. They're just not swallowing enough. And so this is a device that allows you to quantify swallowing and provide that as feedback to the patient so they can learn how to swallow at a normal cadence. The other thing that turns out to be important with swallows is it's not just that you have to swallow frequently enough, but you have to swallow at the right time point relative to the respiratory phase. And so naturally, and you probably do this unconsciously, you swallow at the peak of inspiration or the depth of expiration. You never swallow halfway in between. And if you do, you'll choke yourself, and that can be a life-threatening type of thing. So here, the patient is swallowing more or less appropriately here, 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 maybe slipping up a little bit here. So you get a lot of information, single device of that type. So what does it look like, those kind of measurements as they're done today in a rehab clinic, like the #1 ranked rehabilitation hospital in Chicago? Well, it consists of a couple of things. It's these respiratory inductance plethysmography bands that mount on the upper and the lower chest. And then nasal cannulas that allow you to measure airflow. And they use airflow variations to determine when swallows occur. And they're using these RIP bands to capture those cycles of respiration. And these devices then connect through hardwired connections to data acquisition electronics, allow you to record all of this and provide real-time feedback to the patient. So the idea is get rid of all of that, allow for a much more accurate and much more natural way to do rehab while they're in the clinic, but in a form factor and a platform that can deploy to the home. So here's what it is. It's the device on the suprasternal notch, and this is real-time streaming to an iPad that's doing real-time data analytics. So it's just simple bandpass filtering. You get the respiratory signal here. You get the high-frequency stuff here. You can identify the swallows here, and you can see exactly providing visual cues to the patient. So when they're swallowing, how often they're swallowing, and when those swallows are happening relative to the respiratory cycle. Now, this is the transition where I'll focus more on haptics, which is it's fine if you're looking at the screen, you get all this information, but a lot of times you might not want to have to stare at your smartphone or stare at your iPad. So there, having a vibrohaptic interface to the body can create non-visual, non-audio cues to the patient to create an awareness. So what we did here is this is a multi-haptic interface. It's a band that goes around the wrist. It's Bluetooth connected to this sensor. We do in-sensor analytics here, passes the swallow information, the respiratory information, and provides vibratory signals to the patient to let them know what's going on with their swallow behavior. Now that might seem like a very narrow targeted application, and perhaps it is, but it got us thinking more broadly about skin interface devices, not just for sensing, but also for providing information to the individual using skin as the interface and maybe creating an artificial sense of touch. And so you think about what types of devices involve haptic feedback. There are lots of them. Game controllers, smartwatches, smartphones, industrial equipment, and so on. So handheld devices, vibrating motor, it's fine. It's a pretty primitive type of haptic interface, but it's one that's been around for a while. And so we took a look at what is the history of haptic. And it involves a lot of those kind of portable devices that may be predated from desktop systems that have haptic vibrators built in, and they engage through the fingertips when you interact with the device. Moving into gloves, where the haptic engagement is really focused on the fingertips. Lots of work has been done in that space over the years. But then looking to the future, maybe thinking about these skin-like devices for haptic engagement beyond the fingertips to the entire body. Like what would that look like, and would that be sort of interesting, maybe for application not only in medicine, but again as maybe control interfaces to robotic systems. And we know a lot about how to make electronics into skin-like forms. Could we kind of leverage that for haptic devices as well? And so the whole emergence of this metaverse is sort of, amplifying, directions that we were going anyway. And you may have seen, YouTube videos of the latest devices out of the Meta reality labs in in Seattle. And I mean, these are sort of wearable robots, I guess is the way you can think about it. And so I haven't really decided if that's interesting or frightening. But anyway, it's a device to create sort of a haptic engagement to go beyond just the visual and audio components of VR systems as they exist today. And so we've been interested in this for a while. It sort of dates back to 2012. We have like a finger cuff, and we're using electrotactile stimulators. So these are pairs of electrodes. You can inject current. You can directly excite haptic haptic sensors in the fingertips and create kind of a rough sense of touch in that way. It's not that ideal, however, because the threshold between creating a sensation and causing pain is very narrow, and you have variation in the skin impedance due to insensible sweating and moisture that builds up in the skin. So it's very difficult to build a robust haptic interface using electrical stimulation. And so there's a lot of work going on in different groups, focus on mechanical, stimulators, and ranging from dielectric elastomers, piezoelectric options, soft pneumatics as a basis of soft robotics, but now adapted for body interface. Again, focused on the fingertips, but we think the fingertips only a small fraction of the kind of haptic interface that you might want to think about into the future. And so this is our first kind of demonstration of a epidermal or skin-like haptic interface beyond the fingertips. And so it mounts on the inner forearm. It has the ability to measure muscle contractions through EMG electromyograms, but it also has these electrotactile stimulators. And so we're using this as an interface to control a robotic arm. And so we have a haptic interface that couples and is responsive to the responsive pressure sensors that are integrated into the end-effector associated with the robot. So it creates sort of ability to modulate pressure during the control process. I'll come back to that in the context of amputees in a little while. So that's kind of a little bit of a background. And so we started to accelerate our efforts in this space maybe 2017 or so. And this is kind of a first attempt at a platform that could do full body engagement at the level of a haptic interface. And so it consists of an array of vibrotactile actuators that can be controlled in a fast, real-time spatiotemporal manner using a backplane of soft electronics as a control system. And the whole thing sort of stacks up like this. And so it's flexible and can kind of conform to the curved textures of the body and move naturally with motions of the limbs, for example. Now, the kind of mechanical actuators you're using here, very primitive, very simple, but they work. And we can produce hundreds of them, which is what we need to do in the lab to build these things at any kind of realistic scale. So it involves just a Lorentz force. We have a neodymium rare earth magnet. We have a copper coil. We can modulate current flow through the coil to create a force on the magnet. It sits on a cantilevered platform of a thin polymer membrane. We can control the shape of this to define the resonant frequency. We define the resonance frequency to align with the highest response of the mechanoreceptors in the skin. It turns out to be about 200 hertz, and you can stack these up and use soft elastomers to create the individual actuators, and you tile them out. You put the backplane of soft electronics on the back of these things, and then you have a control strategy in that way. We're using the same kind of magnetic inductive links that I described for the NICU vital signs monitoring technologies for power delivery wirelessly, so there's no batteries in these systems, and for wireless two-way communication with the device. And so we use RFID tag reader technology for doing that power delivery data communication. We have various ways to increase the range. It's about a half meter or so. So if you're sitting in a chair, it's fine. You put it at the base of the chair. You're sitting in a hospital bed, that would work as well. So I won't go into the details, but it's 13.56 is sort of standard NFC, high frequency RF link, again, for power and for data, that connects a touch screen to the device. And so you stroke your finger across the touch screen, and that creates a corresponding pattern of actuation across these vibrotactile actuators. And so that's the GUI and kind of what it looks like. So what's it good for? A number of different things. I won't go into the details, but you might imagine social media. So, you're interacting with Zoom, you got the audio, the video, it's great. Might be interesting to be able to touch through the skin in a virtual way the person that you're corresponding or interacting with, and we can do that, and we can do that in real time. I'll give you some examples of that in a little bit. All kinds of applications in gaming and entertainment, obviously, but also things that really touch medical care, and I'll focus on this one a little bit in a few slides in terms of sensory substitution. that allows an individual with a robotic prosthetic, for someone who suffered from a lower limb amputation, an ability to sort of feel objects through patterns of haptic engagement at the upper arm. So that's what it was in 2019. Got a lot better. This was just published this week, actually. Much, much thinner, much more highly functional, more dense collections of these actuators at densities actually that exceed the 2-point discrimination threshold for nearly all regions of the body, except for the fingertips, the toes, and certain places on the face. And so these platforms can do full body engagement wherever you want to put them, except for those locations. So the pitch here is about half a centimeter or so. And again, that exceeds the 2-point discrimination threshold for tactile receptors in the vast majority of the body. So you can put these on the back, on the upper arm, the lower arm, pretty much wherever you want. And you have multi-touch, real-time GUI interface for controlling the operation of those actuators. And not just patterns, but you can transmit information associated with pressure. If you have a pressure-sensitive touchscreen, that can be translated into amplitudes of vibrations. You get the spatiotemporal, but you also get the amplitude information as well. Very easy to do that. So one of the postdocs working on this project actually developed sort of a Lego-style way to assemble these actuators into tiled arrays that have anatomically matched shapes. So you basically plug and play, you put these things together, and you can cover very large areas in geometries that sort of match the natural contours of the body. You can embed them in stretchable fabrics as well to facilitate donning and doffing of the devices. That's the way it works. So it's all compatible with Bluetooth, NFC, wireless communication protocols, but you can also pass information through the internet, and you can do this with very low latencies, about 20 milliseconds or so. And so here's an example of a demonstration that shows that. So here you have touchscreen. There's an individual in our Evanston labs. We still have some labs in Urbana from when I was on the faculty there at U of I. So the student in Urbana is wearing one of these epidermal virtual reality systems on his outer forearm. He can't see what's going on in Evanston, but the student in Evanston is going to stroke his finger across this touch screen. That information is going to pass wirelessly through Bluetooth to a computer that's connected wirelessly to the internet. That information gets transmitted, again, through a separate Bluetooth link to the epidermal VR system, and then this individual is going to write on this whiteboard the characters that he's feeling on his outer forearm. And so all this is happening in real time. And so this individual is stroking out the letter V, and you see, this guy is writing out a V on the whiteboard, just as a visual illustration that, it works, I guess is the point. So you might think that this is pretty simple. It's just stroking. You're just defining letters. Can you sort of replicate at some level different forms of engagement between fingers and the skin? So for example, you can map sort of a pinching deformation into a pattern of actuation that looks like this. We have LEDs here just to allow visualization, or squeezing or twisting. And you can imagine many different types of engagements, two pattern stroke, one finger, two finger stroke, one finger stroke, that type of thing. And then you might ask, well, can you tell the difference between all of those different patterns of actuation? It turned out to be pretty simple to do that. This is a truth table, and so we had a number of individuals sort of learn these different sensations, and they were quite good at distinguishing one from the other based on that kind of actuation applied to the inner forearm. So let me give you this specific example of sensory substitution for robotic prosthetic control, because this maybe begins to intersect a little bit more obviously with this community. So the idea here is we have 30 pressure sensors in this robotic hand. And that information from each one of those pressure sensors passes through a Bluetooth link to the tactile haptic array mounted on the upper forearm. And this is an Iraq war veteran who suffered a lower arm amputation. So the control is happening through an EMG interface in this socket that forms the base of the robotic hand. And then he can sort of develop a sense of feel of touch through these sensors as reproduced in vibrotactile form on his upper arm. And so this requires, as you might imagine, a little bit of training process so that he can associate different patterns of pressure on the robotic hand with different patterns of haptic engagement on the upper forearm. But it turns out that that was very easy to do. And this person could learn the system quite quickly. And this is a pattern of a video of him doing that learning. And so now you can imagine you can much better control the robot in a sense. And so here's an example. He's blindfolded, the haptic array is off, and he's being asked to grasp this eggshell without breaking it. As you can imagine, it's almost impossible because he can't see what's going on. He can't feel how tightly the fingers are grasping the egg. And so when he tries to grasp it and pick it up, it's impossible to do that without shattering the egg. However, even when he's blindfolded, when you have the haptic array for sensory substitution turned on, now he can develop a sense of how tightly he's grasping the egg, and he can release the force to allow him to pick up the egg without cracking it. So he can feel when he's contacting, and he can feel the sense of the magnitude of the pressure, and he can keep that pressure below a fracture threshold to pick up the egg. So that's what it looks like. So what else might you do? I mean, you can think of the skin as an information interface that's typically underutilized, I guess, and it might be interesting as a complement to the eyes and the ears as a way to sense the environment. And so here's a simple example. We have a navigation app running on a phone, and now we're passing directional instructions to the haptic array. And so without audio and without looking at the phone, you can move through an environment just by feel. So you can feel different arrows and different symbols being reproduced on your back as a way to help guide yourself through an environment. And so here's an example of 17 different kinds of instructions that can be passed in that way and can be accurately assessed and distinguished as illustrated by results from this truth table. So there's a lot of information content that come through that interface sort of in real time. The other thing you can do is you can pair it in real time with the sensor. So here's the suprasternal notch device. It has that tracks as accelerometer, so you can determine the orientation of the device from the output of those accelerometers. You can transmit that information in real time to this vibrohaptic array to create a sense of body orientation for individuals who are undergoing rehab and need that kind of feedback. And so all this can happen in real time. Bluetooth connectivity from here to here, and you can see different patterns of actuation corresponding to different orientations of that device. Just as another example, exploratory use of this kind of technology. So let me describe kind of wild stuff that may or may not make sense, but here's an example of a haptic representation of music. So you're used to thinking about listening to music, but maybe there's a way to engage your skin to kind of enhance the experience of listening to music. So here's the most trivial way to kind of do that, where we actually have the microphone activated on the phone. It's in real-time computing power spectra by FFT, and then picking out the peaks in that power spectra, determining which notes are being played at any given time, and then sending that information to map the notes that are being sensed to individual vibrohaptic actuators across the array. So it's just a one-to-one mapping between notes and haptic actuators across this array. So this is Flight of the Bumblebee. So this is real time. This is about the highest tempo that you can go with this kind of real time control, but it's pretty good. It's impressive how much computational power you have on the phone. But anyway, this is what's happening. It's sensing the notes. It's actuating the actuator. So maybe that's interesting, maybe not. We decided that maybe a more abstract way to convert the music into a haptic movie might be more appealing. And so I asked my student to create like a video that represents Flight of the Bumblebee, and then create a haptic representation of the motion of that bumblebee, across the array, and you can do that as well. So a little bit more loosely coupled to the music, but you can see the bumblebee floating around, and then there's a corresponding pattern of actuation across the array. So if you're interested in reproducing the sense of a bumblebee crawling across your skin, we have the technology. So it's a real breakthrough in that sense, I guess. But maybe this is more interesting, a little bit more abstraction and different kinds of music converted into different patterns of actuation. Again, trying to create a haptic level of engagement in listening to music. So just kind of exploratory. So that's all I had to say, but I think there are tremendous opportunities for research in these kinds of platforms. The metaverse, I think, is going to accelerate activities in these areas. We're mostly interested in medical applications, but I think there are probably a lot of opportunities in robotic control interfaces as well. But you really need work on everything. So I think it's just baby steps in the direction we hope to go over time. Electronics, electromechanics, I think artificial muscles is something we really need. We don't really have that. Sensors, power supply, skin interfaces, software control, and so on. So with the last 2 minutes that I have, I think I'm 43 minutes in. I wanted to stop by the 50-minute mark. Let me describe a couple of future opportunities. So the kinds of skin engagement that we're thinking about right now are sort of the most simplistic mechanisms that you can imagine. It's just a normal vibratory force being applied to the surface of the skin, but there are all kinds of skin receptors at different depths across the skin responding to different kinds of actuation. So DC, sort of constant forces, shear forces, there are thermal receptors. And so looking into the future, I think you can imagine multimodal operation in these devices. It's not just vibration, but static force, it's shear force, it's thermal actuation, local cooling and heating. And we're kind of working in that direction, sort of leveraging some of the stuff that we're able to do today, trying to improve the functionality of these devices and the level of engagement with the skin. And so with that, let me just give you one quick snapshot of what we're doing in robotics, because I love robotics and really enjoyed the talks this morning. But we're kind of newbies to this field, but we do have some kind of unusual and unique ideas that are maybe interesting for the field of micro robots. And so we can create, using these lithographic techniques that we leverage for these skin interface devices, all kinds of planar multi-material structures that can be buckled up out of the plane to create very tiny robots. And we do that with a stretched elastomer. We mount these planar structures, and through a process of mechanical buckling associated with compressive stresses that follow from releasing that pre-strain, we can create all kinds of very tiny 3D robots. And this is one that we built in the shape of a crab. And you can see the body of the crab here. It's a polymer-based body. We have shape memory alloy here at the joints, and we're using that shape memory alloy in the shape chains induced by thermal mechanisms as a way to drive motion of the legs. And to our knowledge, this is the smallest terrestrial robot, and you can see it move here. So we use a laser-based actuation scheme to coordinate the motion and the gait in these robots. So we're scanning a laser here, actuating these shape memory alloys and causing motions of the legs. And you can do all kinds of other things in 3D using that kind of scheme. This is sort of a jumping kind of like a grasshopper type system. This is real time, actually, 1x. We have a laser scanning in this direction, actuates those legs and causes the robot to jump around. So anyway, we're just dipping our toes into this very exciting field of robotics. Just want to share that with the community here. If you're interested, be happy to speak more in detail. This just appeared a couple weeks ago in Science Robotics. So with that, I think I'm pretty much on time. I'm just going to go ahead and conclude by acknowledging senior collaborators, very collaborative group. We work with many different folks in engineering science. Our core expertise is in material science, but we need computational modeling for the mechanics. We need manufacturing, haptics, and the interface to the clinical community is critical for pretty much everything that we do. But the students and the postdocs are the most important people, so I always like to acknowledge them at the end of my talks. This is the team. It's a holiday dinner party that we had in December. Everybody's masked up. We dropped the mask, took the picture. Everybody masked up again. But anyway, really talented group of kids and coming up with a lot of great ideas, working super hard. And I just talk about this stuff. They do it all. So I want to thank them and thank you for your attention. I'd be happy to answer questions if you have any.
All right, thank you for the amazing talk. We have a few questions. Let's start on the right.
Yes, thank you very much. That was very interesting. I'm particularly interested in the sensors. And one thing I was curious about is how long do they last and how easy is it to replace them?
Yeah, it's a great question. So when we first started on this project, we were deeply engaged with neonatologists at Lurie Children's Hospital. If you take a look at what's done in the NICU, all of the sensors are single use. They throw them away. So they take them off on a 12 or 24-hour cycle, the taped on wired sensors. and they throw them out because the cost structure is such that the risks associated with sterilization and reuse just aren't worth the cost benefit of reusing those sensors. And so they're thrown away. So the devices I described initially were designed with that mode of use in mind. So single use, disposable, throw them away. When we were approached by the Gates Foundation, Save the Children Foundation, we immediately realized that that mode of use is totally incompatible with the economic constraints in Zambia, Kenya, all these other places, these lower and middle income countries. So for those use cases, we had to re-engineer the devices to allow many cycles of use because you need to amortize out of the overall cost structure, the cost of the device, to get to the price points that are sustainable in those countries, which again correspond to a few cents per patient monitoring day. That's the way you think about it. So the devices have to be reused about 1,000 times in order to get there. So they're much more rugged, to allow that kind of reuse. So two different platforms designed for two different use scenarios is maybe part of the answer to your question. But maybe a broader answer, and I'm just going to kind of infer from your question that this is a point of interest for you as well, is how long can the devices stay on? And that's determined not so much by the material science of how they're constructed or the choice of adhesive that we're using to bond them to the skin. It's much more limited by natural biological processes of the skin itself. And so the stratum corneum is the very top surface of the skin. It consists of dead, dry cells that serve as a water barrier to prevent water loss through the base layers of the skin. But that stratum corneum layer, those dead cells are constantly exfoliating, and they arise from a process of differentiation of cells that start in the base of the skin, migrate, differentiate, end up terminating their lives at that stratum corneum layer and then exfoliating. The time scale for that cellular elevator process is about 2 weeks. So if you have a device sitting on your skin, you're preventing that exfoliation. If that's prevented for more than about 2 weeks, now you're sitting on a very unstable layer of cells that itself is not adhered to the underlying living healthy skin. So your devices just tend to slough off, basically, almost like the cells of the stratum corneum itself. It kind of just falls off. So I've worn devices just playing around myself for as long as about 4 weeks. And at that point, the adhesion just wasn't sufficient to keep it on. So it falls off, and then I was rubbing my finger across that area of the skin. It felt very rough at the location where the device was. Take a piece of Scotch tape and you exfoliate that off, you're back to healthy skin. So long answer to your question, but it's really that process that kind of limits the time that the devices can be on the skin.
Great, thank you very much.
A question on the right.
Oh, hi, hi, Professor Rogers. Thanks very much for the talk. It's such a great pleasure to have this chance to hear your talk. So I have 2 questions regarding the wearable device. So firstly, I want to hear your comment about how to calibrate them regarding to the measurement of magnitude. So especially considering that they are highly deformable, and if we were putting them on the surface of human skin or surface of robots, either rigid or the soft robots, there may be large-scale deformation and very high degrees of freedom deformation. How can you get a reliable measurement regarding the magnitude over the time? So the second question is that I wonder whether you have considered about making large-scale measurement units, in the scale of thousands or tens of thousands or even beyond that. In this case, what do you think about how to do the wiring and how to do the signal processing?
Yeah, those are great questions. So the first one has to do with stability of and operation of the sensors under deformations associated with motions. And the second question had to do with scale up, I think, and manufacturing to thousands of units and broader deployments. Is that correct?
Yeah, the second question is specifically about wiring in those cases. So I know fabrication is not a big deal due to the new technology, but the wiring, how can coordinate wires and how to arrange the wires in those cases, if there are some existing technologies or technologies in the near future could be a good solution.
So you're talking about the wiring? How do you manage and route the wiring?
Yeah, exactly.
Yeah, okay. So the first one had to do with stability. And what we can do there is you really only need soft mechanics at the system level. It doesn't, in many cases, doesn't need to be soft throughout the system. at a granular level. So if the sensor is sensitive to strains, and the sensor performance could change as the skin deforms, we just create a rigid island at that location. So we rigidify the sensor region of the device. The rest of the device, though, is still soft and kind of skin compatible. So that's kind of what we can do there. It's a little bit harder to do that with antennas because in some cases they have to consume a larger area than the sensors do. And so there we do a lot of electromagnetic, like multi-physics modeling, where you couple the electromagnetic response to the mechanical response and the strains, and you have to design the antenna to be robust to deformations over a range that's relevant for the particular mounting location. So you have to do that. In many cases, it is doable, but you have to pay deep attention to that. And so that's a very good question. And hopefully that's kind of a practical answer. You know, many details, but roughly those are the two strategies, antennas and sensors. For the wiring, I guess I'm not sure that I fully appreciate the question. You know, we have design tools, circuit design tools just adapted from standard SPICE modeling tools that are used, you know, for conventional electronics to do the layout from the circuit level functionality standpoint. And then with our collaborator, Younggang Huang, we can move the components around, change the lengths and the geometries of the interconnects such that when those circuit components and interconnects are embedded in a soft elastomer, we get the effective mechanical modulus that we're interested in. So that is not fully automated. So it's a combined level of intuition and getting things at a reasonable starting point, and then iterative cycles of running the mechanics modeling, looking for any stress concentrations that develop on the basis of different types of mechanical deformations, and then adjusting the topology to eliminate those areas of concentration. So I guess in the future you could imagine it being fully automated, but that's not the way that it's done from a practical standpoint at this point. So maybe we do intuitive design that makes sense, and then we'll go through maybe a couple dozen iterations to minimize and smooth out any of the concentrations, tweaking the layouts from that standpoint. I don't know if that answered your question.
Yeah, thanks very much.
So we have a question up there in the dark on the balcony.
Thanks for your talk. I have a question about the haptic feedback. So on the forearm, it's a lot easier to distinguish two signals, even if they're really close together, as opposed to on the back, the signals have to be more separated in order to distinguish. So I'm wondering if you've done any experiments on kind of scaling up the size of the sensor or having to separate those signals more depending on where you're placing the haptic feedback.
Yeah, great question. So I didn't spend enough time on this slide probably, but along this axis is what you're getting at. This is the 2-point discrimination threshold. So you have two filaments and you push them on the surface of the skin and you ask an individual, does it feel like 1 or 2? And then you continue to increase the separation until they say 2. And that defines the 2-point, but look at the distance scales here. This is 3 centimeters, 4 centimeters. If you look at the calf, the 2-point discrimination threshold is nearly 5 centimeters. You look at the finger, like the upper lip, the fingertips here, it's more like 5 millimeters. So it's like a factor of 10 different, but depending on where you are. But if you have a haptic array that exceeds the 2-point discrimination threshold, it's fine. Right? You wouldn't in those instances need to independently control every actuator. You can control clusters of actuators, I guess. And so our thought is you don't need to tailor the density and the pitch of the actuator array to the specific body location. You just have to know that you're oversampling the density of tactile receptors in the skin, and then you're fine. And so that's what we've done here. This array has a density that oversamples everything except, as I mentioned, like the fingers, maybe the upper lip, maybe the toes, something like that.
Okay, great, thanks.
Yeah. We have actually a line of people up in the darkness of the balcony.
Hi, I have another kind of haptics vibrotactile question. So as far as the longer term applications such as like for prosthetics or in terms of controlling robotic manipulators. Have you found that doing or having long-lasting vibrations has you found that impacted anything such as phantom vibrations, or how have you overcome those sort of issues for those longer-term applications?
Great question. I don't know the answer. It's a good question. I wouldn't expect that. We haven't, of all the human subjects and myself, I've worn these devices. I haven't experienced anything like that, but it may be dependent on the individual, depending on where the device is located, how long it's been operating, things like that. I think it's a great question. We just haven't explored those limits because we haven't noticed like a problem. It could be. I mean, there could be a problem, but we haven't seen it.
Thank you.
Yeah.
All right, let's take one more question down at the front.
Hello, thank you very much for the talk. I know you said that the cost was relatively low pertaining to the medical field in terms of these haptic wearable devices. Kind of what are the main barriers of taking them from a medical situation and bringing them to a broader consumer market? Like what are the biggest remaining barriers, I guess?
Just like financing, commercial, business-related things, I don't think there's a significant technical challenge that needs to be solved there. So we have a small company, Cybel Health, is doing all the deployments on ICs. They have a deal with Anthem, as there's the second largest medical insurer in the US for home deployments, mostly around sleep apneas. They also have a partnership with Draeger, which supplies hospital equipment. They have a deal with GE. So I think a lot of this stuff is going to be happening, which for me is pretty exciting. But I think the other consequence is now you have a platform that sort of works. It reproduces ICU-grade data streams that physicians are familiar with. Now you can think about novel sensing modalities and expanding the breadth of measurements that you're making. And so I think a lot of those developments, other companies working in this direction as well. And we're not totally unique. I think our approaches are unique, but others are thinking about it. But if you think about synergies around big data and machine learning and advances in that field of science, I think there's going to be tremendous alignment, big health data and machine learning. So I think that's likely where things are going to go in the future. But I don't think there's any fundamental like manufacturing challenge or cost challenge. It's just like a deployment challenge, regulatory challenge, adoption, that kind of stuff.
Thank you very much.
All right, let's thank John again for his wonderful talk. So now we have a break for lunch. Let's reconvene at 2 p.m. it's going to be a set of long talks, and our chair is Henny Edmoni, who you saw yesterday.
Hi, everyone. Welcome back from lunch. You're in for a really great session of 4 long talks. Our first talk will be by Bao Wen, and it's titled, You Only Demonstrate Once, Category Level Manipulation from Single Visual Demonstration.
Okay, hello everyone. I'm Bowen. I'm glad to present our paper, You Only Demonstrate Once, Category Level Manipulation from Single Visual Demonstration. This is a joint work with Wen Zhaolian, Kostas Bakris, and Stefan Shaw, while I was doing the internship with Intrinsic, formerly known as Google X. So as humans, we're able to watch the demonstration once and immediately generalize the task to various instances. We are interested in answering this question in this work. Can we teach the robot similar to human-to-human apprenticeship? That is, category-level manipulation from single visual demonstration. To do so, there are multiple challenges. First, we need to generalize with high data efficiency. When only one demonstration is given, we need to generalize to various instances, backgrounds, and configurations. We also consider multiple challenging tasks in this work. For example, the video shown on the right, for the battery assembly, there could be large dynamics due to the rich context, a lot of dynamic uncertainties. Also, for the gear insertion, it requires high precision. And also, for the battery assembly, the critical sequential action is required to put the battery into the, beside the spring. For the related work, KPAM achieved promising results on category-level manipulation. It uses key points representations. Another related topic is visual imitation learning, which is the representative work GTI is able to learn long horizon rearrangement manipulation and can generalize to new tasks on the same set of objects. However, both of them have some limitations that prevent them to achieve the intelligence level of human-to-human apprenticeship. In contrast, we overcome some of the limitations. So, for example, we reduce the demonstration to only 1. Also, we tackle some of the very challenging tasks that involves dynamic uncertainties and high precision. We also remove the requirement of human annotation of the key points. To clarify more about our problem, during the training phase, we assume access to the object CAD models in the same category. We are also given 1 demonstration RGBD video. During the testing phase, our goal is to execute the task on the novel unseen object instance in the same category. We formalize this problem as category-level behavior cloning. That is, we first extract the trajectory from the single visual demonstration, and then we generalize this trajectory to the novel unknown instances to follow. Here's our approach overview. It can be divided into 3 parts. First, offline NUNOX learning learns a category-level representation. The NUNOX is an abbreviation of non-uniform normalized object coordinate space. It learns how to associate different instances in the same canonical space of a category. The second is the demonstration video parsing. We use a 60-pose tracker, which doesn't require an instance or category-level models to extract the motions from the single visual demonstration. And then we convert this trajectory into a category-level canonical space using the NUNOX representation. And during the online testing stage, our goal is to take the object and closely follow the trajectory using closed-loop feedback from the visual tracker. Let's first take a look at the offline NUNOX learning. We use a neural network to learn this representation. Our goal is to associate between the training instances with the novel unseen instance. During the training stage, we put the training instances into the simulation and generate large-scale synthetic training data with domain randomizations. The network is only trained on the synthetic data, and later will be directly applied to the real world for the novel unseen instance. Let's take a closer look about the NUNOX net. It takes as input the partially scanned point cloud and predict the per-point canonical location. During the training stage, the supervision is the cross-entropy loss over the discretized coordinate space between the canonical point cloud against the ground truth from simulation. During the testing stage, given the predicted point cloud in the canonical space, we can compute two byproducts. First, we can get the 90 poles, and second, we can get the dense correspondence between different instances within a category. Once we have the 90 poles and dense correspondence, we are getting prepared to transfer the trajectory from one instance to another. We just talked about offline Nunox learning. Now let's take a look at how do we transfer the trajectory to a novel on-scene instance. Here we show the comparison of using different methods to transfer from the demonstration trajectory to the novel on-scene instance. Nunox only will simply align based on your object centers. KPAM 2.0 will align based on the human annotated key points and their orientations. Our method combines Nunox learning with dynamic attention that allows to dynamically change the anchoring coordinate frame. And as the battery travels along the trajectory, we can see that at the later stage of the trajectory, it is able to attend to both the spring and the bottom plate to avoid collision. And note that this process is fully automatic, just using the demonstration without any human annotation. But how do we get this attention heat map? During the demonstration, we know the complete shapes of the training objects under the receptacle. So we are able to get an implicit sign distance field of the receptacle and then look up the sign distance values of the objects. Intuitively, the nearest group of points and the contact points are the most task relevant. So we can derive a heat map based on their sign distance values. During the testing stage, however, we no longer have the shapes because they are novel on-scene instance. So we cannot directly repeat this process. Instead, we choose to transfer the heat map using the dense correspondence obtained with Nunox. We just talked about transferring the trajectory. Now let's take a look at the tracker. Because we want to apply the tracker to the novel on-scene instance, we adopted our previous method, bundle track, which does not rely on instance or category level 3D models. The tracker is used for two purposes. During the offline, we parse the video demonstration and extract the motions. And during the online execution, the visual tracker will provide visual feedback for the closed loop control. We conducted experiments over two categories, the gears and the batteries. Note that the testing splits are the real products purchased from the retailers to resemble the real-world scenario. We also consider three tasks, the battery standing task, battery assembly task, and the gear assembly task. Here shows one qualitative example on the battery assembly task. On the corner of the videos, we show the visualization of the tracker and the Nunox color embedding, which indicates the dense correspondence between the two different batteries. We first extract motions using the tracker from the single demonstration, and then transfer to the novel unknown instance to follow. Note that this is a very challenging task, because the intermediate action also matters. If you only provide the goal specification, it is not possible to achieve this task. Also, at different timestamps, very specific orientations and positions of the battery is desired. However, thanks to the imitation, where the robot is able to quickly learn this complicated manipulation skill. What's even better is that the robot is also able to generalize this complicated skill to various on-scene batteries. All the batteries have not been seen during the training, and these are zero-shot transfer from the same canonical trajectory. Sorry, it gets freeze. Sorry about that. Okay, to continue, here's another example on the gear insertion task where the high precision is desired. Here, the video shows the 0.1 millimeter tolerance between the gear and the shaft. Again, we are able to achieve this task by transferring the trajectory. Here's more examples on different gears. And again, they are all zero-shot transfer to the novel on-scene gears. And they are all transferred from the same canonical trajectory using the single visual demonstration. We conducted comparison methods with different baseline methods, including KPAM 2.0, and DON. And the point is that we are only the one that trains on the synthetic data, and also we remove the requirement of human annotation. Here's a task success rate comparison over the baseline methods. In total, we conducted over 1,500 experimental trials. For the gear insertion task, we conducted 3 different levels to investigate the boundary of each method. And notably, we are able to outperform the baseline methods by a large margin. For the very tight tolerance region in the gear insertion and battery assembly, the original baseline method is not able to succeed. And also for the commonly considered pick and place tasks, such as the battery standing, we're able to easily achieve 100% reliably. Here, next I will introduce more additional study. Due to the closed loop, our system is robust against external disturbance. Here, even if I'm dragging the gear and change the gear's in-hand pose, the robot is able to know this and adjust to it, which still results in a success. Previously, we have shown the naive top-down strategy for the gear insertion. There's another smarter strategy that is anchor and pivot. However, while it reduces the expectation on the precision, it introduces more complex intermediate actions. Again, thanks to the imitation, the robot is able to learn this complicated skill and generalize to different instances. We also have limitations and failure modes. On the left, one common failure is that when the robot is doing the anchor and pivot, due to the rich context, the gear's pose changed significantly, and the robot arm wants to lift more to adjust, but due to the joint limits, it's not able to continue. On the right, due to the strong spring force, the battery is ejected, and this is because we don't have the tactile to detect this beforehand. In the future, it will be more interesting to integrate with in-hand manipulation and tactile sensing. To summarize, we propose the category-level manipulation from single visual demonstration framework. By just using one demonstration, we are able to generalize to various instances, backgrounds, configurations, and external disturbances. It is also robust due to the closed loop, and this only requires training in the simulation. Finally, we unlock some challenging manipulation skill, such as gear insertion and battery assembly, where the original baseline method can only achieve 0 success rate. Thank you for your attention, and welcome to my poster session.
Very cool work. Do we have questions? I see a question over there.
Connect. Okay, hello, thanks for the fantastic presentation. I wonder what are the assumptions that we make for different objects to be in the same category? And also, given a new category of objects, how should the Nunox coordinate frame be decided?
So for the first question, let me repeat. Your question is, how do we identify different objects within a category?
Yeah, or like, let's say given a bunch of different screws or different new parts, what are the rule of thumb that we should decide whether they belong to the same category or different categories?
Yeah, for this we follow the definition of previous work such as KPAM and KPAM 2.0. That is the objects that's under the same name and they are used for same task purpose. They have the same geometry structure in the general. And so we follow that definition. And I agree that there is so far not a way to, a metric to quantify, quantitatively quantify this the similarity between the different instances, which maybe require some common sense. And I believe that will be very interesting work to quantify how do we measure the similarity of different objects within a category.
Thanks. Also, let's say given new category, does the specific definition of the Nunox matter? Or like it actually doesn't matter and the attention module will take care of it?
Yeah, here the Nunox is a canonical space because here we are working on the industrial objects such as the batteries and the gears. When they are designed, when they are CAD designed, they are following the same industrial standard. For example, the gears are, the z-axis are always perpendicular to their plane. And when we can directly, then we can directly process over these CAD models during the training. And the Nunox is just their canonical space.
Is this assumption about which axis is the gear like actually is used for the algorithm, or it is learned automatically?
The canonical spaces can be arbitrarily defined. That depends on your category. For example, for the gears, the canonical space maybe makes more sense to make the z-axis perpendicular to the plane, or you can use XY axis. For the objects such as the bottles, you can also use the axis or the cups. So you can, the bottom line is that all the instances you have to follow the same canonical definition.
Okay, thank you so much. Sorry about taking so much time.
No problem.
Yeah, great talk. I have a related question to the last one. So how do you decide what parts of the object to align to each other? So if you have like objects of different lengths, should you align the tops or the bottoms, or how do you decide?
Yeah. Maybe let me go back to the slide. Yeah, so this is exactly the problem we are considering. So for example, when there are two batteries and one is longer, one is shorter, to finish the task, the battery has to first press the spring on one end. If you are simply using the Nunox, that will only basically very simply align based on their centers. So the longer battery may first may just collide with the spring because it will not figure out first the contact of the spring. But in our case, because we are using the attention heat map, we compute the attention heat map and then align the different shapes using the local parts. Because the one limitation of 6D pose is that the coordinate frame is fixed and it's not very flexible to different local parts on the objects.
Great.
Let's take one last question as we switch speakers. Go ahead.
Yeah, great talk. Quick question to clarify. You said in your future work, in-hand manipulation, would that also involve making and breaking contact, even with just an antipodal gripper?
Sorry, your question is, would it be helpful to consider contacts?
Yeah, well, actually, I just wonder what you mean by in-hand manipulation.
Oh, yeah. So for example, on the left side, because the gears pose, the orientation also changed in hand. So the tracker notifies the robot that it needs to lift the arm more to adjust. But because this is a rigid parallel gripper, you can only, the kinematic chain between the object and the arm is, and the end-effector is fixed. So you can only change the arm to reorient. But that will like lift a large angle on the arm. But instead, if you have a dexterous hand, you can just do in-hand orientation to very easily reorient, just like human hand. I don't need to adjust my whole arm. I just need to adjust my fingers.
Gotcha. Awesome. Thank you.
Let's thank our speakers. Our next speaker is Gianluca Monacci, and he is going to present a paper called DIPCAN, Distilling Privileged Information for Crowd-Aware Navigation.
Thank you. So this is a joint work with my colleagues Michel Aractingi and Tommy Silander from Naval Labs Europe in France. And, the main motivation for this work is to enable robots to navigate in dynamic crowds to deliver services to humans. And as you see here in this picture, some of these robots already exist and operate services, like in our headquarters in Seoul, but that's not a scene that you see very often, actually. And there are a number of reasons for that, but one of the reasons is that indeed the algorithms that are used these days are still falling a little bit short to achieve these tasks. So traditional approaches decouple, let's say, people motion prediction, from robot motion planning, and this leads to well-known undesired behaviors, for example, reciprocal dance phenomena or the freezing robot problem. More recently, there has been developed methods that are based on deep learning that jointly predict crowd motion and plan robot actions. However, these methods assume to have a view like this one on the right, where you have precise tracking of pedestrians in simulated scenes. And as we all know, to have this information accurately on a robot platform is very hard. You either need some expensive wide field of view leader and complex and brittle tracking algorithms, and potentially you are still not there. So the intuition behind this work is to actually, let's say, it's to observe that we probably do not need to track precisely pedestrians. That's not how we do that, actually, how has human navigate through a crowd. And these introduces, as we said, a lot of complexity in terms of computation and hardware requirements. And also it might be suboptimal in the sense of the system perspective, because you might have estimation errors in these algorithms that propagate to downstream tasks in ways that are unknown. So the key idea here is to learn a low-dimensional embedding that models these crowd dynamics and contains only the information that is needed for the policy that controls the robot. This is potentially a simpler problem, and we hope to introduce some robustness at invariance through this dimensionality reduction. So how we go to do that? We propose a two-step approach where we first learn to project some privileged pedestrian motion information that is available in a simulation to this low-dimensional embedding that is then used by a policy that is trained jointly with this projection. And then in the second step, we learn to reconstruct this embedding space from non-privileged information, image data in this case. Now, to ground this in a concrete problem, as I said, we are going to look at the point-goal navigation task in a crowded environment where we used a differential drive locobot to achieve that has embedded RGBD sensing and can sense its odometry. And we are also going to be equipped with a simulator, a pi-bullet-based iGibson simulation environment in this case, where we can procedurally generate scenes with all sorts of moving pedestrians with different characteristics. And we randomize all these characteristics that include the different type of motion, static, pseudo-random, or ORCA for optimal reciprocal collision avoidance, the level of cooperation of the pedestrians with the robot, how many pedestrians are static or moving, and so on. So this is an example of what this simulator looks like. So to come back to the core of the method, the first step is that we want to learn using this privileged information in simulation. So we have non-privileged information like odometry available both here and to the robot, but we also have privileged information, exact pedestrian position at every point in time. And what we want to do is that we use these information to jointly train a policy and an encoder using reinforcement learning. Now, we do that using PPO and the curriculum on the pedestrian density. And it's important to notice here that indeed this encoder only models the low-dimensional vector Z that is useful to the policy, since they are jointly trained. Now, in the second step, we also extract some we freeze the network that you trained before, and then we also extract non-privileged information. For example, here, history of depth images. And then, since we are in simulation, we train an adaptation network that model these embedding ZT using supervised learning. We have both of these informations. Now, the interesting part that I would like to underline here is that this design is modular, so you can have different adaptation networks for existing policy and encoder combinations. And here in this work, we developed two variants, one which we call DeepCAN-D, based on depth images, and one which we call the DeepCAN-Y, based on YOLO people detections. And just to mention a small trick here, we use modalities that have a smaller simulation to real gap compared to raw RGB to hope to transfer better to a real robot. And then at deployment, we can just use the policy and the adaptation network that you just trained and only exploit non-privileged information, images and odometry in this case. Now, how does this work? Here I have an example in a simulation with about 30 pedestrians. Sorry, the robot is here at the bottom. I don't know if you see it well. It's a bit dark. And you see that it learns some interesting behavior where it nudges his way through this crowd and pushes it a bit and comes back a little bit and manages to get to the goal, which is the red cylinder at the end. This is a quite challenging scenario to achieve with this narrow field of view camera, of course. Here, just a few more examples in settings where you have static crowds on the left, randomly moving crowds that do not perceive the robot, in fact, so they are not cooperating to the robot and could stumble into it. And on the right, again, these ORCA policies. And here a simple example with a real robot. So here the crowd is still quite dense. It's a much smaller room. And you see that the robot still manages to get to the goal, which is this red cross down here. Now, the interesting thing about this video, which is maybe not so impressive, is that is using the exact same policy that we have just trained. There is absolutely no adaptation, it's just transferred to the robot. And I think this shows nicely the robustness of the method with this dimensionality reduction through the embedding space. A couple of slides about quantitative results. So we compare to a number of baselines. One is, let's say, an oracle, which we call DeepCAN-P, because it uses privileged information. This is an architecture that is comparable with the deep learning-based methods that I mentioned in the first slide, where we assume exact pedestrian position available. The second one is our beloved dynamic window approach that I think most people working on robot navigation know. And then we have two learned methods, what I call here ReckonD, which basically uses the architecture trained in the first, let's say, learning step with privileged information, and then in the second learning step, instead of learning the embedding, it just, let's say, it simply learns to reconstruct the privileged information from non-privileged information. So it uses depth or people detection to try to reconstruct the exact position of people at every moment in time. And the last one is, I would say, a prototypical end-to-end approach, which is trained in one pass, which has the same structure of the our proposed architecture, but is trained just in one pass using non-privileged information. And the results, here it's quite of a big table. I will just go through the lines briefly. It compares these methods on scenarios with an average of 10, 20, and 30 pedestrians, and on scores such as success rate, the success rate weighted by time length, the personal space compliance, how much the robot doesn't bother people or doesn't go too close to people, let's say, and the collision rate. And what I want to highlight here is that our proposed method it has strong performances across the board and has very limited degradation with respect to the oracle policy. Interestingly, we see some properties of the algorithms that we might expect actually from their design. So DWA is very careful. It doesn't collide a lot with people, but it often freezes, especially in complex scenarios, here on the right. ReckonD that tries to reconstruct the privileged information from the privileged one has significant inferior performance to DeepCAN, and it also has a high collision rate. And we might speculate that this is because of these estimation errors that he encounters. And finally, the end-to-end method performs a little bit better, but still significantly worse than DeepCAN. So to conclude, I have presented a new model to bridge the gap between this crowd trajectory prediction and robot control, and we have achieved, I think, encouraging results in simulation and in the robot platform. And in terms of perspectives, as you might have noticed, we don't have obstacles, static obstacles and rooms layout. So we are working to integrate this model into a kind of mixture of expert kind of approach where we include a planner when we couple with the planner, and then we want to test this in real service robots. This is a picture that I took last month in our headquarters in Seoul, where a bunch of these robots, about 50, are already delivering coffee from a well-known American brand to our employees. And for the moment, there is not a lot of people because of COVID still, but I think there will be large crowds and there will be a nice test bed to test this algorithm. And with these, I conclude. I welcome you to come to my poster. You have to climb up to the second or third floor, I guess, to see me, or check the website for more videos and material, or contact me. Thanks.
Oh, all right. Thank you very much. Do we have questions for our speaker?
Thank you for great work. I have one question. As the policy was trained with model-free reinforcement learning with function approximation, wasn't there any limitation of the policy limited to a reactive policy rather than long horizon planning? Like, for example, when people plan for a long horizon to avoid like dynamic obstacles coming toward them, like these things.
I'm not sure I understood everything. You were asking if the policy is purely reactive or if it's trying to predict. I'm not sure I understood the question.
Yeah, I think that's what I want to say.
Yeah, so the one that, the policy that we learn in the encoder, it uses one of these trajectory prediction models that is being developed recently in the literature. And so it has a component of prediction in terms of what's going to happen. Then I think altogether, when looking at the behavior, it looks a little bit like a balance. It's trying to understand through its action what is going to happen around it, around the robot, and is trying a little bit to predict and a little bit to react. We have the impression it's a little bit of a combination of it. We did some probing experiments that are not really in the paper, where we can see that this embedding vector represents, is able to predict better than other types of representations the future position of the robots, of the nearby pedestrians. So there is some of this information in that embedding. Then, yeah, with these reinforcement learning methods, it's not always completely obvious to interpret exactly what is used and what is not.
Okay, thank you.
Great.
Thanks.
Sure, go ahead.
Yeah, very interesting work. I'm wondering if you compared to simpler methods that don't necessarily use learning, like just an MPC method that samples trajectories at every time step and picks the best.
So we compared with DWA, which is to some extent, let's say, which is related. So with the dynamic window approach, I guess you are familiar with it. So you sample, you predict a number of feasible points in the dynamic window of the, according to what is your current state, and then it predicts a number of possible trajectories and picks the one that minimizes the chance to collide and gets you closer to the goal. So that would be, let's say, the comparison that we did with in terms of non-learning based approaches. This is the standard. DWAs, for example, is the standard local policy for the ROS navigation stack. So.
Right. Yeah, the reason I ask is I'm wondering, in an environment with people that are moving so randomly or chaotically, I wonder how useful it is to actually think so hard about where the people are versus just wait for them to get out of the way.
Yeah, I agree. Yeah, I mean, that's also the whole reason why we didn't want to predict the position of people, indeed. I don't think it makes a whole lot of sense to exactly predict the position of people. You want to get a rough understanding of what is the situation in front of you and how dynamic it is and how these people are roughly moving to take an informed decision without having to exactly think too hard about where they exactly are, indeed. So I think, I agree with you. I think it's not really necessary to think so hard about where these people are and they are going, but you would still want to have an indication to make an informed decision of where you would like to go, and that's what we hope and we think we are capturing with this embedding.
Thank you.
Thank you for your talk, really interesting work, and thank you especially for showing an actual robot going through a dense crowd of pedestrians. One of the questions I have, so like, when I see work like this, I immediately think of that little mouse robot from Star Wars that's weaving through the crowd. And one of the things that we've encountered in our own work in moving through dense crowds is this problem where the robot has to stop, right? Because its predictive model has presumably been incorrect about something. And that can limit which kinds of robots you can apply this work to, potentially, right? And so first question is, have you thought about applying this to something like a Ackerman steering vehicle where if you just stop, you might get yourself into a situation you can't easily get out of?
No, not really.
and so, the sort of follow-up with this is, why do you think the model was incorrect in some of these cases where the robot did get stuck? And what can we do to improve upon that?
So when the robot got stuck is, of course, when the crowd is very dense. In our case, it is very patient at trying to push, for example, people around to see if they are cooperative, or it can backtrack and try to backtrack, and then it's also where you get collisions. In fact, that I didn't show here, so that's where you have the failure case. I think the best option in those cases, and this is some of the heuristics that we use in the real services, is to start to, you stop, essentially. That's the easiest when you really are, it can become dangerous to try to push or backtrack too much, and that's what we do, is that we stop, in fact, in the real robot. Thanks.
Thank you. I'm sorry, Ruben. I have to cut us off. Thank you so much. Let's thank our speaker again.
Thank you.
Our third speaker is Alex Ocean, who will be presenting a talk entitled Parameterized Differential Dynamic Programming.
Hi, everyone. My name is Alex Ocean. I'm a PhD student at Georgia Tech and also a part-time research engineer at NASA Langley Research Center, and I'm excited to share with you our work on parameterized differential dynamic programming. And so our team is really excited about this emerging sector of aviation known as urban air mobility, or UAM. And these UAM vehicles are unique in that they exhibit 3 distinct phases of flight. They have vertical takeoff and landing capabilities. They can fly like a more traditional fixed-wing aircraft, and there's a transition phase between the two. And so UAM is projected to be up to a $28.3 billion industry by 2030, and it has the capacity to revolutionize transportation in cities through the use of air taxis, efficient robotic cargo transportation, and more. To achieve scalability, we need to be able to fly these vehicles autonomously, but this presents numerous challenges for a potential path planning algorithm. And so some of these initial challenges include, we'd like our planner to have some principal guarantees on the trajectories that it generates. We need these trajectories to be very accurate to the dynamics. Our planner should be able to account for any epistemic uncertainty in our model. It needs to be able to handle this multimodality aspect of UAM vehicles. And it should be generalizable to different vehicles, which may have vastly different dynamics. And so there are, of course, many existing path planning algorithms out there, but we choose to focus on one in particular due to its nice properties. And that's differential dynamic programming, or DDP. And so DDP starts with a trajectory. It performs a backward pass to calculate the optimal controls, U star, and then performs a forward pass using the new controls to generate a new trajectory, and the process is repeated. And so one of the nice properties of DDP is that it converges quadratically to a minimum, meaning that after just a few iterations, we can find a low-cost solution. Furthermore, this forward pass process uses the full nonlinear dynamics to integrate the state forward, meaning that any trajectory that DDP generates is accurate to what the vehicle can feasibly perform. And while past extensions of DDP explicitly address stochasticity, parametric uncertainty, non-parametric uncertainty, and more, these methods are either not generalizable, they may require very problem-specific parameters, or they require some offline learning component. And so in this work, we're proposing a method that has a general parameterization that naturally generalizes to different tasks and systems. It co-optimizes for the controls and the parameters simultaneously. And it's able to handle this multimodality aspect of UAM vehicles. And so our algorithm is a generalization of DDP. DDP solves a standard optimal control problem using dynamic programming and a second-order approximation to derive an efficient algorithm for calculating the optimal controls. Our method, which we titled Parameterized Differential Dynamic Programming, or PDDP, starts by parameterizing the optimal control problem with this vector of parameters theta that's highlighted in red here. And so the role of theta is task dependent. And much like standard DDP, we'll use dynamic programming and a second order approximation to not only calculate the optimal controls U star, but also to calculate the optimal parameters theta star. And so for dynamic programming, we use the value function, which is now parameterized by theta, but we're still able to adopt a nice recursive structure to the problem, which you see here. Combining this with the second order approximation allows us to derive a set of backwards pass equations. And these equations, when you solve them backwards in time, They give you a quadratic approximation of your value function along your trajectory. And so highlighted in red are the additional terms that PDDP needs to compute compared to standard DDP. Using these backwards pass equations, we can derive an optimal control update and an optimal parameter update. And proposition 1 in our paper shows that this optimal parameter update is actually a Newton's method step for minimizing the value function at the initial time, so at the starting point of your trajectory. Finally, we can apply these updates iteratively in an algorithm until convergence. And theorem 1 of our paper shows that the convergence is independent of your initialization of your controls or parameters. So no matter where you start, you're guaranteed to find a minimum. And so this general parameterization not only allows PDDP to solve standard optimal control tasks, but it enables the solving adaptive control and time optimal control tasks. It allows for optimization of multimodal systems, including UAM vehicles. And in terms of future directions, we see PDDP being applicable to model-based reinforcement learning, inverse optimal control, and more. But this work specifically will focus on adaptive control and time optimal control for multimodal systems. And so 2 applications that we present are on adaptive model predictive control, or adaptive MPC, and switching time optimization. For adaptive MPC, we use a combined cost function where minimizing the first term solves a moving horizon estimation problem that maximizes the likelihood of your previously observed states. Minimizing the second term solves a model predictive control task that allows us to plan a future trajectory. And so we test our method on 3 systems of increasing complexity: a cart pole, quadrotor, and an ant quadruped. Starting with the cart pole, here you see our adaptive MPC algorithm using PDDP to estimate the pole mass of the cart pole while simultaneously bringing it to the upright position. And in just under 50 steps of our algorithm, we're able to converge to the true pole mass while simultaneously solving the problem. Likewise, on the right here, you see the quadrotor. And we apply our adaptive MPC algorithm to estimate not just the mass of the quadrotor, but also the diagonal inertia components, while simultaneously attempting to reach the target state denoted by the red dot. And so in just a few iterations of our algorithm, we're able to converge to the true model parameters. Finally, we use the ant as a sort of demonstrative comparison of our algorithm. So on the left here, you see DDP planning a trajectory using a model that doesn't match reality. So the leg lengths are very long. If we were to apply this planned trajectory on the true model, it would result in failure, where the ant is about to tip over. But if we use our adaptive MPC algorithm with PDDP, we're able to successfully estimate the true leg lengths of the system while simultaneously driving the ant forward using this jumping gait. And remarkably, in just 2 optimization steps, we're able to converge to the true model parameters. So those were some results on adaptive MPC. Now we'll move on to switching time optimization, where we'll consider a multimodal system where the dynamics pass through n modes. We'll augment it into this switching time system through a discretization and an introduction of this parameter theta I that determines the terminal time of each of your modes. And so once again, we test on 3 systems: a cart pole, quadrotor, and NASA lift plus cruise vehicle. So starting with the quadrotor on the left here, you can see a converged solution found by PDDP, where the modes are determined by the target state. So the first mode of the dynamics actually has a target state on the left with an x position of -5 and the pole in the upright position. And the second mode has a target state on the right with an x position of 5 and the pole in the upright position. And so you can see that PDDP has found a time optimal control to reach these 2 targets sequentially. On the right here, you see a similar setup for the quad rotor, where our goal is to reach a first target state and then a second target state. And because we've explicitly introduced the terminal time of each mode as an optimization parameter, this avoids the need to manually tune the time horizon of our problem. Finally, we'll present a result on the NASA Lift Plus Cruise UAM vehicle. And so the goal here is to perform a vertical takeoff to 200 feet and then transition into forward flight. So note that the transition point wasn't manually specified. It was found by our algorithm. So I'll replay it. So we can successfully reach the target altitude before transitioning into forward flight, which is invaluable for flying these vehicles in cities. And so, in conclusion, our algorithm, PDDP, is a second-order algorithm derived by extending classical optimal control. It has principal convergence guarantees. It co-optimizes for the controls and parameters simultaneously. It generalizes to multiple tasks. And it enables time-optimal trajectory planning for multimodal systems, including UAM vehicles. So thank you for your time. Visit our poster session today at 4 p.m.
Questions for our speaker? Go ahead.
Thanks for the talk. I was wondering, with the adaptive MPC experiment, you have this combined estimation and optimal control problem. How do you stop it being kind of optimistic about the parameters, like choosing parameters that would make your problem easier?
Yeah, that's a good question. So the moving horizon estimation portion is only over past states that we've already seen.
Yeah, but for example, you might want to, as in if your dynamics are a function of the parameters, for example, you might, or are you not using gradients of the parameters with respect to the...
Yeah, I think I understand what you mean. So the planning portion doesn't incorporate the parameters in the cost.
Okay.
Does that make sense?
So you wouldn't use any gradients for...
Yeah, exactly.
Okay, all right. Thank you.
Yeah, no problem.
Hi, thanks for the great work. So I'm curious as to if there are any conditions on the observability of the parameters in order for your method to actually converge.
Assumptions on what? Sorry.
On the observability of the parameters theta over time.
I'm not sure exactly what you mean by exertability.
Observability.
Oh, sorry, observability.
Yeah.
Yeah, so the parameters actually don't have to be observable at all. So for instance, in that scenario where we're estimating the pole mass or the inertia components of the quad rotor, we don't observe any of these parameters. We only observe a set of states, and then we're able to estimate what the parameters should be given what states we've seen. Does that make sense?
Sure, thanks.
Yeah.
All right, let's thank our speaker one more time. Our final speaker of this session is Weizhi Chen, and he will be presenting a paper titled AK, Attentive Kernel for Information Gathering.
Thanks for the introduction. Hi, my name is Weizhi Chen. We present AK, Attentive Kernel for Information Gathering. This is a joint work with Ronnie Carden and Lantao Liu. So why do we care about robotic information gathering? Robots collect mapping information to navigate in unknown environments. Robot arms actively localize the object for contact-rich manipulation. Dynamics information of the physical robot helps sim-to-real transfer. In these applications, information gathering is a necessary auxiliary task. In some other scenarios, information gathering itself is the main goal of the task. For example, 3D reconstruction, elevation mapping, environmental monitoring. In this work, we focus more on the active learning or sensing problems, but our approach can also be applied to the first category. So what is robotic information gathering? This is a system diagram showing how it works. The robot perceives the environment and uses the collected data to build the probabilistic model that not only gives us the prediction of the environment, but also the uncertainty of its prediction. The uncertainty can be used to calculate the objective function for the downstream planner that guides the robot to collect the next batch of valuable data for building an accurate model. Many existing work in robotic information gathering focus on developing planners. In this work, we would like to emphasize that the probabilistic model is also very important, especially the uncertainty quantification aspect. Many existing work use Gaussian process regression as the probabilistic model. Gaussian process regression gives us the prediction and uncertainty based on the correlation among data points. The correlation between two data points, x and x prime, is characterized by the kernel function k, which is further controlled by a hyperparameter length scale, here denoted by L. We will visualize the L at the upper right corner and give the digital representation of length scale at the lower right. Intuitively, a small length scale gives us a weakly function, while a large length scale gives us a smooth function. Commonly used kernels like the RBF kernel we've seen in the previous slides are stationary kernels. Stationary kernels are not good enough. There are two problems. First, stationary kernel has only one single global length scale parameter that controls the variability of the target function. We assume that the environment has the same variability everywhere, which is typically not true in a real environment. For example, in this volcano environment, we have a higher variability in the central part. Due to this mismatch, we will see a higher modeling error in the center. The second problem is that stationary kernel assigns higher uncertainty to the unexplored area rather than the high error area or complex area. This problem is even worse than having a high error because now we cannot reduce the error by minimizing uncertainty. As a comparison, if we use a non-stationary kernel as the attentive kernel we will introduce later, we can capture more environmental features. And we have smaller modeling error. Most importantly, we assign higher uncertainty to the complex area. This is a side-by-side comparison between using a stationary kernel and a non-stationary kernel in robotic information gathering. We can see that on the left-hand side, the stationary kernel guides the robot to explore the environment uniformly, ignoring the fact that we have a higher error to the right. As a comparison, non-stationary kernel gives higher uncertainty to the right, so the robot collects more informative data or valuable data there. If we look at the prediction and ground truth map, the non-stationary kernel gives us a better prediction that is closer to the ground truth than the stationary kernel. I hope everyone is motivated as me to design a non-stationary kernel for robotic information gathering. First, we identified that there are two types of non-stationarity. The first one is called variable length scale. This is demonstrated by this toy function. In the middle part, we can see there is a wiggly function where we need a small length scale to model it. And we need large length scale for anywhere else, because they're pretty smooth. The second type of non-stationarity is the sharp changes around the transitions. Let's first look at why stationary kernel fail in this case. If we use a small length scale, we're not able to model this smooth part if we don't have dense data. And also, we have a high error at the sharp transition because we use the small length scale, which assumes that the data points are not highly correlated. If we use the large length scale, we cannot model the wiggling part, and we smooth out the transition. So how the attentive kernel handles these problems? For the variable length scale, we propose similarity attention, where we learn a weighting function that can adaptively combine different base kernels with prefixed length scales. Our key observation is that after normalization, the data typically has a typical range of length scale, where we can build some primitive base kernel and then combine them together later. Here is the learned W vector for each input. We can see that for the middle part, we select the small length scale, and for other area, we select large length scale, so that we can model this function better than the previous result. But we still cannot model the sharp transition. which leads us to the second idea, which is called visibility attention, where we learn a membership function Z and use the inner product to mask out the correlation, no matter how large or how small their length scale is. Here's the learn Z function of attentive kernel. We can see that we select different membership for the two sides of the sharp transition so that we can model this part pretty well. Although I present it in this simple way, the attentive kernel is actually extracted from this generative model called AKGPR. This, compared to the stationary kernel or other the standard Gaussian process regression, this model gives us a better uncertainty quantification. We can see that a high uncertainty is assigned to the complex area. Applying this to the robotic information gathering problem, we can have better uncertainty, better objective functions for the planner. We've conducted experiments in 4 environments with different characteristics, and we compared to 2 leading non-stationary kernels and a stationary baseline under 5 evaluation metrics. Attentive kernel consistently outperforms these competitors. We've also tried different sampling strategies. Sensitivity analysis shows that the attentive kernel is robust to the number of base kernels, the hidden units, and the range of primitive length scales. Ablation study shows that similarity attention contributes more than visibility attention. And finally, overfitting analysis shows that attentive kernel is more robust than others, but we think the regularization method is still needed for training non-stationary kernel. We've conducted the real-world experiment in this quarry lake where we hope the robot can collect more samples in the interesting area at the lower left corner and upper right corner. You can't quite see it on this Google map, but I have swam in this lake. So at the lower left, there is a rocky area, and the upper right, there is a large stone platform, which has the sharp transition. This is the system. We have IMU and GPS for localization, and a downward-facing sonar for collecting the depth measurement. The robot first collects information or circling around the environment to get a sense of the environment. And then it starts focusing on this lower left complex area because the attentive kernel assigns higher uncertainty there, just like the volcano case. I'll show the map building process in the next slide, where the bottom part is the prediction and the upper part is the uncertainty map. Oops. The robot keeps chasing an informative waypoint while collecting data. After effectively reduced uncertainty at the lower left, the robot starts exploring the environment. Here we discover another interesting spot and build the map. Here we can see that we capture these 2 environmental features autonomously. To wrap it up, we emphasize the uncertainty quantification of probabilistic model is important for robotic information gathering. We propose attentive kernel, which is similarity attention and visibility attention, to provide better uncertainty for information gathering. We've done field experiments showing that the robot is able to identify essential sampling locations and collect more valuable data. We provide a code for all the figures, animations, and results, and more videos can be found here. We also open source the software called Pipolo, which is for informative planning and uncertainty-aware learning. Thank you for your attention. I'm ready to take any question.
Questions for our speaker? Go ahead.
So this is really good work. I have tried to struggle with this problem of heteroscedasticity, and you get the failure you exactly point at, which is you don't get the hard boundaries between the different kernels. So I just want to say, I think that's great. It's a nice solution. What do you do when you actually don't know the membership? You have a point, and it lies halfway between the support of all your previous points, and you can't tell which GP to associate it to.
Which members? You mean?
So you have some new point, and you're going to do inference, and it lies halfway between, so you have, say, a bunch of points from one GP and a bunch of points from another GP,
yeah.
And you've associated them. And now you have one point that lies right in the middle between the two. And so it's not clear which GP it belongs to. How do you handle that in terms of the inference there?
Oh, actually, for the weighting function and the membership function, we use soft relaxation. So we can soft assignment for those points. It's not a hard partition.
I see.
Yeah.
So, and do you weight the output of the 2 GPs according to the weight of the soft assignment?
It's proportionally assigned to different Gaussian processes.
Okay,
yeah.
Great, thanks.
Wonderful. So I'll ask a question. This is really interesting and not in my area, but is there a way of including prior information, so adding priors to the system that would allow the information gathering to focus on specific areas?
Yeah, great question. So we actually have another RSS work proposing a multi-objective planner for doing this multi-objective sampling where you can inject your prior information about the environment. For this task, the robot just sampled the environment autonomously, so we can only inject prior information in the kernel function where we can provide provide knowledge of how smooth the environment is to the Gaussian process regression. If we want to focus on some specific area, I think we need to define another objective function and do multi-objective sampling.
That makes sense.
Yeah.
Thank you.
Thank you.
One more question?
Yeah, this is a very interesting talk, and I can see it's following kind of like a next best viewpoint strategy. Would like to hear your comments or thoughts on how easy is it to extend to multiple targets or more complex targets?
Do you mean by more complex, do you mean high dimensional data?
Yes.
Yeah, well, we have tried running this kernel on some UCI high dimensional data sets. It's also better than the Gibbs kernel and the deep kernel learning non-stationary kernels. So we have already extended that to high dimensional.
Oh, great. Looking forward to that. Thanks.
Thank you.
All right, let's thank our speaker. And that brings us to the end of the session.
So before I turn it over to Dylan, I have a couple of quick, what happened here? A couple of quick administrative announcements. So about the banquet, we're really concerned that you're all going to get lost and not be able to make it onto this boat. So first, a couple things. You can get +1 tickets. We have a couple of them still available. So if you need one, please check out the registration desk and use the Feedloop site as well. The QR codes will be available at the registration desk. We want to make sure that you all can get to the banquet. It's actually going to depart at Pier 40, which is actually a bit of a drive or subway from here. You definitely cannot walk this. So by subway, it'll take about 35 minutes, plus or minus, depending on how long it takes for your subway train to arrive. You can take the #1 train from the 116th Street station, which is just over here. You'll take the direction to downtown or Brooklyn, and you'll get off at Houston Street. I thought it was Houston Street until Matei corrected me. An alternative is you can take a taxi or Uber, which will take about 30 minutes or so. You must bring your badge, and the QR code on the back is for your ticket. We recommend that you arrive by 6:30 p.m. because if you arrive after 7, you'll be swimming after the boat. So please arrive between 3:30 and hopefully several minutes before 7. The boat cruise is 3 hours long, so it will return at 10 p.m. And we had some mistaken information in the email that was sent last night. The cruise company told us that they'd be returning at a different location, but then after some negotiation, they decided, okay, we'll return back to the original place, which is good because it makes your return trip better, more easy. If you just want to come back here, you'll just take the #1 train back. For those of you who are staying elsewhere, you have to check out the subway system and figure your way back. One other thing is that we are out of space on the lab tours, and so if you are deciding not to go on the lab tours, please relinquish your ticket so that somebody else can join. We have no real way to do this automatically, but if you can email Florian, our registration chair, he will kind of take the ticket off and let somebody else attend. So thanks, and with that, I'll let Dylan get started.
Thank you, Chris. I'll let Jens get started setting up here. So it's my great pleasure to introduce Jens Kolbe. He is our second early career spotlight speaker. He earned his PhD from TU Darmstadt with a thesis entitled Learning Motor Skills from Algorithms to Robot Experiments. which was recognized via the George Garreau Award as the best robotics PhD thesis in Europe in 2012, so 10 years ago. Since then, Jens has become an associate professor at TU Delft, and he's been recognized as an Ellis Scholar. His group studies many aspects of machine learning with applications to robotics, including learning skills, motor primitives, RL, imitation learning. And the last thing I'll say is that Jens has made significant service contributions to the community. For the last 5 years, he co-chaired the IEEE RAS Technical Committee on Machine Learning. He was program chair for CORAL in 2020, and he was the RSS Virtual Conference Arrangement Chair in 2020 when we were all scratching our heads wondering what was going to happen. So he's going to tell us about using interactions to teach robots. Please join me in welcoming Jens.
Thanks a lot for the very kind introduction. Let's start with something a bit more fun. Who of you can flip pancakes in the air? 1, 2, 5, 10? Not many. OK. Then robots surpassed the rest of you about 12 years ago. I guess many of you have seen this video by Peter Komuchev, went viral back then, using a combination of imitation learning, so giving a demonstration and the robot trying to mimic that, and reinforcement learning to fine-tune that movement. And personally, why I like that is because for the reinforcement learning part, they used an algorithm I developed. It takes about 50 trials or so until it can do it, which is pretty impressive. But there are obviously also quite a few limitations. It's effectively an open-loop movement, needs a good demonstration, and so forth. So I'm still pretty confident that I myself, once I get around to try to learn that skill, will be able to do it more quickly. Let me start with giving a brief overview of how people learn. It's not going to be scientific in any way, but I still think it's very interesting to see how that connects to things we do in robot learning. We already saw using a combination of what happened now. Nope. Yes. Okay. Ha. I'm really sorry about that. Okay. Okay. It's not a video. It's not? Nope.
When you get to the presentation, you blink.
Yeah.
Take it off.
And that doesn't allow me to duplicate. It works for a second, and then fingers crossed.
Do you want to skip to the next slide to see if it's...
It's mine.
It's always the same slide, right? Is there
Yeah.
animation on it?
Nope. Okay, let's see. So on the previous slide, I had a combination of imitation and reinforcement learning like we saw in the pancake example. One of the other things you can notice if you think about how humans learn is that while we're young and a baby, it takes quite a long time until we learn basic things like grasping and walking. But once we have those basic skills down, then we can actually very quickly learn related skills, like grasping a book in this example. If you translate that to robot learning, that might be doing some higher level planning with a fixed skill library, or some form of transfer learning or meta learning. The other thing is we as humans have a pretty good understanding of our environment and how that works. So we have an understanding of intuitive physics that an apple is always going to drop. And we can use that to do mental rehearsal, to just think about what we should do in order to achieve a certain task and how the environment is going to change before we actually try it out in the real world. So that's then connected to model-based learning and planning and optimization, or also sim to real, for instance. What I want to focus on today is interactions with teachers. If you think about how you, for instance, learn a new sport, you're not going to get an initial demonstration and a rough description of what you're supposed to achieve, but rather you're going to have a coach look at what you're doing once in a while, then give you some corrections, some feedback, some hints to get you unstuck if you went down a wrong path, or maybe just to tell you on what you should focus next. Henny already talked a bit about interactive learning yesterday, but you started from the assumption that it's actually useful and really helpful to make robots learn quickly, and then you went on to discuss that from a human-robot interaction point of view. But if I talk to some people, not all of you seem to be convinced yet that getting a human involved really in the learning loop is a good thing to do. And my goal today is to try to convince a few more of you. So, teaching through interactions. That means that we're going to have continued student-teacher interactions while the robot is in the process of learning. So you could provide some additional demonstrations, some other form of intermittent feedback. And you see that more and more in robot learning. I believe there are huge benefits to that in order to speed up the learning process, which in turn enables the robots to learn more complex tasks. And hopefully, if we get the HRI side down, is also intuitive for humans, especially if they're non-robotics experts. And the cool thing is, I now talked about how humans learn. Also, if we look at how we teach other agents, like animals, that's one of the things you constantly see. So to start out, I'm going to talk a bit about interactive reinforcement learning. I'm going to give you another example, ball in a cup, where the goal is to catch the ball in the cup. That's my cousin's daughter. She was around 10 years old back then and took her 35 times to catch the ball in the cup. If we do the same thing like we saw in the beginning with the robot, start with a demonstration, you try to execute that on a robot, works kind of, but misses by a few centimeters. After 15 trials, it's already quite a bit closer. Now it's trying to optimize the distance between the ball and the cup. It takes about 40 trials to sometimes get it in, usually it bounces off, and after 100 trials, it has converged. So that didn't have any interactions yet, except that Katharina had to practice quite a bit to get the demonstration down, and also I had to learn quite a bit about how to design the reward function, so we had some iterations in the learning process there. So why not formalize that a bit? So, interactive learning. Before I show you how ball in a cup with interactive learning looks like, I'm just going to give a brief introduction about the setting. So we have an agent, a robot, and an environment. We have a state, and then the robot needs to decide which action to take next, so that's a policy. And then that looks very familiar, like a reinforcement learning loop or just a generic controller. Now what we have additionally is a teacher here in the center who is able to observe both the states and the actions the robot is taking, and then once in a while he or she is going to provide some kind of feedback. We heard in Henny's talk yesterday there's quite a spectrum of kinds of feedback you can give. And I think there's a big trade-off between how easy it is for humans to provide feedback and how informative that is for the robot. So on the one end of the spectrum, you could have really a binary feedback, works, doesn't work, which is really easy for a person, but not very informative for a robot. On the other end of the spectrum, maybe you have a complete demonstration, which helps the robot a lot, but can be very tricky for a human demonstrating, because then you really need to learn how to use the system to demonstrate it. So in practice, what my group figured out that works really well is to do something in the middle. So we settled on using corrections, mainly in the action level. So that means you don't need to give the robot the correct action to take, but rather you tell it a relative correction. You should move more in that direction, for instance. That seems to be a nice trade-off between having something that's still doable and still informative. To give you an example of an interactive imitation learning approach, here's COACH, which stands for Corrective Advice Communicated by Humans. It's a bit confusing. There's another algorithm that is exactly the same acronym that also does something kind of similar. Anyhow, so what the setting is, the car, or the robot in this case, is supposed to drive from top to bottom. It has some initial policy, and then the human teacher is once in a while going to jump in when the robot is screwing up to give corrective advice, move more to the right, move more to the left. What's also important to note is that this is truly interactive, so the robot is going to directly adapt and take the correction into account. And then once you've done that, once, hopefully the robot has learned from the corrections and is able to do it a bit better, so the human teacher needs to jump in less frequently. And then in the end, hopefully the robot is able to do it on its own. So now we could say, okay, I have a nice interactive imitation learning approach. We could just replace the initial demonstration where Katharina had to practice so hard by this interactive learning approach. And then we, again, use reinforcement learning, or in this case, policy search, to fine-tune it. But I think we can do better by really doing it simultaneously, all in one. So how we did it there is that we actually model the human input as a form of exploration. In reinforcement learning, you need exploration, so the robot needs to try out new things in order to figure out what works better and what works worse. And that's usually a form of perturbation or noise on top of the nominal policy. And now we additionally treat the human corrections as a form of exploration. And that works very well if the algorithm can cope with off-policy data. Standard policy search looks something like that. So need to explore and do a number of rollouts, so try out different strategies with a bit of exploration, and then you evaluate how well that worked. Here it's just an episodic setting, and then you apply your favorite policy search approach to update the policy parameters. What changes now, if we make that interactive, is that we additionally get the human in here. Why do we have this hard switch? Turns out that if a human is trying to demonstrate something and the robot is additionally also exploring on its own, that gets very confusing. And here we indeed used COACH, the algorithm I introduced a few seconds ago, for the human guidance. Then that looks like that. Now we can not see anything. Okay, let me try once more to duplicate. Nope. Okay. So, let's try to play that once more. So we can start from scratch. But additionally, instead of the demonstration, now we have a teacher sitting in front of the robot providing corrections like move more to the right, move more to the left. And then within 20 trials or so, the robot can catch the ball in the cup. As a plot, that looks something like that, where you have the number of times the robot tried here on this axis. Here we have a cost, so lower is better. The blue and green are the interactive approaches, and in red is a reinforcement learning approach without any interactions. So for both the interactive approaches, took about 20 trials to get it in. For the reinforcement learning, it takes about 200, so an order of magnitude longer. And then the main difference between the green line, which is imitation learning only, and the combined imitation learning and reinforcement learning is that you can get pretty good, but only by having the robot fine-tune, you can really get the best final performance. So I think that's very interesting because it nicely shows that the strengths and weaknesses of a robot and a human are very complementary. A human is very good at giving the rough idea and the rough demonstration, figure out the big strategy, while people typically are not good at fine-tuning and being reproducible and very accurate. And that's something a robot excels in. So let's switch gears a bit and talk about interactive imitation learning. And actually, I'm also switching gears once more and talking about slightly higher level learning. In imitation learning, the thing you want to do is not just replay what you've seen. That would be boring. You want to generalize to a new situation. So for instance, you should be able to grasp a cup no matter where it is placed. In this example, we additionally have a coaster. So the robot is then supposed to figure out with respect to which objects it's supposed to move or relative to the world. As long as the cup and the coaster are always together, that doesn't make a big difference. And if you forget to demonstrate that maybe those two objects can get separated, then once you have the two examples on the side, then the robot suddenly is lost because it's ambiguous. And you would either need to go back and collect more demonstrations, or what I'm going to show you next is actually have the robot ask for feedback and try to get the human teacher to disambiguate that for it. And what's really interesting also is that in many situations, it doesn't really matter. Even if there's an ambiguous situation, if the action the robot would take is effectively the same thing, then there's no need to bother the human with a question. So our approach is only going to ask the human teacher to disambiguate if that's really crucial for the robot to complete the task. So here we taught the robot how to put a cucumber into a crate. It can do it from different initial positions of the cucumber. But what we forgot to teach it intentionally is what happens if you swap the position of the two crates. So now it doesn't know whether it should move relative to the world coordinates or relative to the position of the crate. So it can still do the first part of the movement. Now it gets stuck. And it stops, so we need to give it a little correction, a little feedback, so it can disambiguate that, and from now on, it knows that. We also ran a user study for that, where we compared kinesthetic demonstrations and teaching, where you're supposed to collect quite a few demonstrations that are sufficient to disambiguate all the things the robot might encounter. So there you need a few corrections. You can try it out. You need to figure out, OK, I forgot something, collect a few more demonstrations, and hopefully it works in the end. And we compared that to LIRA, which stands for Learning Interactively to Resolve Ambiguities, which is exactly this interactive framework where the robot is asking if it needs to disambiguate something. So there, we just saw one additional correction. Then if we compare them, KT, a bit more on the left, is the kinesthetic demonstrations, and LIRA, the interactive one. And for all of those blocks, lower is better. So both in terms of demands on the user and in terms of what they prefer to do, the interactive approach does a lot better. So far, I've only shown you things that don't involve any deep learning, but there's no reason why not to do that. So we can also apply these ideas if we want to learn directly how to control from images. Well, not entirely directly. You still need to bring it down to a manageable size, some latent representation as usual. So one idea could be to start out collecting a bit of data of your environment, maybe not exactly the task you're interested in, and then train an autoencoder. Then use the encoder and attach a policy head on top of that. That works. It's quite a bit of additional work, and depending on the data you collect, it might not work that great. So instead, again, can't we do that at the same time? And indeed we can. So now the main objective is to learn a policy, and as an auxiliary criterion we have the autoencoder, so the reconstruction of the input. And then to come back to the little driving example, here you have Duckytown environment where the robot driving around. On the top here, that's the camera image, and that's the reconstruction from the latent state. And then it takes around 9 laps or so, and then you can also intermittently test how well the robot does. You just don't give it any feedback any longer, and then you can see that it already does quite well. That works very well if you can directly map from states to actions, but for many tasks you actually need some form of memory. either because you need to remember something or simply because you might want to have an estimate of a velocity of some objects. So the most natural thing to do is to include some memory in the network structure. Either you stack a few images or you include a recurrent structure like an LSTM in this example. And the other thing that changes is now we are not trying to reconstruct the observation directly, but the next one in the future. And if you're collecting data, that's easy to do. That actually then forces the network to learn about the dynamics and the memory because it needs to predict into the future. So here's an example of that. The goal is to collect these fake oranges. To make it a bit more tricky, the robot can only see the part here in white. So it needs to memorize where the objects are so it can touch them later on. And here, that's what the network sees here. And there, again, the reconstructions on the bottom. And then already after 15 minutes, it does quite well. Here we're using keyboard interactions to provide the corrections. And then after 35 minutes or so, it has reached peak performance. And what's really cool is if we have a good policy already and a good representation, we can actually transfer it to a new task and very quickly adapt it to that. So here now we're covering up the oranges with pairs, and it's supposed to avoid those. Here you can really see the corrections we're providing. And then after 3 minutes, it can already do it. And then if you train a bit more, like after 10 minutes, it has converged. The things I showed you so far were in action space, corrections in actions, which is nice because it's direct. However, if you have a robot like that, it also gets high-dimensional and can be very non-intuitive. So why not teach in state space instead, so in end-effector space? That needs an inverse model to map back to the actions you actually want to do on the robot. If you just buy it and you're interested in the end-effector, that's something you get from the manufacturer. But in some other cases, like for example here, you might not know this transformation, so this inverse model. So here the task is to use the laser pointer to track the shape on the whiteboard, and we want to give the corrections directly in the space on the whiteboard. So here within 20 minutes or so, the robot learns to both do the task of tracking in the letters and also learns the inverse model it needs in order to map from the state space to the actions. Then one final block, going beyond kinematic trajectories. If you're interacting with the environment, you also have forces that you want to exert and have complex contact dynamics. So here, for a very classical whiteboard wiping task, with this kind of robot, if you don't have a force torque sensor, you can't actually record the forces. So what you're going to see now is Anna providing a correction, so effectively pushing the robot down, which is going to put the attractor below the whiteboard and also to increase the stiffness in that direction. And then with just one little correction, it can learn that, and now you're going to see a validation that actually learned to do that. What we learn here is attractor fields represented as Gaussian processes, both for the stiffness and the trajectory. You see the original trajectory in red, the final trajectory in black, and the background tells you how much force it applies. One final example, trying to restock in a supermarket. If you would do that in a very traditional way, do a pick and place action, you go to the object, stop, close the gripper, and then continue moving, which is very slow. If we want to, here we want to do it in one nice fluid movement, but then you actually get interesting contact dynamics and it can bounce off. And the additional difficulty is that the timing of the gripper is very imprecise, so we needed to teach it a trajectory that is robust to that. We started out with a pretty slow demonstration. If you've ever tried that, it's really hard to give good demonstrations if you want to move quickly. And the goal was to speed it up 4 times, so bring it down to 5 seconds. And that's what you're going to see here. It can do that in one nice fluid movement in 5 seconds. And here we gave the users the opportunity to separately tell the robot where it should speed up and how to correct the trajectory. And then what we learn can generalize to different initial positions of the object. You can also mess with it a bit by moving the object around. However, also here, it's unaware of what it knows and what it doesn't know. So if the object is too far away from what it has seen, it's just going to stop and wait until the object is close again, or you provide additional corrective feedback. So to sum up, I talked a lot about teaching through interactions. And I hope I could convince you that this is a promising way of speeding up robot learning, because humans and robots have very complementary strengths and weaknesses. And it's not a standalone thing. You can combine it with many of the other ideas that people are exploring to speed up robot learning. The other side of the medal is, how do humans actually like to teach? How can we make it easy for people to teach? And for that, Hini's talk was great yesterday. So I fully agree with the statement that assuming humans are oracles for training data is a bad idea. In all the things we tried, that never was the case. However, to paraphrase the famous sentence by George Box, all models are wrong, but some are useful. I'd say, at least so far, all humans have been wrong, but most have been useful if they're trying to teach a robot a new skill. So to sum up my talk in 2 images, I believe that it's a great idea to help robots to learn new tasks quickly by interacting with them while they're actually trying to achieve the task, in order to enable them to move to learn very quickly and efficiently, such that they can support us later on. So I'd like to thank all the people that contributed to the work I was presenting today. They put in countless hours of hard work. And I'd also like to thank the organizations that funded this research. Thanks a lot.
Thank you, Jens. So do we have any questions? I see a few people coming up. Okay, good. Excellent. Shall we start on that side?
Yeah. Thank you for the great talk. So I just have a question. In the cases you showcased, how robust it is for the robots against like adversarial interactions from human actions. For example, imagine you have a teacher who is like always giving the wrong instructions, or like sometimes give the wrong instructions. How would that affect the system's performance? Thank you.
Yes, excellent question. I'm going to answer in 2 parts. For the imitation learning part, we essentially assume that whatever the teacher shows is what the robot is supposed to learn. There might be some noise on that, but on average, that's what the robot is supposed to learn. So there, that doesn't really apply. However, where that gets really, really important is in the reinforcement learning setting. Especially, so very simply, if the reward of the robot and what the human is trying to teach doesn't align, or if the human is trying to be adversarial, then it's just going to fight it and it's not going to converge to anything. So one way to deal with that is actually think about interactive inverse reinforcement learning and trying to first figure out what the human is trying to achieve by learning a optimization criterion and reward function. And there's also quite a bit of work on that.
Thank you.
Hi, thank you for the talk. So my question concerns how do you solve, or is there a problem, and how do you solve a problem of correspondence between the human's feedback and feedback that is useful for changing the robot's policy? I'm imagining the case where you have some sort of deep network representing your policy, where the easiest feedback might be, change the weights in this direction, but a human can't give that feedback. The human has to say, move more left, move more right. How do you solve that mismatch, and are there best practices for designing policies that are more interpretable and more open to that sort of feedback that's more easily given by humans?
Yes, indeed. I don't have a recipe yet. And I think it needs to come from at least 2 sides. We need to think about it from the robot's perspective, about what's useful for the robots. And I could also think along the lines of going more the direction of active learning, where the robot is actually actively requesting information, but then you need to be careful not to totally overburden the human. And then you also need to look from the other side about what can people do? What do they prefer to do? Actually, it turns out that there's also a big difference between people and groups of people, how they like to teach the robots. I'm sorry, I don't have any answers yet. We now started working also together with people looking at it from the human-robot interaction perspective, so maybe in a year or so we can tell you more.
All right, thank you.
Go ahead.
Hi, great talk and a very impressive demo. And one question I have is, have you ever considered a case when the human's not an expert at giving these kind of feedback? Because it seems that PhD students obviously know how to work with the robots, but if you actually deploy this robot at a, I don't know, nursing home or someone's home, the person that's trying to use the robot may not be very good at giving feedback. I mean, these cases, how do you still ensure that robots are able to learn from human feedback?
Yes. So we don't necessarily assume that a human is an expert. A human needs to know how to roughly solve the task. And quite often, it's actually an interaction of the teacher trying out to teach the robot something, then seeing, okay, it doesn't really work how I imagined it, and then changing the strategy a little bit. More practically speaking, yes, we are the university, so most of the people we had in the experiments are students. Quite a few have a computer science background, not necessarily robotics background. We tried to get in a few people also that didn't have any experience with the robots at all. Yes, you can see a big difference. And people that are playing computer games are amazingly good at teaching robots, but also the others managed.
Great, thank you.
So I do see there's some more questions, but I'm afraid we're going to have to stop them there. You'll have to ambush Jens.
Yes, I'm around till Friday evening, so try to find me.
Great, so we're going to move directly then into session 8, the next session of short talks. Let's thank Jens again.
Thank you. The chair of the next session is Abdeslam Bouliaris.
Okay, so it's my pleasure to chair this last session for today, where we'll have a block of 5 talks, 5 minutes each, followed by 5-minute questions and answers. And first talk will be given by MD Jahidul from University of Florida, and he will present SVAM.
Hello, everyone. Welcome to the presentation of our paper titled SVAM, which stands for Saliency-Guided Visual Attention Modeling for Autonomous Underwater Robots. So the idea is to identify interesting objects and pixels in an image so that visually guided underwater robots can model its visual attention and make fast operational decisions, such as where to go, which samples to collect, and so on. Towards solving this problem, we adopted the salient object detection problem and proposed a novel deep visual model named SVAMnet. The SVAMnet not only achieves state-of-the-art performance, but more importantly, it provides platform-specific design choices. So it provides a full model for high-end GPU use and provides a light model for robot deployments. So our full model runs at 20 frames per second on 1080 GPU, and light model runs on 20 frames per second on Jetson Xavier. Here's an example of how we can use SVAMnet for real-time robot vision. Imagine we want to perform enhancement on a full-resolution image from robot's camera. We can use state-of-the-art models, but they run on very low input reception, so the output will be something like 256 by 256. To enhance all the patches, we need quite a few computational load, which is not possible on a single board device. So what we can do instead, we can run SVAMnet and look where the salient pixels are and only enhance the patches that we need. So SVAMnet runs on 46 milliseconds only. So depending on how big the salient objects are, we can get at least 2 times or up to 10 times faster processing. So now we'll briefly talk about our model architecture. So the backbone of the SVAMnet model is a traditional encoder-decoder model. So the input goes to 5 layers of encoders for feature extraction, and then those are used by reflective 5 decoders in a top-down fashion for saliency estimation. So we then use a residual refinement module to further refine the output for fine-grained salient object detection. So this is the full model. But then we add 2 special attention module, or known as SAM, to refine the early encoder layers. So and we apply independent loss functions to all these ends. The idea is to train the whole model together, and once the whole model is trained, we remove everything else, the decoders and refinement modules, and use one of the shallow encoder branch as a light model on embedded devices. We achieve this comprehensively by 2-step training. On the first step, before training, let's discuss this. So this is our full model. Input goes to encoders, then decoders, and refinement modules, and the output. And this gives us 20 frames per second on 1080 GPU. And this is our light model. So input directly goes to encoder and the shallow branch. And this gives us 21 frames per second on Jetson Xavier, which is equivalent to 86 frames per second on 1080 GPU. And as I mentioned, for training, we pre-train the backbone first with comprehensive terrestrial and underwater images. And then we fine-tune the end-to-end model on underwater images only. We use the traditional cross-entropy loss and the binary localization error term, which we kind of formulated. Please refer to the paper for the detailed loss function formulation, training pipeline, and evaluation pipeline. For the rest of the presentation, we'll just show some qualitative examples and demonstrate how we can use it in practice. For instance, here, the white pixels represent the output of the full model, and the green pixels and the red object contours represent the output of the light model. As you can see, the full model's output is fine-grained and pixel-level accurate, where the light model's output is sort of abstract, but still pretty well localized for high-level decision-makings, and to segment out the background from interesting foreground regions, such as humans, other robots, fish, and coral reefs, and instruments, and so on. This is our model in action on footages of underwater human-robot cooperative experiments. As you can see, it can successfully segment out the water body background pixels and sort of gives you a visual attention modeling, like visual filtering light of kind of job. And as it runs on 20 frames per second, we can use on near real-time applications. The backbone is trained on both terrestrial and underwater images, so it sort of works on random data. We'll show in the next example that on a random Gundam-style video, it can also work well and sort of gives you where a human would look at. So this concludes our presentation. I look forward to talk more in our poster session. Our poster number is 18, so I look forward to seeing you there. Thank you.
So next talk will be given by Thierry Guan from University of Maryland, and he will be presenting TNS.
So hello everyone, my name is Thierry Guan, a PhD student at University of Maryland, College Park. Today I'm presenting my work, TNS, Terrain Traversability Mapping and Navigation System for Autonomous Excavators. The work is conducted while I'm interning at Baidu RAL Lab. Just to give you some background, construction robotics has been $1 billion industry. The size of global market of excavators is $44 billion in 2018 and is expected to grow to $63 billion by 2026. Baidu previously developed an autonomous excavation system that can perform excavation tasks for more than 24 hours without any human intervention. And in this paper, we focus on navigation aspects. So we present a real-time terrain traversability estimation and navigation system, TNS, for excavators. We show that our method is the state-of-the-art method on traversability mapping in complex environment. We have integrated TNS with planning and control algorithm and evaluate the performance in real-world setting on an excavator in various challenging settings. We highlight the benefit of TNS in terms of the first autonomous excavator that can navigate through complex, unstructured environments. And in the end, we present a complex worksite terrain dataset in unstructured environment with 7 different classes based on different terrain types, traversable regions, and obstacles. We will release the dataset. So the dataset is collected on an excavator while a worker is navigating through a construction site. We extracted 669 images from 30-minute videos and annotate those data according to terrain types and obstacles. So the perception pipeline of TNS consists of 3 components. So the first component process the RGB image stream and segment the image according to terrain types. The segmentation results are projected onto the 3D space. The second component extracts geometric estimation according to slope and height, step height based on the point clouds. And finally, the semantic information and geometric information are combined to calculate a traversability map for mapping and navigation module. So here are some perception methods that include 3D semantic segmentation methods and traversability mapping methods. We evaluate the final traversability output based on both traversable, non-traversable regions, as well as the mean accuracy of each terrain type. Now we present the proposed TNS. The perception module takes several perception sensors and generates the traversability map that encodes the terrain types and shapes. Next, the planning module takes the traversability map and generates a feasible trajectory. And finally, we use a tracking controller and speed controller to navigate the excavator following the planned path. So we use a high accuracy GPS RTK for localization purpose. So next, we'll show some traversability map generated by our methods. So on the left is the image stream. On the top left is the image stream from the excavator in real time, and on the top right is the generated semantic segmentation result, which is also predicted in real time. At the bottom left shows the colored point clouds after we project the semantic segmentation result onto the 3D space, and the bottom right is the final traversability map. Next, we'll show some planned trajectory based on different mapping methods. On the left is a planning result from a method that based only on geometries, while on the right is the output of TNS. On the left, no viable trajectory are found due to the noisy output of the map. On the right, our mapping methods can find a safe path to the goal. Our method can remove noise from geometric computation and generate a clean map through a semantic segmentation. In this case, we highlight the obstacles on the map with a red circle. The geometric information could identify the geometric information could not identify the obstacles, while we can see the obstacles through a semantic information. So the geometric-based methods would draw a path over the obstacle, while our method can avoid the forbidden region and obstacles. Now we show a clip of excavator navigating in a construction site based on TNS. So there are many technical difficulties that we need to overcome and make the excavator navigate through this challenging terrain. So please refer to the paper for more details. Just as a safe protocols, the human operator has to be in the cabin for all times. And finally, I want to thank everyone for being here today, and thanks all the collaborators. If you have any question or would like to chat, please feel free to reach out. Thank you so much.
Thank you. Next talk will be given by Nathan Hughes from MIT, and he will be presenting Hydra.
Hi, I'm Nathan Hughes, and today I'm presenting Hydra, a spatial perception system for 3D scene graph construction and optimization in collaboration with Yun Chang and Luca Carlone. 3D scene graphs are a promising hierarchical map representation for robotics. In addition to the 3D metric semantic mesh and objects that a traditional 3D reconstruction technique might provide, a 3D scene graph also includes a sparse description of the free space in the places layer, as well as the scene layout and the rooms layer. They've shown promise for both high-level scene understanding, as well as early promise for path planning and reinforcement learning search. However, previous approaches like Chimera, scene graph fusion, and others have had to make trade-offs between scene graph completeness, online operation, and actually correcting the scene graph for noise during scene graph construction. Chimera especially could take up to 30 minutes to construct a scene graph for large environments due to a reliance both on a global voxelized ESDF of the environment, as well as a need to rebuild the scene graph from scratch to actually correct for drift after detecting a loop closure, both of which aren't great if you want to use scene graphs for real-time robotics applications. Instead, we propose Hydra, a parallelized architecture. Hydra ranges between low-level, mid-level, and high-level perception processes. We use VIO for basic localization of the robot, and we piggyback the first two layers of the scene graph off of 3D metric semantic reconstruction. We also have a backend that turns a odometric scene graph into a persistent scene representation. Hydra also includes as contributions a novel room segmentation method that operates directly on the places layer, a novel loop closure detection method that exploits the hierarchy of the scene graph, as well as a method for optimizing the scene graph to actually correct for drift. Next, we show a video of Hydra actually operating in an example scene. We first use Chimera to actually produce the 3D metric semantic mesh inside a spatial window around the robot. We then use Euclidean clustering to actually extract the objects from the mesh vertices inside that active window. We extract the places from a generalized Voronoi diagram that is a byproduct of building an ESDF inside that active window. And finally, we extract the rooms from the places in a process that we describe next. This room extraction process is divided into two phases, the first of which is shown on the left. We filter the places graph at different distance thresholds to simulate dilating the environment, naturally closing off doorways and other openings. This leads to a series of candidate rooms, of which we pick the most persistent. We fill out this candidate with partially seeded Lobain clustering, a community detection method giving us the final rooms. For loop closure detection, we supplement traditional vision-based descriptors that are dbout2 and orb descriptors with subgraphs in the object and places layer, forming a hierarchy of descriptors that we use to actually filter the vision-based matches. We can also register these subgraphs together when vision-based matching fails using point cloud registration techniques, giving us additional robustness. When we actually detect a loop closure, we can then go and optimize the 3D scene graph by building an embedded deformation graph from the robot poses, the mesh control points, which are obtained by spatially compressing the mesh, as well as a minimum spanning tree of the places graph. When we optimize this structure, it's equivalent to pose graph optimization. Here we show example data in MIT student housing. You can see two hallways on top of each other at an angle due to drift, but once we detect a loop closure and actually optimize, the scene graph snaps together, creating a much more consistent scene. Hydra represents a very significant step forward for real-time performance, and we include preliminary results on an NVIDIA Xavier NX, an embedded processor. Note that we also show comparable accuracy to Chimera in the paper despite running in real time. So in summary today, I've discussed Hydra, a spatial perception system that constructs 3D scene graphs in real time. Hydra is capable of actually correcting the scene graph for noise through 3D scene graph optimization and has a method for augmenting traditional vision-based loop closure using the scene graph. Our code is open sourced and released on GitHub. We're very excited about future steps involving improving the semantic richness of the scene graph, and I'm personally looking forward to talking to everyone at our poster session about future applications of Hydra, as well as other technical details. Thank you.
Thank you, that was excellent. So next talk will be given by Andriy Roshav from University of Bonn, and he will be presenting Fadiv Sin.
Hi everyone, my name is Andre from the University of Bonn, and I will present Fadiv Sin, fast depth independent view synthesis using soft masks and implicit blending. So our work is motivated by an avatar setup on the left, where an operator with an head-mounted display perceives the environment through stereo cameras which are mounted on an avatar robot. Due to limits in degrees of freedom and latencies, it might be necessary to synthesize novel views at different camera locations, as you can see on the right. So the main task here is to synthesize novel views given just two input cameras from in dynamic scenes in real time. Our two main competitors are 3D photo and stereo magnification. On the right, Xi et al. First estimate stereo depth to then build a so-called layered depth image and in-paint disocclusion areas. The main drawbacks are that their method is very slow, that they have to re-estimate the LDI in dynamic scenes, and that they have a strong dependence on depth, since they warp using depth explicitly. On the left, Su et al. Then predict the so-called multiplane image from a given plane sweep volume to then render novel views using warping and alpha blending. Their drawbacks are that they also have to re-estimate this MPI in dynamic scenes, that they have limited in-painting capabilities since they built the MPI in the reference camera, and that they also have a strong dependence on depth since each pixel will be assigned to one depth plane. So in our method, we forgo the geometry estimation by building the plane sweep volume in the target camera. We therefore So we built the plane sweep volume in the target camera and therefore forgo the geometry estimation. And a single CNN then learns to propagate areas of high correspondence to the output image directly. We mark these in green. In the lower figure, we show blended corresponding planes where such areas occur as sharp regions. These you can see in the green circles. The network should also learn to discard poorly corresponding areas, which are marked in red, and to in-paint disocclusions already at this stage. Our method can handle reflections, transparencies, occlusions, and disocclusions. This I'm going to show in this animated figure, where we also have the blended corresponding planes and the prediction of our network in the lower right. We further extend our pipeline by a so-called soft masking network, which estimates plane-wise masks. We call these soft masks since each plane pairs are considered independently, and thus one image pixel can have multiple high values in different planes, as we illustrated here in the lower figure. The main network then accounts for these masks in a learned fashion using gated convolutions, which eliminate the need for explicit masking operations. Through this gating, the network then might also learn to ignore the mask if beneficial. So we evaluate our method on the large-scale real estate 10K dataset, where we compare our ablations with 32 planes, 19 planes, and without the soft masking called NoSM against our competing methods, stereo magnification and 3D photo. As you can see in the left table, all our methods or ablations outperform our competitors in all metrics. We can furthermore see the benefit of our proposed soft masking. On the right, on an image size of 540p, our fastest variant then achieves up to 40 frames per second, which allows us to render in real time. So on this animated comparison with Su et al., we show that their explicit depth estimation can lead to significant synthesizing errors. As you can see on the right in the circle, the window separation is clearly assigned to a wrong depth plane, which leads to such errors. Our method on the left does not suffer from this problem. In the second animated comparison, I show disocclusion areas which are correctly inpainted by our method on the left, whereas the method of Su et al. Creates strange stretching artifacts in these regions. I hope you can see that. An example can also be seen in the lower right corner. Yeah, thank you very much for your attention, and if you're interested, feel free to see me at my poster session. Thank you.
All right, last but not least, Zhang Chen from Indiana University will be presenting Kali, and right after this, we'll have the Q&A session.
Hello, everyone. My name is Zheng from Indiana University. In this work, we propose a novel domain adaptation method to help robots better understand the traversability in images. It could be easy to obtain plenty of data in simulators, but it could be very expensive to have data in the real environments. Data is the decisive factor for learning-based methods, but there is usually a non-trivial gap between the data in different domains. In this work, we're targeting at decreasing this gap by proposing a novel and supervised domain adaptation model. In a supervised domain adaptation, we have a source domain and a target domain. In the source domain, we have images and labels. In the target domain, we only have images without labels. We want to leverage those data to make the model have the inference capability on target domain. Typically, fine alignment is required for dense predictions. Fine alignment means we need to consider to align features of different classes from two domains. But in unsupervised domain adaptation, we cannot detect class features in target domain, as we have no labels here. To align the source features and target features, we first have to train two different classifiers on source domain, which generate two different decision boundaries, F1 and F2 here. The disagreement between the two classifiers is only training force to align the features. We use adversarial training between the feature generator and the classifiers to align the features. An equilibrium between the feature generator and the classifiers is expected to reach. But this is very difficult to reach because the searching space is complex, as we need to predict multiple classes for each pixel. And the training can be very easy to diverge. In this work, we solve this problem by applying a domain alignment as a constraint to the class alignment. At the very beginning, we have a source-only model, which performs poorly on target domain. In the first stage, we perform a domain alignment, which is trying to align the two domains generally. This will decrease the general distance between two domains, but lead to prediction errors, as this coarse alignment does not consider any class features. In the second stage, we perform the class alignment based on the decreased domain distance. To integrate the domain alignment and class alignment, we propose a pseudo-trilateral game structure where both classifiers and the domain discriminator are trying to adjust the feature generator. Here is how we train our model. During training, we first perform a supervised training using source labels. Then we maximize the distance between the classifiers, as we expect to have two different classifiers. And next, we perform a domain alignment, and we use a training order of max-min instead of min-max. Last, we align the features in a fine way. We repeat the 4 steps until the maximum iteration is reached. We have also proved in theory that the domain alignment can be a useful constraint for the class alignment, which is consistent with our intuition. In experiments, we have validated that the training of our Kelly model is smooth and efficient compared with the class alignment method. And compared with other baselines, our model shows advantages over other baselines for most of the classes in this city environment, sim-to-real adaptation, and forest environment, real-to-real adaptation. We have also validated that the proposed model is useful in the real navigations. Here, we assign a navigation task for a ground robot in a fall forest, which has a very different appearance than the summer forest in the source data set. The selected environments are particularly challenging, and we have no any label for the images from this fall forest. But our perception model can accurately predict the semantic classes in images and facilitate navigation. We believe our model is useful in the real deployment of the robot because our model can quickly adapt to different domains. Thank you. And if you have any question, please come to my poster, and the number is 22. Thank you.
Okay, so we'll start the Q&A. I will ask all speakers to come ahead.
I have a question for the Hydra paper. So does your scene graph currently consider dynamic objects? And if not, do you plan to work towards that direction? Thank you.
No, we don't actually explicitly consider dynamic objects yet, but that is definitely something we're very interested in for future work.
Thank you.
Yeah, I have a question for TNS paper. Yeah, I just wonder, for this challenging environment, how do you define what is traversable terrain, what is untraversable terrain? Is that kind of human decided, or what's
Yeah, so that's so basically that's a tricky concept. So basically we annotate them according to their semantic labels, and then basically for now assign a score. So basically if it's roughly flat, we assign it to, with a lower score, while if it's obstacles or bumpy region, we assign it to a little bit higher score. So right now it's more like a heuristic, but eventually we want to find some more better criterion to decide what is the best traversability.
Any more questions from the audience? Okay. Then I will ask maybe a few questions. Maybe we'll start with Tiana. So do you have a mechanism for recovering from classification errors once the robot starts following the planned trajectory?
Yes, so basically there are some classification errors. So indeed, we're not able to test extensively on like all different scenarios. We only tested some roughly bumpy scenarios in the real world. But if we want to give a little bit more unconstructed environment, there will definitely be some segmentation error, and we need to deal with that.
And how does the robot deal with that? Let's say, for example, some location is classified as traversable, and there is an obstacle there that was missed by the classification. How does the robot deal with that?
Right, so basically that's why we use geometric information as well. So there are some cases that can only be captured by geometric information, while some cases can be captured by semantic information. So basically, we collect some data in our work sites. So basically, it can be regarded as, we saved this environment before, and we annotate them according to the traversability criterion. And so, so the classification should be relatively accurate. And if it's not, then it can either be detected as from geometric information, or it's just a corner case that we need to handle.
Mm-hmm. Any more questions from audience? Well, if there isn't, maybe I'll ask one more for Hydra from Nathan. So at the bottom level, you rely on semantic segmentation, right? So what if some objects are unknown? You don't have any categories for them.
Then they don't get picked up by the semantic segmentation. But I think we're interested in looking at techniques where you can build in like unknown object categories in addition to the like base 2D semantic segmentation network.
Okay, thanks. Okay, thanks. No questions, so keep asking until somebody comes up with question. So question for Andre. So I was curious about the how much you can generalize outside the input image. Like, is it mostly interpolation between the two views that you give as input, or is it able to predict views that are beyond the interval between them?
Yes, so all the results we show are extrapolation results, so we always go outside.
How much can you go outside, usually?
That really depends on the situation. So if you have only geometry very far away, you can go very far outside. If you're very close to objects, it's obviously a more difficult problem then. So it really depends.
Okay, thanks. Yeah, thank you all. Yeah, so let's thank the speakers again.
Okay, everyone. So we now have the poster break, the poster session and coffee break. Just about the timing, if you don't need to drop things off at your hotels, you can go ahead and stay here until about 6 p.m. and have enough time to get to the banquet. If you want to drop things off at your hotel, probably leave around 5:30 if your hotel is nearby. Otherwise, hope to see you on the boat, and let's set sail.